So shall we start, Sushmita?
Uh, Gaurav, just 30 seconds. We are setting it up on YouTube. So once it goes live, please.
It is
Go
already
ahead,
streamed.
Gaurav.
Okay. So welcome all to second day of Soft Matter Young Investigators Meet. And first session of day 2 will start with Dr. Aditya Bandyopadhyay's talk. So over to you, Aditya. You can start.
Thank you very much, Gaurav. A very good morning to everyone, the panelists and people watching this live. So today's talk is going to be about reocoalescence and universality that we find in the overall process. So coalescence of drops is quite important in a host of physical phenomena, and not just in physical phenomena but various applications in engineering as well. In particular, processes which involve condensation, they involve the coalescence of drops originating from a vapor phase. They are particularly important for designing heat transfer equipment where there is a phase change occurring, and how exactly condensation can help in promoting heat transfer by making a transition from drop to film. That is quite important. In spraying and coating, depending on the nature of flow, sprays can be thought of not just fragmenting, but in zones of low shear and low flow rates, they do coalesce. So the entire distribution of droplets depends quite heavily on the coalescence characteristics and the flow. This is particularly important for enhancing combustion. In various industrial processes, such as in petrochemical industries, in chemical processing of immiscible fluids, the process of fragmentation and coalescence hold the key towards enhanced reactivity and throughput. Moreover, apart from fluids, in the processes of sintering, the elevated temperatures and the pressures, they give rise to various coalescence and merging behavior of powders, and this is also dictated by the tendency of various particles which are fusing together to coalesce. Another interesting observation from nature is that of raindrop growth. So when precipitation occurs, there is first a process of coalescence of very small diameter drops, and during the process of falling down towards the earth, it undergoes a host of physical changes which involve fragmentation, as seen from this very famous experiment in which flour was used to assess the distribution of raindrops. So it is quite apparent that coalescence as a process in general is observable in many areas of science and engineering. But the key difference is the physical behavior of the drops, or the physical properties of the drops, have a large bearing on the overall process of coalescence. In the bottom panel, there is a screen grab from the Kaber experiment, which is the extensional breakup rheometry. In this particular experiment, a film of liquid is squeezed between two plates, and the plates are rapidly separated from each other. Upon rapid separation, the process evolves in the following manner. There is first a liquid bridge between the two drops. The first drop is attached to the lower surface, while the second drop is attached to the upper surface. Now, depending on the rheology of the drop, or the liquid rather, there is a evolution of the neck to a filament and then breaking up into a string of droplets, which is quite reminiscent of the Rayleigh plateau instability. So this particular evolution of the neck radius, the radius of the bridge between the two drops, gives us insight into the nature of the rheology. If this was to be a Newtonian fluid, it would not form such a bridge but rather it would immediately fragment into various small droplets dictated by the Rayleigh instability. The fact that the fluid is elastic in nature, or rather has a component which is elastic in nature, gives rise to a persistent stretching of this particular bridge, and consequently the neck radius evolves in a certain fashion, and that is a signature of the elasticity, which is also quantifying the rheology of the liquid. So Kaber as an experiment was quite insightful in helping physicists and rheologists probe into how a tackiness of a system can be, and such kinds of system properties cannot be ascertained by using the classical rotational rheometry. In the case of coalescing drops, so we are trying to assess the inverse phenomena, which is, to be fair, quite logical and straightforward. Instead of extending two drops, we are investigating how two drops would coalesce. So the same neck radius, but you imagine the inverse process. Instead of having a long elongated bridge, we are simply bringing two drops close together and they merge. So in the case of Newtonian fluids, the scaling is quite distinct. There is an initial time where the surface tension and viscous forces, they balance each other, resulting in a ballistic growth of the radius. So radius, I am referring to the neck radius. Beyond a certain time, at large times, there is a square root of t dependency on time. So the radius transitions from a linear to a square root behavior at a certain critical time, and that is all dictated by the Ohn-Schorge number. So the Ohn-Schorge number is quantifying a combination of inertial, viscous, and surface tension effects. So this was a very classic experiment, which was originally by the group of Jens Eggers, Howard Stone, and their co-workers. But there was some controversy as to at what time does the viscous inertial transition occur. They had predicted a time which was of the order of some nanoseconds. But later on, the group of Nagel, they showed that the scaling based on which they could arrive at such a crossover was not correct. And they were able to precisely show, with the help of electrical conductivity based coalescence measurements, that the time takes order of few milliseconds. So the key point is the transition for aqueous substances like water, or even their mixtures with salt and all, they take something which is order of milliseconds. And in the case of elastic fluids, where the presence of polymers can dictate a certain kind of relaxation towards equilibrium, that we expect that there will be a competition between this crossover time and the elastic effects brought about by the fluid. So the elastic effects are not just there as a crossover indicator, but rather it is quite interesting because the manifestation of elastic effects is because of the rate of strain that a fluid experiences. The process of coalescence has initially a very high rate of strain, and that rate of strain eventually dictates the entire evolution of the flow. So the question is whether the inertia of viscous scaling is something that would be prevalent for the coalescence of non-Newtonian drops, in particular elastic drops, and what is the role of rheology towards dictating the characteristics of the entire phenomenon. So we do expect the presence of multiple timescales, and we expect that the presence of elastic timescale would interact with the viscous and inertial timescales. And the fact that the manifestation of viscoelastic effects is due to the rate of strain. The process from the initial neck formation to the end of the coalescence would have the elastic effects all over the entire time span. So we expect that the relaxation should compete with viscous and inertial forces, and it should extend over the entire time domain. So these are sort of the physical arguments that we proceeded with. The experimental details are shown. So there's a stage which can be controlled. At, at one end of the stage, we have a droplet generator. So basically we dispense a small drop and then we move the stage very slowly. And there is a substrate on which there is a already it's a deposited drop of the same fluid. When they are brought close together, they coalesce, and the imaging is done with the help of a high-speed camera. So the evolution of the coalescence is characterized by two primary length scales. The first is the neck radius r, and the second is the height of the bridge. So if you look at panel C, you will see that initially the radius is quite large compared to the height. But as time evolves, the height becomes of the same order of magnitude as the radius. So the two diagrams are shown for, so the first diagram is for PEO and the second diagram is for water. So for PEO, we see that the height remains quite small for a very large time. So you will see that the aspect ratio of the bridge is quite small compared to the aspect ratio of the bridge for water. And that does say that during the entire process, if the height is quite small, if the gap is quite small, the flow that will be initiated inside the drop will cause a rather high strain rate, which will cause the elastic effects to be persistent over a long time. The different polymers that we have employed over here are PAM, PEO, PVA, and PEG. PVA and PEG have significantly lower molecular weights than PAM and PEO. And consequently, PVA and PVG, as we will see later on, they are not as elastic as PAM and PEO. The concentrations that we have employed is also written, and the concentrations have been chosen in such a manner that below a crossover limit, there are certain data sets, and above a crossover limit, there are certain data sets. So the crossover is a quantification of the entanglement of the polymers. So there is a dilute regime and there is a dilute entangled and unentangled regime. So we wanted to impress that the observation that you see is not just true for weakly polymeric fluids, but it extends over a broader range of concentrations of polymers. And that even for highly entangled fluids, for example, in the case of PEG, you do have the same phenomenon occurring. So the entanglement concentration is typically 5 to 10 times the crossover concentration. And a standard protocol has been adopted to prepare the solutions because some of these polymers are not that easily soluble in water. And the purpose of choosing these different polymers is that they span across a spectrum of relaxation times, and that also gives us an insight into whether this entire universality is true only for fluids having a very small relaxation time or a high relaxation time. So just a small overview of the rheology. So for PAM and PEO, so for PAM, there is no, the strain rate required to obtain the zero strain viscosity is quite less. Okay, so it is much lower than what the machine could give. Whereas for PO, you do get the plateaus. And overall, they do show a shear thinning behavior. As strain rate increases, the perceived viscosity also reduces. Similarly, PVA and PEG, the elastic component is there, but the zero strain viscosity does not change significantly as the strain rate is increased. Surface tension for all the three or all the four solutions is varying from something around 47 to 72 millinewton meter. So from a density viewpoint, all the fluids, because the concentrations are maximum at 24% weight per volume, the densities are assumed to be not significantly different than water. They are all dissolved in water. Let us look at how the raw evolution of the neck radius happens in time. For reference, the plot of DI water is also plotted. So DI water does show that initial ballistic growth followed by a square root of time. Whereas for PAM and PEO, the long time evolution seems to be a power law with an exponent of 0.36. For PVA and PEG, the long time exponent increases to somewhat around 0.39 or say 0.4. PVA and PEG are fluids which are characterized by significantly low relaxation times and a very characteristically steady viscosity, shear viscosity. So the PVA and PEG exponent is tending towards that of a Newtonian behavior, whereas PAM and PEO have a much lower exponent of 0.36. It is also seen that the characteristic velocity of the neck radius. So basically, you can find out the characteristic velocity of the neck radius from this particular curve. So that gives us more insight into what kind of parameters should be chosen for undertaking the scaling operations. So in this particular plot, we have rescaled the radius and rescaled the time. From Buckingham pi theorem, one can easily deduce from a balance of elastic forces and capillary forces that the characteristic radius should be of the order of square root of mu naught times lambda, where lambda is the relaxation time, mu naught is the kinematic viscosity of the solvent. And the fact that the initial neck is quite confined, it is far away from the walls, and the initial growth is quite rapid. So these observations lend us to an assumption that there is no inherent time scale that should be present in the initial physics of the problem. So that absence of any length scale can be constructed from a scaling analysis, that there should be a length scale which should depend on a combination of the two viscosities, or rather the viscosity and the relaxation time. The characteristic time is the Ohnesorg number times the lambda, and this scaling encompasses all the effects of viscosity, of surface tension and inertia, and it also incorporates the relaxation time lambda. With this set of parameters, T by lambda, Ohnesorg number, and the mu lambda square root of that, there is another dimensionless group which is C by C star, where C is the concentration of the solution and C star is the crossover concentration. So when we fit all the data according to this, so T by lambda raised to 0.36, Ohnesorg number raised to minus 0.36, and C by C star raised to minus 0.432. All the different distinct data sets like this, I've just shown a very small subset of the data sets, but all the data sets, they collapse to a single curve, and they seem to lie on this particular relationship. So then the question is whether, so what is the rationale behind such a weird power law scaling? This is the question that we had after achieving this kind of a fitting. So towards this, there is no obvious answer. And the lack of an obvious answer stems from the fact that the elastic effects are not localized to a certain regime. They span over the viscous and inertial regions. So because of this, we tried to justify the observations with the help of a linear Fanthian Tanner model. So we assume that the flow is quasi-steady, and that's a very strong assumption. But based on this assumption, once we find out the solution does check out with this particular assumption posteriori. Okay, so we can make an assumption, we can find a solution, then we can feed this approximation to the Gurney equation and see whether that approximation was correct or not. And such kinds of things is quite common to do in convective models. So we start off with the PTT model. We write down the governing differential equations. We introduce a seemingly arbitrary rescaling in terms of the Weisenberg number, but this scaling helps in maintaining the orders of magnitude in the momentum equation, nothing else. And Weisenberg number square times lambda, so we end up with combinations such as this. And the second simplifying assumption in order to achieve any kind of analytical progress is that lambda times Weisenberg number square is much less than 1. And this assumption is valid for all the different fluids that we have considered. For example, for PG, the relaxation times are 10 to the power minus 6 milliseconds, which is quite small. So this number is expected to be quite small. PVA is 10 to the power minus 6 seconds. PEO and PAM are order 1 millisecond, but the Weisenberg number is quite small. So this assumption is generally true. But the other simplifying assumption is regarding the trace of the stress tensor. So it should be a trace over here. Is that 1 plus this trace term is approximately this term. So this tau times kappa lambda Weisenberg number by eta that dominates over 1, that is much larger than 1, where kappa is a fitting parameter of the PTT model. So all this approximation can help us simplifying the constitutive behavior to this. So the order of magnitude of the shear stress in the R direction and the RZ direction. So they can be achieved from this. So once these relationships are obtained, we can plug them into the momentum equation and obtain, using the conservation of mass, a Gurney equation, rather the conservation of momentum, a Gurney equation for the evolution of neck radius. So essentially from the momentum equation, we will obtain an equation in terms of the velocity. So in this particular context, the velocity is the rate of change of the neck radius. So that is the order of magnitude. So ultimately, this final equation that we've obtained is a lumped equation which clubs together all the different terms. So there's an inertial contribution, there's a pressure contribution from the Laplace pressure, and there's a viscoelastic contribution. So all these reduce to this single lumped equation. So this is not an equation which is microscopically resolved, but by considering a control volume and writing down the averaging equations across that control volume.
So Aditya, last 5 minutes.
Yes, I'm almost done. Okay. Thank you. So we obtained two parameters A1 and A2, which are in terms of these simplifications and the Ohnesorge number. And once you solve this equation numerically with the Runge-Kutta method, we do obtain this kind of scaling. So there has to be a square root over here. Pardon. So that also gives rise to the t to the power 0.34 scaling. And that is remarkably close to the t to the power 0.36 scaling that we see from the data fitting. And one could argue that, I mean, at the second decimal place, it's not really that much of a hassle. So to conclude, we have shown that the polymeric contributions to the evolution of the neck radius spans all the way from inertial to the viscous from the viscous to the inertial regime. All the data sets coalesce to a single master curve when they are rescaled as per the equation shown. And this gives some insight into how we can possibly exploit this method to assess how viscosity or relaxation time can be measured through a complementary Caber-like mechanism. So in the Caber mechanism, we have extensional geometry. So we could coalesce two drops of the same fluid together and also achieve the same data. If we are able to measure the solvent viscosity, which is not that difficult, one is in a position to translate these data sets into a lookup table and figure out what the relaxation time of a certain unknown solution would be as well. So with this, I end this particular talk. This was published in Soft Matter recently. So I thank you for your kind attention.
The forum is open for question and answers now. We can have question and answers. We have questions now.
There's a question by Vaibhav.
Yeah. Vaibhav, you can speak.
Or you can put your questions in Q&A if you're not able to.
Where can I see the chat?
Gaurav, if can I ask you a question? While he tries to frame the question.
Sure. Yeah.
Hey Aditya, really nice talk. I have a so if you see, you showed that these 4 polymers that you are using, they showed very different. A couple of them at least showed Newtonian-like behavior. Couple of them were shear thinning, and then some showed. That in some cases the surface tension was constant, in some cases the surface tension was decreasing, but yet the scaling that you did, the radius versus time data showed, they were pretty similar. Of course, you did say that 0.36 versus 0.39, are they really same or different? But I was surprised that they seem to have very different physical properties as well as interfacial properties, but yet they show this evolution. So any thoughts as to why that is?
Yes, so it's quite remarkable that you have that we have such a behavior happening, that despite there being so many disparate scales and disparate behavior of various properties, one does have that collapse onto a master curve. So what drives the flow is the presence of the Laplace pressure, especially in the initial times, because of the small curvature. Okay, the small radius of curvature leads to a flow which is primarily driven by the Laplace pressure. And as the flow is driven towards equilibrium, the presence of this Laplace pressure is what is so the Laplace pressure is trying to take the drop towards equilibrium, while the elastic forces, so if it's almost, if you can imagine, you're trying to pull a rubber band and there's a elastic recoil in the orthogonal direction. So that behavior is sort of trying to balance it out from the very first get-go. But yes, that still poses the question, despite the surface tension being a strong function of the concentration, which is not reflected through the Fanthi-Tanner model. The Fanthi-Tanner model does not account for the crossover concentrations. It's strictly speaking valid for dilute species only. So despite that, it is able to achieve that master curve. And what I think, and what I believe rather, is that all this, whatever I've shown, everything is in its infancy. This is an observation which we have done quite recently, and there are more unanswered questions than there are answered questions. So this is something which we would be looking more into, in particular the microscopic models, because whatever we have right now is sort of a lumped parameter. So even though there are variations with concentration and all, you sort of smother out everything because of the averaging over a control volume. So possibly that is getting rid of all those nuances.
Okay. Yeah. Thanks so much. Thank you.
Okay, thank you, Aditya. I don't think we are left with any time now for any more questions. Those who have questions, they can write an email to Aditya. Would that be okay, Aditya?
Yes, that's fine. That's
Yeah.
perfectly fine.
All right.
I'll
Okay.
just like add that if you have any questions, please put them in the Q&A. Aditya, please stay back for a few minutes. I mean, obviously you have to stay for the entire conference, but please look at the Q&A for some more time and answer the questions because
All right.
hands up.
All right, thanks. So I'll stop sharing the screen, right?
Yeah. Thank you, Aditya.
Thank you.
Is Kaushik here already? Yeah. Okay. So the next talk is by Kaushik Vishwanathan from IISc. So Kaushik, you can start. You can share your screen, Kaushik. Yeah.
Can you see my screen?
Yeah, we can.
It says I'm unable to start video. I don't know why that is. So I'll just continue without the video.
All right.
Okay, so it's the full screen is visible, right? Gaurav, can you just confirm?
Yeah.
Okay, great. So thank you so much. I'm very excited to be here. Talks yesterday were extremely interesting. I just wish that the time limit of half an hour wasn't really enforced, but still it was a fantastic set of talks that we have yesterday. My name is Kaushik. Like Gaurav mentioned, I'm an assistant professor at IISc. The work I'm going to present today is in two parts. The first part is already published. The second part is not, and I'll focus on the second part. And it mostly was done by Akib, who was a master's student who just submitted his thesis. He's heading to UT Austin for a PhD. And we hoped we could get a preprint out before this talk, but unfortunately we haven't been able to do that. So if you need additional details, please let me know and I will be happy to provide them. Okay, so the system we're interested in is very, very simple. So you take a hard object, you take a soft object, you put them together under some normal force, pressure, and then you slide them remotely. Okay, so this is, let's say, your hard object, the blue, and the gray is your soft object. Put them together, there is obviously an interface, and then far away from the interface, you apply a remote sliding velocity. Okay, now this is very, representative of several situations. For instance, in lithography, this is something that you will always see. You have a die, like soft implant lithography, you have a die that's going to pattern a substrate, presumably, and so you see exactly this type of interaction. It turns out it also happens in locomotion of invertebrates. This is a snail, and it's has no limbs, so it basically has to rely on the interaction between its soft body and the ground, which is presumably much harder than what it is. Now, why are these interesting? They're interesting because apart from applications, their properties are very unique. When you bring the rigid body in contact with, let's say, an elastic polymer, which is a representative soft body, the asperities or the wiggles on the surface that are usually responsible for friction are completely secondary. And why is that? The reason is adhesion. And adhesion is mediated by these polymer chains. They're all causing the two interfaces to stick to each other. And as a result, the interface can deform and the deformation can influence the friction. So this is not just a situation where you measure coefficient of friction and you can be happy. You have to take into account the elastic deformation. That's what makes it very interesting. So I'll ask three questions. The first two questions are basically building up to the third. Okay, so the details in the first two questions will be reasonably skimpy. If you want additional details, I'll be, like I said, happy to provide them. The first question is, what do experiments tell us? So if you take a simple interface, just like this, I have the rubber, which is the gray again here, soft polymer, and I have a hard object, which is a lens. It's made of some plastic, presumably some glassy plastic, much harder. Young's modulus is much higher than the rubber. Okay, and you bring them into contact and you observe. Both are transparent and the lens is mounted on a transparent surface, and so you can look right through the interface. And if you look, this is what you see. It's backlit, of course. You see a light region where the lens is contacting. So all along the length of the lens, you see a contact, which is a light region with a width, certain width. And the rest of it is dark, right? And what you do now is simulate that interface sliding business. You just take this and far away from the rubber, you just slide, okay, at a constant speed, V0. Okay, so you bring these two together, apply a force, and you slide this remote from the interface. Simple experiment, okay? Now, there is a phenomenon called stick slip that happens, and it's not just a trivial phenomenon, but it happens as a result of some very interesting dynamics. It turns out there are two types of waves that can travel at the interface. So even though the polymer is being moved remote from the interface at a constant speed, I've indicated that here, V0, V0. These are two images. I'm going to play a movie and show you what exactly happens. Even though this gray area far from the interface, out of the plane of the screen, is moving at a constant speed, the interface doesn't really do that. So I'll show you what happens in one case. There is a little tracer you see in black, which is stuck on the interface, so it moves with the interface. And just observe how that moves, okay? So it remains stationary, and then there is a little pulse that comes and pushes it forward. And once the pulse goes, it becomes stationary again. Okay, so it's initially stationary, pulse comes, pushes and goes. Now, this pulse people have studied before. It's named after a person called Charlemagne, who was the first to image it in the 70s. And it's called a Charlemagne wave. And I'm going to call it the plus wave because presumably there's a minus wave, which is coming next. And it has some curious properties. Firstly, if you slide the polymer to the right, notice these guys outside the contact are moving at constant speed. There are two dots at the bottom. If you slide the polymer to the right, the wave goes from left to right. So it goes parallel to V0. That's why it's called a plus wave. Okay, this wave is in the same direction as V0. Now, if you change the conditions a little bit, change the normal load, change the velocity, sliding velocity, remote load, and so on. Details are not important for now. You can find them in this paper, the experiments. Then another thing happens. Now there's a wave that goes in the opposite direction. Okay, so you look at this point, that's again on the interface. This little dot, it will jump to the right. It has to go to the right because you're moving it to the right, far away from the interface. But the wave is going in the opposite direction. So this is negative of V0. So we call this a minus wave. It's called a separation pulse, and we call it a minus wave henceforth. Okay. Now these two waves go at speeds that are completely orders of magnitude smaller than what is called the Rayleigh wave speed or any typical elastic wave speed, right? Which is of the order of kilometers per second. These are of the order of 10 to 100 millimeters per second, so really slow. And that makes them very peculiar. Now, if you look at what, if you measure the shear stress, the shear force, and you normalize it with respect to the contact area and the shear modulus, as a function of time, if you look at that, then you will see oscillations like this. So basically what's happening is the interface is stationary, 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 then a wave goes and then the force falls. Okay, then again it's stationary, stationary, wave goes, force falls, and so on. So it's repetitive. So this wave phenomenon keeps happening over and over again. For the negative, the minus wave, you see the same situation, but it's somewhat different. You still see oscillations. Oscillations die out for various reasons, which I will not get into. But again, you see oscillations, distinct frequency, distinct amplitude drop, and so on. Okay, so this is a perfectly periodic phenomenon. It keeps happening. The interface only moves because of these waves. So it doesn't move uniformly, even though the remote velocity is uniform. Good. So what do these experiments tell us? They tell us, well, there are two waves, plus minus. They have two wave speeds. Both are really slow. The waves have distinct properties. They have distinct frequency, forces are distinct, and so on. But they also have some similarities. The first is both waves cause the interface to slip in the same direction, which is the direction of remote V0, right? That's the direction which the interface has to move. And they have identical interface boundary conditions. So that dark band that corresponded to each wave basically is a region which is detached from the rigid body. So the polymer is detaching from the interface. That detached zone is going from left to right in one case, right to left in the other case. Okay, so this is what the experiments tell us. Good. What's the second question? The second question is, can we make a common theory for both of these waves? Now there are two waves. The interface conditions seemingly look the same. You have a zone that is detached. You have a zone that is completely stationary outside of the wave, but they're going in opposite directions. So what is going on here? Now, I'll give you a quick background. If you usually have a traveling wave solution, they come as a result of some PDE, right? So this is a standard 1 plus 1D wave equation, and depending on what phi is, whether it's the pressure in a compressible fluid, whether it's a vector, electric field, and so on, you get different types of waves. And you can derive these from other governing PDEs, for instance, Navier-Stokes and momentum conservation, and so on for the first case, and the equations of electrodynamics for the second. The problem is in elastic materials, the equation looks a little bit more complicated. And the reason it's complicated is because you have two types of waves. You have what are called longitudinal waves and you have what are called transverse waves. And both waves are super fast compared to what we're doing here. Our velocity of sliding is reasonably slow. It's a couple of millimeters per second. Our wave speeds are faster than V0, but they're still very slow, order of hundreds of millimeters per second. But the intrinsic speeds of elasticity are really fast. Okay. So you can't really use elastodynamics naively to solve this problem because of this condition, C less than CT and CL, and you also don't know why these waves are forming, right? So initial conditions are a priori not. So what do we do about this? So we set up a special configuration to describe these waves, and it looks like the following. You assume firstly it's a one-dimensional model. Okay, just assume that everything is one-dimensional. There's nothing into the depth, the y-axis in this figure. And you look for exponentially decaying elastodynamic solutions decaying from the interface. So here z equals 0 is the interface. The blue rigid fellow is on top, the elastic fellow is the bottom. And you separate this initial condition problem you get rid of by converting it into angular coordinates. So you make a periodic boundary on left and right because the waves are periodic, they keep coming and going. You can convert from x to eta and you sit on the wave. So you move to what is called a co-moving coordinate system. Basically, when you do this, the wave is at the center and it's stationary. Okay, so that helps immensely, it turns out. Now, for both of these cases, there are two zones that you can identify. One is the zone corresponding to the wave itself, which is the zone of separation, that dark band that you saw in the images. And there, because there is separation, the stresses are 0, right? It's a free boundary at that point. And the stress, again, this is at the interface, so it's at z equals 0. There is the rest of the zone, which is stationary. And because it's stationary, the velocity in that zone is 0. Okay, so this becomes, from a classical elastodynamics point of view, it becomes what is called a mixed boundary value problem. And mixed boundary value problems are kind of painful to solve, as it is. Now you have the additional complication that the wave speed is super small. So it turns out you can do a very simple expansion, perturbation expansion, in the wave speeds. Okay, so you have a very small, naturally very small parameter. You just make use of it. The equations are all just, stuff that has C by CL, C by CT are all polynomials. So it's a very standard perturbation expansion, nothing fancy. If you do that, I'm going to give you a few equations because they're sort of important for what comes next. I will skim over the details of the equations, but if you want more info, we can give it to you at the end of the talk. Good. So this is the detachment zone. Detachment zone stress is 0 because it's detached. So you can write down what's called a dual series equation for the stress. In the attachment zone, the velocity is 0 because it's stationary. So you can write down a dual series equation for the velocities. Okay. The velocity is 0 in this zone, which is the sticking zone. And in the detachment zone, there is a velocity, right? The interface is moving, the wave is moving. So you need a velocity. We call that an unknown phi. The z velocity we call an unknown omega. Okay, so the stresses and the velocities obey these pairs of dual series equations. Now it turns out if you see a dual series equation and you've seen it before, the first thing you would try to do is convert it into what's called an integral equation. Okay. Now you can take those two dual series equations I showed you and convert it into this. Again, the details are algebraically involved, but they're fairly straightforward. And the integral equation governs the x velocity and the z velocity. That's in phi and omega. That's what we had here, right? Phi and omega. So these equations are a little bit non-trivial. Actually, they're highly non-trivial. The reason is the following. Firstly, they're integral equations. So phi is unknown, omega is unknown, phi is unknown, omega is unknown. The unknown array is inside an integral, and it's not just an ordinary integral. The integral is singular. So no matter what value of the integrand you have here at xi, at some point, you will have a singularity because of the cotangent function. Okay, so these are called singular integral equations, and they're coupled singular integral equations to add to the problem. Now we realize that if you make the incompressible limit and you do this perturbation business further and you drop all order of c² terms, then you basically end up decoupling these two equations and arrive at this set. So you have two integral equations now and two what are called side conditions. Again, the details are peripheral. But these two integral equations will give you the velocities horizontal and vertical, okay, of the interface within the detachment zone. Minus alpha to alpha is the detachment zone. Okay, so these are all the equations I'm going to show. This is for the general new case, and this is for the incompressible case. Okay, so two sets of equations. Okay, what is the third question? What do these equations tell us? This is really the crux of what I'm going to say. We've set the stage and set the framework. Now we'll see what these equations tell us. First, the incompressible limit, it turns out, despite that morass of equations I threw at you, is solvable exactly in closed form. Okay, which is quite remarkable. It turns out the structure is so nice that it actually falls into this very standard class of an integral equation, which can be directly inverted. And there are three parameters that you need to keep in mind. There's a dimensionless wave speed. which is C by V naught. V naught is the sliding speed. I have a pi there for some normalization reason, doesn't matter. There is a wave number which depends on this dimensionless wave speed A, inverse of that, and delta x. So delta x is the amount of slip that a single wave causes. So as a wave came, the interface jumped by some delta x, and so that comes into the wave number. And then there's a dimensionless shear stress, of course. I have non-dimensionalized with the shear modulus, mu. Now, if you put a constraint on the solution, remember this nu equals half is exactly solvable. If you put a constraint that the interface velocities and displacements have to be in the same direction as the remote interface, remotely applied velocity v naught, then it turns out you will get two solutions. Okay, and these two solutions correspond exactly to the plus wave and the minus wave that we saw in the experiment. And not only that, it also gives you a theoretical limit, sort of academic. I'll tell you why in a minute. It gives you a theoretical limit beyond which these waves just simply cannot exist. Okay, that's given by 4 by pi of this non-dimensional tau, the remote shear stress. And the reason it's a little academic is because you're already past the elastic limit once you go past 0.3, 0.4, right? You're already in the large deformation domain, and really none of this stuff is a little bit suspect in the large deformation. But nonetheless, if you just analytically continue the solution, you will get this, what we call a bifurcation diagram. Okay, so this now tells you two things. It tells you first that there are two waves, plus wave, minus wave, that solve the equations we have set up. Okay, so the two waves naturally come out of the same framework. You don't have to do anything additional. But it also tells you another thing. This gives you the minimum velocity. Remember, A less than A max is the inverse of the dimensionless wave speed. It gives you the smallest wave speed that you need. So you can have a continuum of wave speeds ranging from a value for a given value of tau. Let's say here tau equals half. This point gives you the minimum wave speed, and then you can have other wave speeds on top of this. Okay, and that's very important because there is no velocity scale in the problem. We've removed the velocity scale. Remember, C by Ct, we did perturbation expansion, put nu equals half. All of them are gone. So there is no inherent velocity scale to set the wave speed. And that's consistent with the solution, which tells you that you can have all possible wave speeds above a certain threshold. Good. Now, if you go to the arbitrary nu case, pardon me, it's actually numerically solvable. Okay, the next couple of slides that I'm going to show you will contain all the results, which took us several months to do. They're highly non-trivial, but the details again are algebraically involved, and I won't go into them. First, you can solve for the interface z velocity. So, how is the interface peeling off? Okay, and you can do this for different nus. Nu equals 0.5 is incompressible. It matches numerical solution, matches exactly with the closed form result that we have. Nu equals 0.2, 0.3, 0.5 are shown here. You can see the inset region where the crossover happens. So Vz dot positive means that it's reattaching. Vz dot negative means that it's detaching. The z-axis is upward. So you can see the zone at which the velocity changes from detachment to attachment right in the middle. And depending on nu equals half, 0.2 or 0.35, this happens exactly at 0, which is at the middle of the interface, nu equals half. And it shifts to the left as nu becomes smaller and smaller. So the immediate consequence of this is the following. When you have a material that has nu equals 0.5, it's very happy to detach, okay? But it's sort of reluctant to reattach. That's important. Please keep that in mind. We'll come to that at the end. Good. The same thing you can see with the x velocity. Again, x velocity tells you in what direction, in the horizontal sliding direction, what is the interface velocity. The two dashed lines in both of these curves are the ends of the detachment zone. So outside this, the velocity is 0, it's stuck. Right? This is exactly where the wave is. Outside this, there's no wave, everything is stationary. We can now calculate the stresses as well, again numerically. The stresses end up being singular at the ends of the contact. The velocities were also singular. If I just go back to that for a second. The velocities are also singular at the edge of the contact. Turns out that's not a violation of any conservation law at all by any means. Velocities are known to be singular in many of these problems. And the stresses are singular outside the contact. So within the detachment zone, there is no stress, it's detached. Outside the detachment zone, there are stresses and they become singular at the ends of the detachment zone. And again, the stress readily becomes singular close to the detachment zone for nu equals 0.5, but the other cases it doesn't. Okay, the shear stress is a little bit more interesting, and this is what will lead us to the third question, the end of the third question. The shear stress looks basically indistinguishable from this graph, but if you zoom in, you will see that in the Detachment zone, again, the nu equals 0.5, nu equals 0.35, mu equals 0.2, they look very similar. In the reattachment zone, the nu equals 0.5 is happy to reattach, but the other two are not. Okay, so this reattachment really is very favorable in the nu equals 0.5 case, and that's also consistent with the fact that these types of waves occur predominantly in these rubbers which are incompressible. Okay, here is another interesting thing that comes out of this, which is if you take the leading edge of the wave, so the wave is traveling through the interface, if you take the leading edge, the front edge, it turns out to be exactly analogous to an interface crack. Okay, so here I've shown you the interface over here. The detachment zone is shown on the left, and the reattachment zone is shown over here. Okay, the stresses sigma by sigma. If you look at the previous curve, I showed you the stresses. If you plot the same stresses, you can do what people in the fracture mechanics community do. They do a cutoff zone, so you can determine a cutoff zone, and you can see how the cutoff zone varies as a function of nu. Okay, for various cutoff values, sigma by sigma equals xi, you put various values of xi, you will get different cutoff zone sizes. So this is like a process zone equivalent in a classical interface fracture problem. Okay, it turns out to be exactly analogous, and the route we've taken to arrive at the result is completely, anathema to what somebody in a fracture mechanics community would do. Okay, but still we've ended up at the same result. Good. Again, nu equals 0.5. The process zone is very small, so the fracture energy becomes stronger, and the attachment reattachment is readily done for nu equals 0.5, irrespective of what cutoff you put. Okay, now this analogy can be pushed a little bit, and you can draw what we'd like to call a phase diagram. Okay, and this gives you two parameters of interest. Delta x is the slip of the interface per wave. Tau r is the shear stress that is applied remote from the interface. Now, it turns out that this thing falls into three zones. The green zone is beyond the scope of our analysis, so we'll have to leave that out. Mixity is something we can't account for. The blue zone basically tells us that if, for a given shear stress, if I pick, let's say, a given delta x or a given size of the initial detachment, and I go up the tau axis, then in the blue zone, I can have d waves, which are these plus minus waves. And the moment I start having d waves, the leading edge, which is now like a crack, will not propagate. So think of it like this. If you haven't followed the equations, it doesn't matter. Think of it like this. If I have an interface and I have a little detachment sitting in the middle of the interface, if the conditions are such that the d wave propagation situation is possible, then the detachment will just translate past the interface. If that was not possible, which is this yellow orange looking zone, then that detachment will basically open up and it will crack and the interface will fracture. Okay, so this D wave sort of leads to a type of toughening of the interface that is usually not possible under any other circumstances.
Kaushik?
Yeah, I'm done. This is my last slide. So the final thing, where do we go from here, is what I'd like to end with, which is okay, here is the displacement. So this is what the displacement looks like, the ux as a function of time. So initially, the interface is not slipped. You're moving it remote to the right. A slip zone is coming. It's coming to the right, coming to the right. And for the plus wave, it goes in the same direction as V naught. For the minus wave, it goes in the opposite direction as V naught. You've seen that already, right? This is from the theory. Now, if you zoom out of this picture completely, okay, if you completely zoom out of both pictures, this zone, which we've spent so much time calculating, doesn't matter anymore. Okay, so it becomes like a step function if you zoom out. And this can be thought of as a topological defect. Okay, the condensed matter community has been studying these types of defects. It's something called the Ising model. And you can map this problem to a 1D Ising model. And this is where it becomes even more interesting, in my opinion, which is that in a 1D Ising model, it's known that defects are stable. Okay. In our case, the defects are unstable because they move through the interface and cause slip everywhere. So that's a fundamental violation. The second one is you could think of the applied remote velocity as being an external equivalent of an external magnetic field. Okay. Again, the 1D Ising model predicts that there are no phase transitions. It's a very well-known result. There is no spontaneous symmetry breaking. But in our case, we see that. So interface was initially unslipped, now it's fully slipped. So why does that happen? Ising model cannot answer that. Our situation probably can. And finally, what is the thermal limit of this equivalent? What is the thermal equivalent of this situation? So if you have a 2D interface, for example, can you have these different types of line defects scattered around and all of them causing slip in the same direction? What happens when you have two of these +1, -1 coming and interacting? These are questions that come up And there are very interesting topological techniques that you can use to address them, which is something that we're interested in and starting to look at right now. So with that, I'll just end. I'm done with the talk. So if there are questions, we can take.
We are open for questions now. Thanks, Kaushik.
Hi, may I ask a question? I'm Priya.
Yeah, please.
Hi, it was a very interesting talk. I just have a very layman's question. Right in the first slide that you showed, where you were showing videos of the waves themselves. So I see some sort of a morphology for the plus wave, um, if I may call it a meniscus. Whereas for the minus wave, we don't see that kind of a morphology when it's traveling. See, over here, you see a V shape. Whereas for the negative wave, we don't see. Is that any way interesting, or does that even matter? Or
Yes, okay, that's an excellent question. I was hoping nobody will ask that question. I was hoping people ask me about the equations, but that's a good question. The reason you see that is because the left wave is formed as a, I haven't said anything about how these waves form. I'm only talking about how the waves are moving through the interface. The left wave is formed because of a compressive instability on the surface. And when you have a compressive instability in a contact of this geometry, you will get a curling of the interface like it happens on the left. Now, can you predict that curling? I don't think it's quite possible right now. And what is the consequence of that curling? Well, the consequence is that you see these ripple type of things you're talking about. They lead to imperfect contact after the wave is gone. So you get these pockets of, and then we're getting into viscoelastic effect. So these will relax eventually, and then they will interface will reheal and things like that. Unfortunately, it was a little complicated, which we just conveniently sidestep. This right one forms because of a tensile necking instability. So this left one is a compressive instability, right is a tensile instability, and so in the tension you don't see these features.
okay, thanks.
You can have a couple of more questions.
Hi Kaushik, this is Tarak here. It's a nice talk. So I have one question where you try to compare with 1D Ising model. I see that most of the phenomena occurring in 2D interface. So why not, bringing 2D Ising model here?
Okay, that's actually a slightly intricate question. The reason is the spins, right? It's a +1 -1 spin,
Right.
and the remote velocity is applied only in one direction. Okay.
I see.
The interface itself is two-dimensional, but all the displacements out of plane that you see here, displacements out of plane, I mean out of the plane of the model, so in the y vertical direction here, are very minimal, right? So the 2D Ising model will not really give you anything. I mean, it's topologically equivalent to a 1D model. It has to be equivalent to a 1D model because you cannot have you cannot have a region which is slipped and have a displacement in the perpendicular direction. I don't know that. I mean, if I had a board, I can show you how that works, but you cannot have displacement in this direction and have slip in this direction.
I see.
So it has to map exactly to the 1D case.
Okay, got it. Thank you.
Yeah.
Yeah, we can have one more question. Kaushik, can I ask you something? I mean, I think in the beginning you showed a picture of a snail moving, and I believe they show negative wave, right? When a snail is moving.
Yeah, this one.
Yeah.
Yes. Okay. It turns out that in this biological locomotion, I have this book. I've actually read through parts of it, believe it or not. These animals show these things called direct waves and retrograde waves. So either the snail, I think, shows the opposite. It goes from head to tail, the minus wave. So it sticks its neck out, creates a tensile neck, and that goes to the tail, right? So it moves forward. The caterpillar does the opposite, right? So it compresses its tail, the tail creates a loop. That's compression again. This is tension. Same analogy, right? And that compression front goes to the head. So yes, it turns out that these analogs exist. I'm not making all of this stuff up. I'm only making some of it up, right? So they actually exist.
My question was, how does because it leaves a slimy liquid behind, which would be very viscous liquid. How would that modify the physics here?
Yes. Okay. Good. So this problem is not exactly mappable. The reason is this lubricant layer in the middle is responsible for the adhesion. So a priori, if you take a rough surface like this, right, this surface is not going to give you van der Waals adhesion with a soft body like this. You need something that's extremely smooth. And in a sense, you could think of the lubricant in the middle as playing the role of causing that adhesion between the soft body of this guy and the floor. Right? So it's, in that sense, enables the adhesion. The other thing is that this is an active system, so it creates these necks and compressions and so on as it moves. So these are not spontaneously generated. In our case, they are spontaneously generated because it's not an active system.
I see. Thank you, Kaushik. Thank you for a very nice talk. So we'll move to the next talk. The next talk is by Priya Gambhir. Priya, can you share your screen, please?
Yes. Okay, I am unable to start my video, but I can share my screen here. Can everybody see my screen?
You will make it full screen.
Yeah, sure.
Priya, you could try now to enable your video.
Sorry. The Dell has a very weird angle. Yeah. Okay.
Yeah.
Good morning, everybody. I'll start off my talk. I'm Priya Gambhir. I'm on the DST Inspire grant, working at the Center for Biosystem Science and Engineering at the Indian Institute of Science. Today, I'll be talking on this work we did during my postdoc, where we developed a spleen on chip. And I'll talk about how we fabricated it and what kind of experiments we did with it. So just to give a brief background to students who may not be familiar with a little bit of red blood cells. So red blood cells are these biconcave discoid shaped blood cells, which are responsible for oxygen transfer in the body. They are typically of 8 micron size diameter and 2 micron thickness. What this kind of shape does is it gives it an excess area. If you compare the RBC to a sphere of the same volume, the RBC has a very high surface area. Also, its membrane has this two-dimensional cytoskeleton, which is unlike the other cells which have a transcellular cytoskeleton. The red blood cell has only a two-dimensional cytoskeleton, which is made mostly of spectral, which has this dynamic linkages with the bilayer of the cell. So what these two things do is it makes the cell very deformable. And this is seen when we look at the sizes of the capillaries that the red blood cells have to pass through. They are more or less of the same size as that of the red blood cell and sometimes even smaller. And yet the red blood cell manages to pass through these capillaries without any issue. It faces the most extreme test when it passes through the spleen within the body. So what happens in the spleen is that if you look at this first picture, it's a small schematic simplifying the process of the splenic filtration. So what happens is that blood enters the spleen into the zone called the red pulp, through which it has to enter the veins. Now in the veins, the wall has these small slits called interendothelial slits, which are very narrow, less than a micron size. And the red blood cells that can pass through these slits are returned back to circulation. And the ones that cannot pass through are destroyed within the spleen itself. So this is done periodically within the body to ensure that only fresh and healthy red blood cells are always in circulation. Here is a micrograph of the spleen. You can see that this here is a red blood cell and over here is a slit that it has to pass through. So on an average, the dimensions of the slit in vivo have been reported to be around 0.5 micron in width and a thickness of 2 microns and length of 5 microns. So on chip, we want to mimic these dimensions. So we want to have channels which are less than a micron wide, and they have a length of 2 microns and a depth or height of 5 microns. So the motivation behind this work is we wanted to see what kind of dynamics does the red blood cell show when undergoing this extreme mechanical stress. This has not been done. This had not been done previously, at least to this extent. And also we want to enable real-time viewing of the deformation. And we wanted to show if the spleen that we make on chip is able to differentiate between stiff and healthy red blood cells, and is it a functioning device. So the main criteria which we had for designing the device is that first thing, it should be amenable to optical viewing. Therefore, we thought we will use the technique of replica molding with PDMS because it's most commonly used nowadays for biological samples at lab scale. So to do replica molding with PDMS, we would need a master mold. So we wanted to keep the microfabrication as simple as possible. So the most commonly used method is to use photolithography to prepare a silicon master. But the disadvantage of this technique is that it is difficult to obtain submicron structures. So what we did is that people usually use wet etching. So we tried to use wet chemical etching to reduce the features that we obtain on the master further so that they reach the submicron limit. And then we use that master to replica mold with PDMS. So this is the design of the master that we planned to have. We had planned to have. So we have this channel, which is a larger channel mimicking the capillary or an arteriole. And then there is region on the channel or device where there will be these interendothelial slits. Now, these slits, the dimensions on the mask, which is used to make the master, is larger. I'll come to it. That what do we use to decide on these dimensions. But once we finish off with the etching, we end up with the silicon master, which has these micro bridges, which are of the same dimension that we want to have in our device. So once we have the master obtained on silicon, what we do is that we pour PDMS on top of it and we get its negative. So therefore, within the PDMS, the micro bridges will form microchannels or submicrochannels. And then we bond it to a glass cover slip at the bottom to make a complete channel. And this is how we made the device. Now, a little bit of details about how we get the dimensions. So what we did was we used a silicon wafer, which was of 110 structure or plane. The advantage of using this wafer was that it has these 110 and 111 planes, which are vertical or perpendicular to the surface of the plane itself, surface of the wafer itself. So that will ensure vertical walls for the channel. And also there is another feature of this wafer, that is that the 110 planes are actually parallel to each other on the wafer. So that would ensure that the walls are parallel and vertical. Now the dimensions A, B, and C are chosen such that upon etching, you would end up with the dimensions L, W, and T. Okay, so let me mention this. So the planes 110 and 111 have different etch rates. The 111 plane is actually an etch stop, that is, it has a very low etching rate. So what happens is that we calculate ABC such that the etch rates for the 110 and 111 plane match up, and after etching for the particular fixed time, we end up getting the right dimensions that we need. So on the left, on the right hand side, these are a few of the optical micrographs of devices that we made. So you can see that for a given depth D, that is, we fix a depth of 5 microns, depth of the channel. For a given depth, we are able to manipulate the width and length of the channel quite well. So what we did was we went ahead and characterized this device a little bit using electron microscopy. Sorry for mentioning AFM, it's not AFM, but bright field microscopy. So this figure over here shows that we have a row of these smaller or submicro channels or micro bridges in this case, because this is the image of the silicon master. So within this row, we saw that we are getting a good maintenance of size. There's not much variation. And also that the walls are vertical and smooth. And the lower picture over here is optical micrograph of the PDMS device. So after replica molding, we obtained the PDMS channel device. And what we did was we cut along this line over here so that we get the cross section of the narrow slits. And what we have observed is that the walls are quite vertical and there's no bending or buckling of these within this channel. So let me go ahead and show some videos of the red blood cells passing through. So all these 3 videos are of healthy red blood cells. What we see is that the red blood cell actually enters the channel, and because its volume is larger than the volume of the slit, it forms this dumbbell shape within the slit, and then it comes out of the slit and tries to reform its original shape. In the second video, when I play it, you'll observe that there's a slight change in the exit shape. Tip is formed, but which is very transient and relaxes immediately. I hope the videos are playing. If not, just please indicate it and I'll see if they're in problem. In the third video, this is slightly different from these 2 videos. I just put in there because it was just interesting to see. The device here is not exactly mimicking the splenic slits because the depth is of 10 microns. So therefore, the red blood cell that is approaching it is already in a different morphology. But it was interesting for us to see that how would they behave when they have to face a inclined slit. And we see that there is slight asymmetry in its deformation. Now in the second, what we did was we had this collaboration with a clinic where they were looking at patients with sickle cell anemia and hereditary spherocytosis, which I'll come to next. So sickle cell anemia is a disease or a disorder wherein the hemoglobin within the red blood cells is mutated, and therefore it tends to form polymeric bundle. So it tends to polymerize when the cell is deoxygenated and form these bundles, which eventually lead the cell to form the sickle shape. In these videos, we chose cells which were looking biconcave and not sickle, just to ensure that there is no bias in the measurement. What we see is that the sickle cells also pass through these slits quite well, and they come out of the other end without any lysis. In the second video, we again see the tip forming for the cell, and in this case, the tip is quite distinct and it remains for a longer time than is seen for the healthy cell. Now, the lower video, we saw a new exit shape, which was an elongated shape, which was not seen for, which was very unique to sickle red blood cells. To point out, this RBC, even before entering, had a slightly elongated shape and was not exactly biconcave or spherical. Now, the third samples that we had were of hereditary spherocytotic red blood cells. In this disorder, what happens is that the association between the bilayer and cytoskeletal proteins is mutated, and therefore what happens is that the cells lose a lot of membrane during circulation and tend to become slightly spherical. They don't really have the biconcave shape anymore. So what we observed was a very startling difference in the behavior of these cells. The cells completely blocked the channels and were unable to pass through the channels. I mean, a majority of them. So in the video, you'll observe that the cells are coming in slowly and they tend to block all the slits. And the cells that pass through the slits show a very unique shape. That is, if you can observe, there's this jellyfish-like structure that the cells show. Let me pause it here. But then, yeah. So it forms this unique exit shape, which was not seen for the healthy and sickle cells. So after obtaining all these videos, we went ahead and tried to quantify or analyze the results. What we saw was that what you've plotted over here is the number of cells that are transiting and the number of cells that are entrapped. For the healthy cells, we see that a majority of them transit without any problem, which is true for even the sickle cell anemia infected red blood cells. The trend is completely reversed for the spherocytotic cells. What we see over here is, especially at lower pressure drops applied for the flow, we see that a majority of the cells are entrapped and the percentage is almost equal to the cells that are transiting even at higher pressures. So this can be attributed to the lower excess area that the cells have, and hence they are unable to deform, leading to their entrapment. Now, this specific shape that we see for spherocytosis cell might be because, so what we see is that at the leading edge or the downstream end, the cell shows a darker gray area, which is indicative of the hemoglobin filled red blood cells. And towards the trailing edge or the end, the upstream end, which has just exited, the color is lighter grayer, which looks similar to that seen for plain vesicles. So indicating presence of only black bilayer. So this was what we want to explain this figure with. And there are some kind of confirmation from one simulation work in the previous literature, and also some collaborative simulations that we did. What they showed is that at the trailing edge, the dissociation pressure is very high. So when the cell exits, it has extreme dissociation pressure at the end, which can lead to this detachment of the cytoskeleton and the bilayer. Therefore, leading to this kind of a unique exit shape. Now coming to the sickle cell anemia cells. So what we saw was that they could traverse through the channel quite well, but the exit shapes that they demonstrated, they had these two shapes. Sorry, something is blinking. Okay. They had these two shapes where they had a tip formation and there was this elongated shape formation. So comparing healthy and sickle cells, we see that healthy cells, the majority of them exit without any tip. And whereas for sickle cells, the majority of them exit with tip and a few with the elongated structure. For the cells that exit with tip for the healthy red blood cells, we calculated the tip relaxation time. That is how much time does this surface take to reach this surface. So when the tip relaxes or disappears. So we see that for the healthy cells, the tip relaxation time is quite low compared to that for sickle cell red blood cells. So this we can attribute to the cells having a higher cytoplasmic viscosity because of the hemoglobin present. So even in irreversibly, even in non-sickled cells, there is still the mutated hemoglobin, which has a tendency to polymerize. And therefore, the cytoplasmic viscosity is reported to be higher for sickle cells. And therefore, this incidence of the tip in sickle cells is higher, and also it takes longer to relax back. In the healthy cells, the tip formation might be due to the older RBCs present within the sample because we had not fractionated the red blood cells. One of the future works that can be done for this is what we plan to do is to have density fractionated red blood cells so that we actually look only for behaviors of the older red blood cell population and see if it matches this much more. So there was some additional, so this was part of this publication that we had out of my postdoc. The group went ahead and did some collaborative research work with the simulations group in the US. And what they could see is that the simulations could actually match our experimental results quite well. And then the advantage of simulations is to understand further. You can probe the cell mechanics quite a bit by changing them within your simulations. And what the key findings from that work was that the transit time for cells is increased if they have a lower surface area to volume ratio, if they have higher inner viscosity. And the cytoskeleton bilayer dissociation pressure is highest at the rear end, something that I just mentioned while discussing the spherocytosis data. Also, they show that within the slit, the biliary tension and the dissociation pressure is very high, but it does not reach the critical values that will cause rupture. And also the other finding that they could say is that the biliary tension was surpassing the critical tension, which leads to the opening of mechanosensitive channels. So which is the other thing that is a future plan for our work, for this work, where we want to see what kind of biochemical changes are occurring within the cell during its extreme deformation. So to summarize this work, we used photolithography and anisotropic wet etching to obtain submicron sized channels. So the spleen on chip, it can differentiate between healthy and diseased cells. And we could see some novel exit shapes and morphology, which is a potential to understand more about cell mechanics. So in the future, we plan to use fluorescence imaging and other artificially different cells and other protocols for understanding biochemical changes in the cells while undergoing this extreme deformations. So that is where I'll end, and I'm open to take questions and comments, feedback, everything. Thank you.
Thank you, Priya. We have a question from Rumia Parveen.
Yeah, please.
Asking that the size of the RBC is in micron range, which is smaller than the nozzle size.
Yes.
And how does the original shape of the RBC get distorted?
So this is the red blood cell. It's in its original shape of 8 microns. But as I mentioned, it has this excessive deformability. That is, it's a very soft structure. So therefore, it can deform and pass through this extremely narrow channel. I hope that is what is the answer you were looking for.
Yeah, I think let me see if she has responded to that.
Okay.
Not really. So, yeah, I believe that does answer the question that she's asking.
Sure.
We can have
Hello?
some. Yeah.
Hello?
Yeah.
Yeah.
Excuse me, ma'am. If that the RBC is very soft and can be deformed easily, then there is also possibility of reshape the RBC after passing the nozzle. So is it possible?
Yeah, so the thing is that healthy RBC, it's viscoelastic, so it recovers its shape.
Yes, it might be.
Yeah, but that is not true for the other cells where it's not as elastic or viscoelastic. So that is.
So therefore, how can I confirm that changing in shape of the RBC for different nozzle shapes or different nozzle construction? Then how can we compare it exactly?
Yeah, so what we did in our work is that we use image processing technology. That is, we use the software ImageG, and we have all these frames from the video. So what we do is that we get the shape parameters, like its circumference and other parameters, and we observe how it is changing with time, and is it reaching its initial value, which was present before it entered the slit.
That is very immediately. That is very immediately after passing the nozzle, or with time.
No,
how can it
it's
changes?
not immediately. It takes some certain time. So if you see over here, when it exits the nozzle, it is quite deformed, and from it relaxes. So there is a certain finite relaxation time that the cell will take.
Okay, so you are fixing the time period for all the RBC when comparing different nozzle shapes. So the time parameter will be fixed.
Yes, yes. So what we are looking at is first thing we are looking at just is it entrapped or not. And when we are looking at the relaxation time, we're looking at how long does the tip take to relax, because it's a very distinct feature on the exit shape.
Yes. And for all the cases, it is relaxing completely, or does that in different permanent shapes?
So in the case of these elongated shapes, they don't relax back to its original shape. But for the tip formation, they do relax back to its original shape. It's just that they take really long for the sickle cells.
Okay. And the same observation you also got from your simulation experiment.
So the simulation work, they had a slightly different parameters. They did not look at sickle cells per se. I mean, the model didn't cover those values. diffuse. So they don't see the tip formation. So therefore, they don't see the relaxation of the tip. But if you see the time frame in the last closer to the same time frame, they see similar shape. So they are able to mimic the relaxation also.
Thank you. Thank you.
So we have some more time for questions. So
Gaurav, can I ask a question?
please, yeah.
This is Basa here. Hey Priya, really nice talk. So if I look at you mentioned that the gap is 5 micrometer. Am I right?
The height of the channel.
The height of the channel is 5 micrometer.
Yeah.
But if you look at the dimension of the red blood cells, right?
Yes.
But in the movies, I just felt that the gap is much smaller than 5 micrometer, because if you look at the way the droplet was coming, if the major dimension is 8 micrometer, however, the gap is hardly visible. So I thought.
Yeah, so maybe I was not very clear. So when I say height was 5 microns, the height within the plane. So we are looking at the top view of the channel. So what we see over here is this gap we call the width of the channel, and this length we call the length of the channel. So the width is less than a micron, which we wanted to achieve using our fabrication process. That's why it's very narrow. So the width over here is 0.8 micron, and the length is 2 micron. So this dimension is 2 micron. But within the plane of the monitor or surface, your height is 5 microns.
But even then, it looks, even if you say that the height is 5 micrometer, if I put it, I mean, looks like if I take that length scale and put it on the droplet that on the RBC that you're looking at, to me, or is it that it's not in focus? That's why it appears a little bigger, the RBC.
So the RBC is 8 microns over here. Because the channel height is only 5 microns, it is not able to go on its side, and therefore it's always floating along its 2 micron thickness. Is that clear?
Yeah, maybe I'll chat with you offline. I'm sure there are other people who are interested to ask questions.
Yeah.
So.
Yeah, Priya, I have a question on the same lines as Baswaraj. My question is, like, suppose if I make the length of the channel slightly longer than the diameter of the RBC, like 10 micron or something, would you see, like, for example, for the case of sickle versus healthy cell, would you see a significantly different behavior then?
Yes. So what we did, if you see in this, we have these channels which are almost 10 microns in length. So we passed the red blood cell through some of this. We actually chose the 2 micron width so that we are not stressing the RBC much. But in majority of cases, although we have not quantified it quite well, most of the RBC is lysed, because they are experiencing that high stress for a very long time, because they have to pass through the 10 micron length. And therefore, the pressure on the bilayer tension was reaching the lysis tension, and majority of them were lysing. So then we didn't go ahead with that device anymore. And
how do you quantify the membrane? Like they would fracture or something beyond a certain tension. So how do you sort of, is there a good number for that?
There is a lysis tension. Although I don't have the number right now with me. Most of the simulation work, they do take into account if they are above or below this lysis tension. In our experiments, we just could visually see that the RBC has burst. So that way there was nothing more we could do with that cell. And once it burst, even the device cannot be used further, because now it becomes quite adhesive to other cells. So that was an issue. So as soon as we increased the length beyond 2 microns, the stresses on the cells were quite high, leading to their rupture.
Okay, thanks. Thanks, Priya. I believe we can move to the next talk now. Thank you, Priya, for a very nice talk.
Thank you. Thank you.
So we can move to the next talk now. This is by Dr. Tarak Kumar Patra. Tarak, are you there? Can you share your screen, please?
Yeah, are you able to see my screen?
Yeah, maybe you can put the presentation on full screen mode and then we can start. Yeah.
Oh, it starts. Okay. So I'm audible, right?
Yeah,
Am
Tarak.
I-
Yes.
Yeah, Tarak. Yeah,
Hey,
everything.
yeah, thanks for the introductions, and and I'd also like to thank Birkeshwar and Shomasri, Alok, Basha, Dilip, and Shushmita for putting up this nice conference and having me a part of it. I work at the interface of data science and material science. I try to bring data science methods like AI and machine learning and explore how those methods and algorithms can help improve our understanding of materials. The AI and machine learning is impacting all of our work, be it a science, engineering, or medicines, or social sciences. And soft matter is not an exception. If you recall yesterday's talk by Shanat, he was mentioning that machine learning are dumb, and then he went on explaining if you keep on adding more and more data, it can do amazing things and it can help you find out interesting structure. So I would argue along those lines and would like to argue that data science is or machine learning is not that dumb. It can do many interesting things. It can help you improve your accuracy and precision of measurements. It can help you identify some new structure and get things done quickly. So to demonstrate that, I will take 3 examples from my own work, and I'll briefly mention 2 examples. And the third example, which is the page transitions, I'll go in details and try to sort of go into a brief overview and how this machine learning can be used in polymeric research. I'm going to demonstrate that. So let me begin with a molecular materials design problem. Materials design is a very challenging task. We know that the huge search space and the physical and chemical space available when you are trying to identify an optimal material. And that's where I am trying to bring some concept from gaming AI. So you all will be familiar with many gaming softwares and programs like Tic-Tac-Toes is a Chinese game, or simple chess, or AlphaGo, which is the one which beat humans. So if I try to compare how those gaming algorithm work, or how all those those tabletop or board games can be correlate, or we can draw parallels in my material systems, I see a lot of grids, and in each of those board games, the disc or the kings and queens, they are sitting in one of those grids. So if I try to draw parallels in material systems, I have lattice and lattice sides, and my atoms and molecules can sit in lattice sides. And in game, you typically try to have a combinations of those disc or kings and queens and some moves which can give you a winning combinations, or which can give you some loss or losing combinations. Similarly, in material systems, we look for certain atoms arrangement and patterns and moves which can give some new structures and new understandings of material systems. So I find a lot of similarities, and I got excited about the possibilities of these kinds of algorithms which are being developed in a relatively different domain, and we can bring them and try to see how it can help us to understand soft matter and material science in general. So recently I tried to emulate this gaming strategy which is there in all the gaming softwares available, and we try to identify some new polymer structures which have some superior properties. So here is the gaming strategy. I'm not going details into how this game works, but the problem here is that unlike winning a chess, I wanted to identify a polymer which can reduces the interfacial tension between two immiscible polymer. So in this given example, I have two immiscible polymer. One is this gray lines, and the second one is this blue lines, blue carbon lines. They're immiscible. I'm looking for some third elements. Those are called compatibilizer, which can placed at the interface and reduces the surface tension. So these are the some steps of my gaming algorithms. And at the end, it identifies some polymer, which is of course having the moieties of those individual chemistries, and try to arrange those monomers in certain sequences that is able to reduce the surface tension. And what I observe is that these gaming rules lead me to situations where I come up with a sequence of a monomer that's leading to a zero interfacial energies. This is something contradictory to all the human designs we have been doing in our academic research or industrial research. Here is a algorithms or a strategy which can take a reasonable or low amount of resources and identify some new structure which helps you to make a incompatible systems completely compatible. So these are the scopes and opportunities where machine learning can bring in. The second example which I would like to take from one of my other work, where we try to develop interatomic force field. So interatomic force field is another area where all of us who work on molecular dynamic simulations, we struggled a lot. Let's say we wanted to study the diffusions of an ion in a solutions. Uh, we may end up choosing a force field where the diffusion coefficient is correct at certain range of temperature. Beyond that, it is predicting high diffusions or low diffusions. So there are existing force fields which are, they're not transferable across a wide range of thermodynamic conditions. And oftentimes they can predict, let's say, diffusions correctly, but they're not able to predict, let's say, liquid vapor phase equilibrium curve. So having a universal interatomic descriptions or force field is always a demanding. And if I look into the development of force field in last couple of years, there have been exponential growth of bringing this concept of AI and deep learning, and they have been showing a lot of successful force field development. So from one of my work, I just wanted to demonstrate what we have done it for water systems. We can have combinations of water molecules, have a lot of water structures, and calculate their interaction energy running very expensive DFT calculations, and all the energies and water structures, assuming that we have a representative of water structure of the entire landscape or entire configurational space. And if you train this DNA model, deep neural network model, with those structures, and if it is learned the configurational space and energy, it should be able to predict a reasonably accurate energy for any unknown configurations of water molecules. If that is the case, I can take a derivative of the energy and get forces and put that force in Newton's equations and solve it and generate a particle trajectories, and essentially I can solve a water simulation. And we did that recently, and we see that we are able to capture a lot of water properties, including very complex water anomalies, which takes place somewhere around 4 degrees centigrade. So those are the complex phenomena which some of these deep learning methods, which is not really a physics-based approach, but able to identify some of the things where oftentimes physics-based model also struggle. Moving on to the another aspect which I have been thinking in recent times, since I joined IIT Madras, I have been thinking that how AI and machine learning can be used to understand some of the physical processes. For example, compressions, if you're taking some soft matter, compressing them, or heating them and cooling them. So during all those physical processes, a lot of things happen, a lot of phase transitions, dynamical crossover takes place. So can AI and machine learning identify those transitions and give some insights of those phenomena? Particularly last couple of months, we have been focusing on cooling or thermal annealing process. And when you take any systems, be it a polymer or non-polymeric systems, if you cool it down, many things happen. You will have crystallizations, or you could end up semi-crystals. And if you manage to control your cooling rate or compressions rate, you will be able to escape the crystallizations, and you will be end up having a glasses, which is even complex phenomena. And during glass formations, you will have things like caging, crossover from areneous to non-areneous kinds of dynamics, and then ultimately it will fall out of equilibrium. So all those complex phenomena, phase transitions, dynamical crossover taking place. So can AI help understanding those processes, or identify some parameters, or help us to kind of measure them very precisely? So that's the kind of motivations we started this project with my MTech student Devjyoti, and I have a very talented intern from BITS Pilani. His name is Ashwin. He is about to complete his UG and looking for PhD opportunity. So we work together and we generate a lot of data and building this AI framework, which I'm going to demonstrate for next 10-15 minutes. So what we did is that we think that let us start with a very simple problem, a very simple system. Let's take a simple bit spring. Let me stop this movie. It's annoying. So let us start with a very simple system, very simple bit spring model systems where two particles are interacted by a Lennard-Jones potential, and any two bits connected by a Finney-Kramer-Gris type of potential. And we try to solve their Brownian dynamics by solving the Langevin equation of motions. And this is a very dilute solutions conditions, and we change the temperature of our simulations, and essentially it has two dominant structures. One will be coil-like structure over here, or we can have a globule-like structure. Now, these things you can simulate even by changing your solvent conditions. From good solvent, you will have this kind of structure. If you have a poor solvent, you will have this kind of structure. So we generate a lot of data, and certainly we try to have a one single crossover taking place during this thermal annealing process, and see whether AI can be able to predict such crossover, and how accurately it can identify those crossover point, or any physical insights it can provide. So we'd start building something called a autoencoder, which is a deep neural network. It is called deep because it has multiple layer of perceptions. And this is a very unsupervised machine learning or deep learning, where we don't say what are those things. We don't label the data. We just give the 3n dimensional coordinates of a polymer configurations. What we try to do is it map the polymer configurations to a latent space, a lower dimensional space. We call it also feature space. So this task is called encoding. This side of the network does encoding, and the other side of the network does decoding. It tries to reconstruct the original polymer configurations from this latent space variable. So we kind of throw thousands of polymer configurations and build this model to kind of uniquely map polymer configuration, 3n dimensional configurations, into lower dimensional representation. That's what we are trying to do. Why you are doing that, I'll come later, but let us understand whether it is learned, or whether it is able to map a 3n dimensional polymer to a lower dimensional space uniquely. So to test that, after building the model, we bring some lot of new configurations and give them in this input layer neurons, and then collected all the polymers which it is reconstructing at the output layer, and computed their radius of gyrations. And this is the reference or the configurations, and this is the predicted RG. And we have done it for many different chain lengths, starting from 30 Mars to 800 Mars. And we see that it is reasonably able to map and then reconstruct the polymer, and the error, or the mean absolute error, is within 0.07, less than 7%. And of course, we can go back and tweak the model parameter more, and even we can reduce the error. But the point I'm trying to make here is that here is a model which is kind of uniquely mapping my three-dimensional space to a lower dimensional latent space. And that unique representations, it is also able to reconstruct back. Now, what we can do with this unique mapping at a lower dimension? So that's where we are bringing the phase transition part. So let's say we have mapped thousands of polymer configurations in a lower dimension, And then we bring some state variable. We say that if a polymer chain, which is of a globule nature, these are at extremely low temperature, which we can assign two state variable, C equals to G and G equals to 1. This define the state of the polymer. C0 means its coil tendencies is negligible, and G1 means globule tendencies is very high. Similarly, that two variable can flip here because this is a very coilish structure. So the C should be close to 1 and G should be close to 0. So we have all this low dimensional data, and we take some of those data and label by these two state variable. And then we build something called a deep neural network. It is a supervised machine learning. Why supervised? Because we label the data. We assign certain properties to the data. Now the machine is trying to learn the structure as well as its property. So we throw another thousands of configurations and build this model. And once the model is built, we try to see whether it can able to predict the label or the properties of those configurations for some unknown configurations, properties of any unknown configurations. So we test that. So for example, we have done it for both training set, the data which it already seen, and unknown which it has not seen. For both the cases, we can see whatever the label values, we know the label value as a reference value, which is coil state 1, globule state 0. It is very precisely predicting coils and globule state. So the mean absolute error is below 1%, which is fantastic. So we have a machine learning model which can look into my polymer dynamics trajectories and tell, hey, here is a globule formation. Hey, here is a coil formation taking place. Now, how we can use these informations to, let's say, identify the crossover point? Can it predict the crossover temperature accurately? That's the next questions which we are going to ask. To do that, we put all the elements which I have discussed. One is deep autoencoder, the other is supervised DNN in a framework, and we acronym this framework as a DPoly. DPoly is a deep learning of polymer. So within this framework, what we are doing is we are doing molecular dynamic simulations to generate a particle trajectories. In this case, my particle is a polymer chain. Chain length can vary from very low value as low as 20 to high as thousands. And then here is a deep autoencoder, which is kind of mapping those 3n dimensional polymer structure to lower dimensional representations. And once I have these lower dimensional representations, which I am putting it here as a featured space, then I build a deep neural network based on the data of my featured space representations. And here is a predictive model ready for me to test new configurations and new trajectories. And for any given new configurations, I ask my model to predict the state variable, in this particular case C and G, and I plot that C and G as a function of the controlling parameter. In this particular case, temperature, but it could be anything, pressure and other parameters which lead to some sort of transformations in your model systems. So this is the overall framework of our DPoly, which we have established, and I'm going to show you how it works for identifying a coil to globule phase transitions. So coil to globule phase transition is very common. It is there in all synthetic polymer to biopolymer and any macromolecular systems. So you can see that we have generated trajectories of all different polymer chains, and our model predicted the C values, which is the state variable C and G, and we are plotting them as a function of temperature. And as you can see that there is smooth, we just fit a standard spline to identify this crossover point. And these are the crossover temperature. We call it a temperature corresponding to coil to globule transition temperature. And these predictions is quite accurate from very low molecular weight to very high molecular weight. So we collected all those crossover temperature and then try to establish some scaling relations. So in this particular case, I am just plotting those crossover temperature as some functions of polymer chain length, and we identify that these kinds of scaling relations. These data are following, and these are some fitting parameters. And then we go back to literature to see how theoretically these correlations looks like. And there are some works where people have used Wang-Landau sampling and advanced method to identify similar correlations. So here is a case where a machine learning model is able to very accurately predict some basics or some elementary polymer physics of a systems which is undergoing thermal annealing. So how I'm doing in terms of time? Okay, I have some more time. Okay. So with that, so here are some summary of what we have done for this DPOLY. I would like to give some of the key features of this DPOLY framework. It's a very general purpose AI tool for analyzing molecular dynamics trajectory. It does not require any order parameter. It could improve the accuracy and precision of phase predictions and dynamical crossover. And we think that it will be useful for identifying new phases. I'll come to that. What are the new phases? What are the new dynamics which we explore with these kinds of framework? But we went on and did some more analysis where we tried to do something called locally linear embedding of polymer configuration. So these are the techniques mostly used in computer science domain. And here is a work from AT&T lab where they're trying to map a phase image to a two-dimensional representations. In this particular case, the leap of a human leap, they have mapped into a 2D representations. So as a material scientist, what I can learn or what I can infer from this work or this analysis is that these data are very nonlinear. And if I look into this 2D space, I can classify two regimes. In one regimes, the leap postures are like a closed leap. And the rest of the regimes, most of the postures are sort of a open leap kind of positions. So if I try to bring some analogy with my polymer system, I'm also dealing with a two-phase systems. There are two kinds of possible structure. So we try to emulate these kinds of algorithms in my polymer system. So my intern, who is from BITS Pilani, Ashwin, he exactly did that. He just replaced these leap images by polymer configurations. And he came up with a very interesting data set. So here you can see that if you map a polymer configurations in a 2D space, it's a very nice dynamical pathways of transformation from a coil to globule state. And it also identifies additional metastable structures during these transformations. For example, this is the points which represent some kind of coil structure, and this is something represents some completely globule shape. And there are intermediate structures which he has used some agglomerative clustering mechanism to identify those structures. These are some sort of metastable phases. Here you will have some intermediate globule formation at the middle of the chain.
Tarak, yeah, we are into question and answer session time. I mean, you can please wrap.
So basically these kinds of framework I'm extending to other systems or other complex phenomena. For example, glass formations. If you cool a glass, any glassy materials, the mean square displacements of its atom, if you plot them as a function of temperature, usually there is a caging, and then there is normal diffusions, and there is a ballistic motion. And these kinds of crossover is very hard to identify. And you need a lot of human interventions to capture those kinds of phase transformation or dynamical crossover. So this is the areas where we are heading to use AI to identify and accurately measure these kinds of crossover. Or if I look into the glass formation behavior, this is a simulation data for all different kinds of glass forming behavior, glass forming systems. There are crossovers from Arrhenius dynamics to non-Arrhenius dynamics, and here is a crossover where things is falling out of equilibrium. So we are trying to use this AI and ML framework to identify and analyze these kinds of dynamical transformations in polymeric systems. So with that, I'll stop here, and I will acknowledge these agencies for their support in our research. So thank you for your attention.
Thank you, Tarak. So we can have some questions. I can already see some of them on the Q&A. Are they visible to you, or should I read them to you? I'll read them anyway for the audience. So Rumia is asking, can we get some information about the dynamic phase behavior, such as in a system, if there is a change in phase in some region, while no changes happen in other regions? So they're like, it's not like the entire domain it's not a homogeneous change. That's
Yes.
what I want to say.
Yes, it is completely.
Those cases, can we get some information out of these deep learning tools?
Yes, it is completely possible. I don't have data here, but yes, it is possible. But I just to demonstrate the framework, we just try to make only 2 phases or so. But in principle, you will have we have some other systems where I go. Yep. So you will see these are the curves which will show a lot of peaks, ups and downs. If we have those kinds of scenario, there are many local transformation taking place. So yes, and these can track those kinds of transformations. And in principle, we are trying to make this code very generic. There are multiple phases, and there are multiple controlling parameters, and we wanted to make this very versatile. And essentially, we are going to make it open sourced also. Yes.
Maybe something called radial base function network or something. Anyway, I mean, just a comment. I don't know.
Can you repeat?
Something called radial base functions, where you have, if you have different things happening in different regions, where your different outcomes are possible, then you model them. I'm not sure if that.
Yeah. I mean, some kind of locally embedding, which I was trying to mention here also. This local regions should reflect here actually.
Okay.
There are certain advanced clustering algorithm which will identify by some different colors.
I see.
Yeah.
So there is another question by Fani, which is, what is the difference between pair and bond potential in your slide? There are, I think, 2
Okay.
potential that you
So that's a pair potential is your simple weak Lennard-Jones interactions. But in addition to Lennard-Jones interactions, you need to have a bond interactions to maintain this polymer structure. This is pair potential is simple weak van der Waals interactions, and then you have to maintain that bond, and you need to have an additional constraint.
Yeah. Then does that answer your question? I think it does. So we can. Shriram is asking a couple of questions. I'll ask one or two. What if AI gives us unphysical parameters, or do we need to set a range of the for the parameters? That's what Shriram is asking. I mean, how do you come to know that AI is giving unphysical results?
Yeah. So that's a good question. So currently, what we have we're training the model by extreme configurations, which are at very high temperature and very low temperature, and we know that these are the phases possible at those regions, and then we're building the model. Now, if you throw something unphysical,
I guess it's between interpolation and extrapolation. I think that's what is that.
Yeah. I mean, so machine learning is very good for interpolations, but extrapolation is too scary. And we have certain schemes called deep neural network biased genetic algorithm. What you try to do is that we do something like adaptive machine learning, where we have some data, we know the regions of space, and we model that regions, and then we slowly extrapolate to the nearby regions and generate more and more data. We cannot do very wild extrapolations. That's anyway is going to fail. So I mean, those are I have done some work which I have not talked about it, but there are a certain scheme which you can help you to kind of judicially, systematically extrapolate from your known region of space to unknown space.
Yeah. Are there any?
Tara, this is Divya here. Can I ask one question, Gaurav? Is that okay?
Sure.
Yeah. So very nice talk, Tarak. As I realized that you haven't used torsions in your polymer chains, right? So have you tried because that will make the polymer a little more stiff.
Right.
So have you tested these models for, say, real systems like thermoresponsive polymers predicting their critical solution temperatures?
Yeah. So that's what we are doing. I have a project assistant who is generating the alkane chain and polystyrene chain and chain cooling particularly the glass transitions as well as the crystallizations. So we have not tested it, but yes, we will be adding those features in this tool. Yeah, but
Okay.
the areas where we are expanding, that more chemically detailed systems it should be able to analyze.
Okay. Thank you.
Okay, those who have questions, I mean, if you still have questions, you can ask, maybe write to Tarak. Is it okay, Tarak?
Yeah, absolutely.
All right. Yeah. Thank you for a nice talk, Tarak.
Thank you, Gaurav.
Thanks a lot. So we will move to the last talk of this session, which is by Vishal. By Vishal. Vishal, are you there?
Yes. So let me share my screen.
Right. Okay. Maybe you can. Yeah.
So
it's still not visible. The screen has not appeared.
Yeah, I can share the screen from my computer, right? It says Dropbox and Google Drive.
I think you should be able to share your screen.
Yeah, I think I see that. Yeah. Okay, can you see my screen now?
See your screen, yeah. Share only the window. No. Yeah, you have to start your presentation. I think your presentation is not come.
No, he shared only the window. Viewing folder window.
Maybe I think you have shared only the viewing folder and not the entire screen. Full screen.
Okay, so
I think it throws a couple of options, and you pick the one where you share the entire screen and not just one window.
Okay, so I should say share screen and screen, right?
Yeah, share screen and the entire screen. Yeah, screen.
Yeah, screen. Okay, can you see now?
Yeah.
Is the presentation visible?
Yeah, you can put it on full screen mode and then
yeah.
Vishal, are you there? Vishal? Hello?
Looks like he got disconnected. Not sure.
Looks like that. But the thing you can see his screen. I don't know how this. It is frozen, I think. Huh? Yeah, I think we've lost him. Maybe I'll check with Alok and he can try calling him. I'm not sure if he's.
Yeah, we are checking. So let's wait for a couple of minutes.
Sure.
Gaurav, I'm calling him. Give me a minute.
Yeah, okay.
Gaurav, he said he's trying to connect back.
Okay, so we'll wait.
Yeah.
And
Hello, Vishal, we
my
can see
video.
the screen now.
Yeah. Okay. Excellent. Thank you, Basa. Yeah. Sorry for the delay. It's the internet just snapped at my end. So okay, let's get started without any delay. So just a confirmation, you can hear me, right, guys?
Yeah,
Yes.
we can hear you.
Excellent. Thank you, Gaurav. So the talk today is going to be whatever I had done during my PhD and a continuation with the help of my students for the last 3 years after my appointment here. So the title of the talk is Micro Nanofluidics and Nanofluidics. How can we understand how they meet? Here's the outline of my talk. So basically, I've split the talk into two sections. One is the physics of what happens inside nanoscale regimes and inside the nanometer domain, especially in terms of the fluid flows and also in terms of the liquid is predominantly an electrolyte solution like KCl. And along with that, what happens when we interface such a nanometer scale cylindrical pore or a channel with a microfluidic system, which we can call it as a reservoir or a slightly, you can say a micro reservoir. And then typically in an experiment, this micro reservoir is connected to a huge reservoir like a bulk reservoir. So you have a bulk, micro, nano kind of a system. But in this talk, I'll just focus on micro nano system where the bulk physics to micro physics is fairly well understood. It's not much change. So that's the scope and the basics of micro nanofluidic transport with respect to an electrolyte solution with which involves a solution like ACl along with water will be studied both using experiments and numerical calculations. And then the physics of this is so interesting, which is a classical 100-year-old problem where you see for electrochemical systems like a battery, especially, or even electrode systems, which have these thin pores inside them, which are at least a micro or a sub-micro or close to nano regime. The classical ion concentration polarization and over limiting currents will be observed. So these over limiting currents, what's the physics behind it, will be explained through a set of experiments that was re-observed in the micro nanoscale as well. And I'll touch upon how they are different from basics of nanofluidic transport and why it is so different that you need to have a micro nanofluidic system to actually understand these polarization physics. You need to have an interface, which is not so if you directly jump from a bulk reservoir to a nanoscale pore, you'll not see such interfacial effects. So the nanoscale phenomena is completely different from a micro nanoscale in terms of polarization and the complexities in the fluid dynamics at the interfaces. So that's the whole outline of my talk. And the second part is the applications, which is very similar to micro nanofluidic and nanofluidic, which is going on for the last decade of research, is in terms of making some sort of fluidic circuits like transistors and diodes for liquid diodes, and also in terms of desalination applications using different types of membranes. Even latest 2D membranes have been used for desalination using these nano and micro nano approaches. So this is something which I came up with a schematic in my lab. What we are trying to do, along with the fundamental physics of what's already been understood, is the center image that you see is, let's say, is a typical nano cylindrical pore of, let's say, 5 to 6 nanometers in length. And you make a hole. It's not necessary to drill a hole completely over the entire length of the cylinder. You can drill a hole using an FEM or using an TEM or an FIB at, let's say, the tip. And you make a hole of, say, from 1 nanometer, which is usually nowadays called a single digit nanopores, and all the way till 100 nanometers, you can also make it till 1 mm. So it's not a difficult job to actually drill a 1 mm pore to a 1 nanometer pore with all the resources being available. And what we would like to see is, if you really want to understand the structure and the dynamics of a fluid confined at these interfaces. So what you see here, the ring is the pore and the outer surface. Let the water leak, no problem. You'll see we wanted to actually, have a pipette experiment to actually put water on the spore and let it leak on the side, and try to get using my collaborator here at IITM, Shiva Ramakrishna at physics department, use an XRD to actually see the imaging of how a water is actually in a confined space, and then try to see and put theory and modeling using CFD or MD or advanced ab initio or DFT calculations to actually understand the MD corrections and CFD corrections to actually come up with something like a nano CFD kind of methods. So this is currently my line of research that I'm trying to do right now. Along with that, we have also understood some dynamics at the nanoscale using molecular dynamics simulations. As you can see in the bottom figure, is what happens at these interfaces of micro nano surfaces. I'll come to touch to that, and you'll see nice complex instabilities to fluid vortices to charge redistribution to polarization effects. And not only that, one of the other things that we are also capturing using the dynamics is the noise in these nanoscale systems, which can be actually understood, especially for the fluidic circuits, if you are interested to understand the fluid dynamics, and so that there is no external noise or external environment disturbances or the internal noises to actually have a good performance when you try to use it for some applications like sensing. So we try to understand, it's a very classical, very well observed phenomena for the last 10 years by experimentalists. And we try to actually do a large MD molecular dynamics of around 350,000 atoms to actually predict that low frequency and high frequency noise that's been observed in nanoscale systems. And the theories are very well matching with the experimental systems. So that's the fundamental aspect. And how do you make these pores? As I said, you can actually have, it's just a membrane physics. So you can have a membrane as thick as a solid state membrane like a silicon or a PDMS or a PMMA, and then make a pore using FIBECR or an electrochemical radiation or an TEM. And then you can just change the dimensions of these membranes to all the way 3D to 2D, and play with the material properties from a semiconductor to a completely polymer based material. And Shiva had recommended when I talked to him that one of the ways you can do it along with the existing techniques is to actually do some sort of femtosecond laser machining, which we thought is extremely powerful to actually control the making the pore size. So this, what you see on the top, is a 2D membrane that's been done at IITM, and the pore was drilled by a TEM. And what you see here on a solid state is being done by a femtosecond in a matter of few seconds with less user training required. And one of the things that I was doing during my PhD as an application of this is to try to use these micro nano phenomena physics to actually make some sort of diodes, which actually have a very high rectification of around 4,000 to 5,000. So you can actually, we were thinking of seeing if we can actually use it for future displays, like instead of light emitting, can we use it as a fluidic displays, for monitors and screens, where you can actually see, in future, if possible, we can actually see the fluid moving instead of only the electrons or the light moving when you see a display of any cartoon to a real image or to a captured image through a camera. Then one of the things that also we are working is to actually use it for power generation, which I'll not touch upon, but you can actually generate power using salinity gradients using these interfacial effects. So with that, I'll just focus on what I'm trying to do right now in IITM. So one of my students, Fanendra, is an experimentalist and predominantly working on micro nanofluidic diodes, and help is being gotten by me from Professor Ashish at Mechanical, and he's helping us in making these microfluidic channels. And this is a typical design that he's trying to do, similar to an experiment which we did in my grad school, and he's trying to replicate a similar geometry of, as you can see here, the vias are also microfluidic, and you have a micro channel that leads to the via to a reservoir that's more like a bulk channel. And then the thin membrane is actually a commercially bought polycarbonate nanocapillary membrane, which has many pores, as you can see here, an NCM being imaged with an SEM image, which has many pores of close around, let's say, 100,000 to 500,000 to the diameter opening on the other sides through these wires. And the way we try to make the reservoirs is by using a classical test tube, which is cut and then finished using mechanical finishing. And Ashish helped us in making these micro channels. And then we used different glues and techniques to actually integrate the micro channel with the NCM. And what you see at the bottom, in the middle, in the as you can see in the assembled device front view and top view, the triangle shape is the NCM, which is being merged with the two micro channels, and the two reservoirs are connected via the two vias, and the two reservoirs are connected via the micro channels. And then the whole point of the study is to see these novel phenomena like ion concentration polarization and electrokinetic instabilities and vortex formations at these interfaces, which are typically not observed in nanofluidic systems, standalone nanofluidic systems. As I said, you need a scale change only of order of 1,000, that is micro to nano. It is not observed if you have anything more than micro. These phenomena will be absent. So what is the fundamental nonlinear transport? I'll touch upon in this slide, which is a very nice experiment when I was in grad school that Professor Han at MIT had done. Was actually, you have a typical membrane, which is shown by this rectangular 2D image, and you have a anodes and cathodes, that is the reservoirs. And when you allow the ions to flow from the left to right or from the right to left, you will see the classical permeation effects, which actually gets hindered due to the ion selectivity of the membrane. And as a result, some ions will be moving, some ions will be blocked. That will reach to depletion and enrichment effects. So what you see here is one side you will have a depletion effect because of the purely because of the electrostatic interactions, and the other side you will have an enrichment effect purely because of the electrostatic interactions. And these can be flipped. You can actually, it's not necessary that you should always have it on the right and left. These can be flipped if your the selectivity of the ion is flipped from a counter ion to a co-ion selective membrane. By that I mean counter ion is one where if it is a positively charged membrane, it will allow negative ions, and co-ion is one if it is allows the same type, which is very rare. And if you have let's say a positive membrane, then negative ions will lead to one type of depletion and enrichment viewing. It can be on the left or right, and it will switch if you have a negatively charged membrane, because of the electrostatic interactions that are switched. And here is a nice experiment where you can see these depletion regimes over a fluorescence imaging, and you can see these fluorescent imaging trying to tell you that the concentration of the dye is completely weakened, whereas the concentration of the dye is completely enriched at the other end. And the difference between our setup and their setup is that these are all fabricated using lithography techniques. Since Han is a ECE guy, so he tried to do it with he tried to do it with the semiconductor approaches, and we tried to do it with the chemist approach when we collaborated with experimentalists in my grad school. And similar experiment, as I said, Dr. Aaron, a collaborator at when I was in grad school, did observe something similar, where he tried to build a different device using micro nano scale etching, and then simple etching, as you saw in the previous slide. And we see the depletion regime very pronounced using the dye that he used. And the good part is I was a computational guy, and we tried to capture the entire micro nano transition physics over the entire domain for different voltages. And you can see the voltage needed is almost 100 volt for a system of almost around 5 microns for the nano channel with 30 nanometers in height. So you can imagine how much electric field focusing has been happening at these interfaces with such high voltages and small devices. So the next part is again something that Han had observed is not only these depletion enrichment regimes, you will also see that when you apply the voltage even higher, you'll see nice vortices being formed at these interfaces, as you can see in image C, where the fluid is trying to rotate because of the field focusing at these interfaces. The reason that happens is because when you actually have a depleted regime, you know that the concentration is weakened and the resistance becomes very high. And if you try to actually increase the electric field, the resistance just snaps out, and it becomes so high that it will disturb the fluid next to it. Because there is no iron, and it will lead to, it can also lead to instabilities and chaotic motions, which we'll come to, but it will start with something called an electroosmotic flow of second kind. The electroosmotic flow means it is the flow of the fluid under the presence of an electric field, and it's usually observed as a linear field in linear flow with a classical, similar to a Poiseuille approximations, except near the interfaces like slip effects or interfaces, except near the walls of the nanochannels. But you won't see, very nonlinear flows for an electroosmotic flows inside a nanochannel, standalone nanochannel. Whereas in terms of micro nanochannels, you actually see very high nonlinear electrokinetic transports leading to second kind, where you can see nice vortices being formed. And the thing that my other student, Manigandan, slogged a lot, I have to say. He developed a micro nano channel system, which is close to around 1.1 million atoms, and ran it for around 6,000 CPU hours, sorry, 25,000 CPU hours, almost a year. And he captured this nice physics where you can see, before I come to what you see, the light part is also water, the dark part is also water, the red is Cl, and the blue is K+. And what you see here is the light part tells you that the stable motion of water, that's the linear motion, and the dark part of water tells you how the water is really moving at when the electric field is so high. It's almost like, even here it is 100-volt electric field for the system, and it's it's for the first time we did a very large MD simulation similar to a polymer physics for micro nanochannel devices using NAMD. And so I'll play the video again. So what you see here is the water is actually, you can see that it gets so compressed and then moves forward, moves back, tries to rotate. And what you see, I'll play it again now. See the yellow, red and blue dots. You can see that the ions also rotate when the water is so compressed and starts to move in such a fashion. You see that the ions are actually rotating in a nice homogeneous fashion near these interfaces, unlike a random motion. And that's what is being captured in the experiments that we try to capture in the fluid flow. And after post-processing, you can see how the fluid motion actually happens in the electroosmotic flow of second kind. He tried to take the trajectories and plot at one instant how the fluid motion happens. And you can see it's a highly nonlinear, no longer a parabolic flow kind of profile for an electroosmotic flow. It's a second kind where you can see the flow is moving to the right, left, and the profiles are completely changed. That results in the motion, circular motion of the atoms, the electrolytes. So whereas this happens predominantly in the depletion region because the concentration is depleted, leading to very high resistance. In the enrichment physics, it doesn't matter so much because once the ions are so highly enriched, the resistance is so small. So in that, even if you have a micro channel, that geometry will just tell you that the physics is very similar to the bulk physics. It's just that the ions are getting crowded with no change in resistance and no motion in no changes in the fluid motion. It's still the electroosmotic flow of first kind. But that's why we try to play with the geometry, and what we got is a diode when we actually try to understand what happens if you actually change the reservoirs and play with the enrichment depletion physics and change the polarity in the forward and reverse directions. So I'll just quickly touch upon what is concentration polarization. So you understood that ions are getting polarized because of the high electric field and field focusing effects at these interfaces that leads to breakdown of classical electroosmotic flow of first kind, and that's the parabolic flow, and leads to highly nonlinear. Now what happens to the ions is that the ions also lead to as I said, the neutrality of the ions also breaks down at these interfaces because of the not because of only the electric field focusing, but there is also a membrane which is selective to one particular ion. and such high focused electric field with a selective ion will certainly disrupt the electric field focus, will certainly disrupt the charge neutrality because of the strong force being applied on the ion that either pushes some ions and breaks the breaks the interactions that is coming from the voltage at the other end. So you have a two-side electric field. One is the electric field in the forward direction because of the voltage, and the electric field in the reverse direction because of the focusing. So there is all possibility that the electric field neutrality of the both positive and negative ion to stay close, even if it is same monovalent ion, and you know that it's a perm selective membrane. It will still break down. The classical diffusion limited theory will break down, and you will see over limiting currents. That is, the highest current is also observed in these systems because it's an over limiting that keeps on increasing if you increase the voltage. And you see in the high MD simulations or large MD simulation, we applied around 170 volts, and you can see what happens to the dynamics of these ions at these interfaces. There is no water effect now. You can see the just the ion effect, and the ions are just moving pretty fast, and you see they are getting depleted at one of the ends as you slowly see the motion, frame rate of the movie. In the other end, it is getting enriched. And the good part is once it is depleted and the field is getting focused, the ions start to move and gets pushed pretty fast. And you will see a situation where they can no longer go to the end of the reservoir in a physical system, and they will try to move to the front and it will redistribute. As you saw that, as you can see, the ions are getting enriched inside the nano channel because of the fast motion at the interfaces, and there is no space for the ion to move towards the bulk reservoir because the voltage is also allowing it to move towards the front. So there is an enrichment of ions inside the nano channel, and that's the physics that we tried to capture during the grad school. Yes.
The last 2 minutes, please. We'll have to wrap it up in 2 minutes.
Sure, no problem. So I'm almost at the end of it. So that's the reason why we have an over limiting current, and that was the contribution that we tried to make. That the physics, it's a 100-year controversial problem of what is the over limiting physics in electrochemical systems and battery. And we try to explain not through the, it's not because of the water vortices or the instabilities, it's because of the charge redistribution effects. So the other observations are also being made in experiments. As I said, these vortices can become, as expected, unstable if you try to increase the voltages, and that's all being captured using our simulations. Also the vortices can be double, triple, multiplied without becoming unstable, even for an EOF of second kind. Even the unstable vortices can be multiplied, and that is the next work what my student is seeing from MD, how to capture that unstable vortices. And through the post-processing, he has also seen, as you can see here, these are all MD simulations that has been post-processed trajectories, and he got the nice contour plots of the fluid vortices at these interfaces. And the theories are showing that EOF of second kind scales quadratically with the electric field, agreeing well with the experiments and with the asymptotic methods. So with that, I think also the charge redistribution, he has post-processed that ion concentration and plotted that you do see enrichment just as the continuum simulations. And as you can see, this is the over limiting current. I'll end with this. So you'll see that you'll have a linear, then you'll have a limiting behavior, as we all know is the current saturated theory. And then you'll have an increased current, which will keep on increasing forever. And we captured that with continuum and with MD, with high large MD simulations. And some of the math for that is by solving the Maxwell's equations, that's the Poisson-Nernst-Planck in a reduced, in a complete sense with hydrodynamics. So it's, you can say it's the EHD equations that's been solved using finite volume, and the continuum methods codes are all uploaded. And we used OpenFOAM to write the codes for this. And then applications, as I said, the class, you can use a nanofluidic physics, just even without the interface effects. You can make a application like diodes along with desalination, which is obvious because you can control the pore, but you can take semiconductor approaches and play with the PN junction kind of method just with nanofluidic pores, without just by having the reservoirs even as big as bulk scale, and get diode applications by having a PN junction or a conical geometry effect, or geometry is a conical diode, which leads to the asymmetry or symmetry breaking, and PN junction will also break the symmetry. Or you can also build it with a gate kind of effect with the classical transistor. And these are all the effects applications. But the thing is, these designs led to a rectification that is on-off ratio of just 150, whereas a real semiconductor is around 1 million. And we tried to use this micro nanofluidic and achieve around 4,000. We saw some numbers around 10,000, but we didn't report. But it's possible to actually shoot it up for some nice applications like displays. And there's another application where you can use that electric field focusing. Once you get a depleted and you concentrate the salt, you just push it out using a pressure pump, and you can desalinate water. And with that, I'll end. So the main focus of the talk I wanted to bring out to you in this talk is micro nanofluidic devices are a new class of devices, different from nanofluidic standalone devices, where you observe very complex phenomena like nonlinear transport, electrosmotic flow of second kind, instabilities, redistributions, and they can be used for applications like circuits and desalination. And it's been done with experiments and MD and continuous simulations. Thank you. Thanks for your attention. I'll be happy to take any questions now.
Yeah, thank you, Vishal. I'm sure there would be some questions that people can write to Vishal. Is it okay? Because there's no time left.
Yeah.
Is that okay? Okay. So I think there is a poster session that has to be started. I think we're supposed to start at 11:30. So, Sushmita, do we have to make any announcement?
Announcement is that following this, we have a poster session.
Okay. Yeah.
Yeah. So the judges are already here. They were introduced last time, yesterday itself. So yeah.
Thank you, Vishal. Thank you.
Sure. No issues. Pleasure.
Excuse me, sir. I have one question. Is it okay to ask you now?
Romaya, can you just write in the QA section, because we are really running out of time. So
Okay, sure, sir.
yeah, so so we now call upon Jason and Udipta for taking over, and then carrying the poster session forward. So.
Thanks, Pasa. So good morning, everyone, and welcome to the second poster session of this meeting. So we're going to get started off with Manikandan from IIT Madras.
Greetings to all. I am Manikandan, doing a PhD at IIT. Greetings to all. I am Manikandan, doing a PhD at IIT Madras. Today I am going to present my poster titled Rapid Moisture Responsive Silk-Fibroin Actuators. Nastic movements observed in nature, such as rapid closure of Venus flytrap, inspires the designing of soft actuators made up of polymeric materials. These actuators found their application in soft robotics, biomedical devices, and sustainable energy generators. Soft actuators respond to different stimulants such as electric field, magnetic field, light, temperature were reported in recent years. Organic vapor and moisture-driven biopolymer-based actuators gaining interest due to their unique capability of the biomimetic movements and interfacing with biological environments. My work focused on the fabrication of moisture-responsive actuator from silk fibroin and understands the actuation characteristics along with the actuation mechanism. Silk fibroin obtained from Bombix-Mori silkworms is a unique material comprises hydrophilic and hydrophobic amino acids with hierarchical structures. I fabricated a freestanding silk fibroin film using solution casting technique as shown in my poster. The fabricated film demonstrates the moisture-responsive actuation behavior upon exposure to a moist surface in a reversible manner. Interestingly, water vapor evaporates from the warm surface can actuate the fabricated silk fibroin films. The observed macroscale response of these actuators is characterized by measuring their response time, actuation time, curvature, and bending angle. After optimization, we achieved the actuator with rapid response time of 0.1 second and actuation time of 0.3 second for 5 micron thick. The actuator exhibits excellent actuation retention behavior upon continuous exposure to water vapor for 600 seconds. From our observations, it is clear that the mechanism which drives the actuator is based on the interaction between the hydrophilic domains in the film and water molecules. The fibrin chains in the film rearrange and expand by changing their conformations to accommodate the water molecules. In contrast, hydrophobic beta sheet domains do not expand, thereby giving rise to inclined stresses in the film. The stress gradient across the film thickness drives the film to actuate. When both the film surfaces are exposed to water vapor simultaneously, the film remains in its standstill position. This exemplifies the importance of the water vapor gradient across the thickness. To estimate the technological potential, we characterize the actuator's performance for 1,000 actuation cycles continuously. Further, we demonstrated some proof of concept applications of the fabricated silk fibrin films. Here, the video shows the movement of a traveling robot using the fluctuations in the water vapor concentration in its vicinity. Thank you.
So thanks, Manikandan, for that nice video recording, and we can now take questions for the speaker.
Yes.
So we're now open to questions. Anyone from the attendees or participants can ask.
I have a question. Manikandan, how are you varying the humidity?
Hello. Yeah. Can you repeat the question?
How are you varying the humidity?
So actually, I'm not varying the humidity. So all the experiments we conducted at the humidity of 40%. The ambient humidity is 40%, and we kept the moist surface and we measured the humidity. So upon exposing this membrane near surface, the humidity will up to 80%. So we can change the humidity by moving that moist surface up and down.
So you're wetting a surface and then you're putting it close to this fibrin.
Yes. Yeah. Yeah. So we can change the height so that we can vary the humidity near the membrane surface.
I see. Okay.
Yeah.
Okay. Thanks.
Jason, can I ask a question?
Yes.
Yeah, sure.
Hey, Mani, nice talk. So this, how do you measure the actuation speed, and what is the
response time and
yeah.
So actually I'm using the high-speed cameras, USB cameras. I'm recording these videos, and I'm using a tracker, an open source software to derive all these data. So I'm recording around 150 FPS. Videos having the very high FPS, so I can extract the data.
So one of the attendees has a hand raised, Avni Chauhan. If you can go ahead and ask a question. Yeah, please unmute yourself and ask a question.
Yeah.
You could also type the questions if you're not able to unmute yourself.
I have one question regarding this.
Yeah, please go ahead. No.
Yeah.
So basically, you are capturing the motion of the, the actuation speed of the flame by using some camera.
Yeah.
You're placing the flame on your hand palm. So most cases, your palm won't be completely flat during the experiment. So how can you assure that flatness of the flame when you are placing on your hand?
So in the hand, I'm just putting a demonstration so that the water vapor evaporating from our palm surface can also actuate the membrane. So I'm not analyzing that video. So I used a standard configuration in the schematic you can see. So I'm extracting this data from the standard setup. I'm not using on the hand.
Okay, so basically during an experiment, you are placing the film on some solid.
So here, in the first schematic, you can see that. Able to see that, like the first schematic, reversible actuation cycle. Below that, I put a sequence of images. So the initial, 0 seconds, the membrane is flat.
Okay.
Yeah, then after that, it starts to actuate, right?
So you are placing the membrane on some solid substrate?
No, it is just a holder.
Okay, okay. You're putting
this is a holder, and it is free. It's a kind of cantilever configuration. One edge is clamped, another edge is free to move.
Okay. So water vapor is coming only from one surface, through the one surface?
Yeah, from bottom side or either top or bottom. So here I use the bottom configuration.
Okay. So this is water vapor.
Yeah.
At the same time, during experiment, there will be humidity which have some water vapor also in air.
Yes.
How could you control this humidity during the experiment?
So the room humidity means we are using the air conditioned room, so it's not changing much. So it is constant over time. Around 40% we usually keep the humidity, and we'll conduct the experiments.
So you're sure that during your experiments,
yeah,
you are maintaining the same humidity?
Yeah, we are ensuring that.
And is there any effect of temperature on that actuation?
We are doing all the experiments in a constant temperature, 30 degrees Celsius in the room temperature. So it will affect, but we have to conduct in the future.
Okay, so it's also temperature responsive as well as water responsive.
No, we can't say it is temperature responsive, because with temperature alone, we have not seen any response.
I mean, if we change the temperature during an experiment, will it show any different behavior, or it is remaining same?
See, if you are increasing the temperature of the environment, basically you will remove some amount of water molecules from the membrane. So it will affect the actuation behavior, because this membrane also have the hydrophilic domains. Hence, the different temperatures and different humidity, the moisture content in the membrane will change. So it will affect.
Okay.
Yeah.
So that directly temperature will also have an effect.
Yeah, it will affect the moisture content. It will not affect the actuation property directly.
And how did you measure that?
I'm sorry to interrupt, but we are running out of time for this slot. So thanks a lot for your questions. But if you have further questions, please put it in the chat. I'm sure Manikandan will be happy to.
Thank you.
Yeah, sorry to interrupt again. So moving on, the next talk is by Yogesh Arya from RRI on behavior of lamponite nanoplatelets in different binary solids.
Good afternoon, everyone. Today I will discuss behavior of laponite nanoplatelet suspension with tunable interaction. We are working on two suspension. One is laponite alcohol suspension, another one is laponite resin solution. So in case of alcohol, we are using ethanol. Addition of ethanol to water serve two purposes. One is solvent hydrophobicity can be tuned. Another one is electrostatic interaction can be tuned. So when laponite is dispersed in water molecule, then it is well dispersed inside the water molecules. But when laponite is dispersed in binary solvent, then we can observe that it is not well dispersed in binary solvent, because it is not getting much space, because hydrogen bond of alcohol and hydrogen bond of alcohol water molecules, a redistribution is taking place, and they are not giving laponite to well dispersed. So they are forming house of cards structure. Then we to study this both suspension, we try to do rheology and cryosum measurement. For this, we first did time test for 3 weight % of laponite with different alcohol concentration, and we observed that up to 20 weight % of alcohol, we are getting crossover. Then after that, we are not getting any crossover, because after 20 weight % gel formation is taking place, and G prime value is higher for 30 weight % and 40 weight %. So we are not observing any crossover for that. We performed time test for 2.2 weight % of laponite with different resin concentration, and we observed that As we increasing the concentration of resin, we are getting different crossover at different time interval, and we plotted crossover time versus resin concentration, and we are getting non-monotonic behavior for the 2.2 weight percent of laponite. Then we perform amplitude sweep test with 1 hour aging for laponate water alcohol suspension, and we observe that G prime and G double prime plateau value is increasing with increase in concentration up to 40% of alcohol, and then after that it start decreasing, because after 40% of alcohol we are observing that some phase separation is taking place in case of alcohol suspension. We plotted G prime value for G prime L value with concentration of alcohol, and we can see that it is increasing up to 40%, and then it start decreasing due to phase separation. Then we perform amplitude sweep test for the laponate water resin suspension with 2 hour aging. Then we observe that plateau value of G prime and G double prime is increasing with increase in concentration of resin. And then we perform some cryo-SEM results to study the surface morphology of the laponate alcohol suspension. With fixed concentration of laponate, we are changing the concentration of alcohol, and we age the sample for 1 hour for all the measurements. And we observe that networks are getting closer to each other when we increasing the concentration of alcohol. And for 28%, we are observing that network collapse is taking place. So we conclude that addition of alcohol to the water affect the behavior of laponate suspension, and we can also observe that much faster onset of kinetic arrest due to presence of alcohol, and for higher alcohol concentration, we can see network collapse for 20, 30 and 40% alcohol. And in further study, we want to try for higher alcohol content behavior in detail. And for resin, laponate water resin suspension, we try to find out a correlation between the conductivity and ion exchange resin, because in our experiment we find out that as we increasing the concentration of resin, conductivity of the sample is suspension is decreasing. So I especially thank Professor Ranjani ma'am for giving me this project, Chandeshwar Mishra for giving help in rheometer studies, Yatendran for helping in cryo-SEM imaging, and lab mates. Thank you for your attention.
Thanks, Yogesh, for the presentation. I hope he's with us. So we have about 4 minutes for questions.
Can I ask one question to Dilip here?
Yes, sir.
Go ahead.
Okay. Arya, it's very good talk. And what is the motivation for putting alcohol in water here?
Actually, alcohol is changing hydrophobicity of the suspension, sir. If we increase in the concentration of alcohol with decreasing the water content.
Why the alcohol makes it hydrophobic? That's what the question is.
Actually, we are keeping constant volume by volume fraction, sir. So laponite is well dispersed in water. But if we are decreasing the concentration of water and increasing the concentration of alcohol, then laponite is not getting much space to well disperse. So for higher concentration, we are trying to study higher also. So for 90%, it is sedimentation taking place. So complete sedimentation taking place. So we are trying to find out that what kind of structure it is forming when it complete sedimentation is taking place.
Okay, thank you.
Yeah.
Hi, Sunita here. Can I ask a question?
Yes, ma'am.
So you talked about the crossover concentration can you go to the graph below? So I could not understand what does it mean, like actually what is happening, why there is this non-monotonous behavior on the concentration. And I think the figure below it.
Okay.
Yeah, this one, yes. Crossover time, yeah.
Actually, we are just pointing the crossover time versus concentration, resin concentration. We observe that as increasing the concentration of resin, there is a 1 point like 0.2 weight percent or 0.1 weight percent. Here, some dramatic change is taking place. In case of alcohol, we also observe that at 40 weight percent of alcohol, below it is forming a strong gel, and after that it starts sedimenting. So there is a correlation between something below it's something happening different, and after that it's something happening different. So we
you have you looked at the structure in those like?
Yeah, means cryosome study is going on, ma'am. Like we try to find out more on this, ma'am.
Okay, thank you.
And for higher concentration of laponite and higher concentration of resin, we also try to find out, because aging is becoming faster in both the cases, alcohol also and resin also. So
Yeah, but that it is already high concentration, right? 2 weight% is really high. It might immediately form gel or glass, whatever.
No, ma'am. We are using XLG, and aging is like faster as compared to like normal laponite suspension, but not simultaneously ages to glass, ma'am. Fast, like sorry, means it's not much faster when normal laponite is dispersed in water, but when we are adding resin, it's taking less time, but not much faster.
At 2 weight%, you say?
Yes, ma'am. We are also doing at 2.8%.
Okay.
For alcohol, we are doing 3 weight%. So it's like aging faster, but not much.
Okay, thanks, you.
Yes.
I have a question. Can I ask you?
Yes, yes.
So, at what concentrations do you see this phase separation? The work you cited is our work. So, we found out it's like below 50%, we have a stable dispersion.
Yeah, 40% we actually. 40%.
How do you measure this beyond 50%?
We actually for 3 weight%, we observe that phase separation is taking place, and we observe that I measure up hour and hour measurement, like 1 hour, 2 hour, 3 hour, 4 hour. I observe that 68% is not sedimenting up to 4 hour. Then it starts sedimenting for 78%. So
concentration dependent.
Yeah, concentration dependent.
Solid concentration.
Solid is up to 40%, sir. Solid is up to 40% alcohol. After 50, it's not complete gel formation. It's opaque for 40 and 50. Not clear suspension.
Do you see any tectoid formation beyond 50%?
Aggregation, yes, sir. Aggregation we observe for like timing is changing, sir. For aggregation, timing is changing. Aggregation start forming after 4 hours for 60, and 70 it's taking less time to form aggregates, and up 90 it's forming like simultaneously. When we are removing the suspension from the steering, then it starts immediately start forming aggregates. So we are trying to find out for higher concentration, like any techniques to study that.
Fine,
and also cryosome is also studied.
Thanks, Yogesh, for your nice presentation, and it was very nice interaction with the audience. So it's time now that we move on to the next presentation, which is by Pranjal Agarwal from IISc. And she's talking about droplet dynamics in transitional boiling regime.
Hello everyone, I'm Pranjal Agarwal and I'm working with Dr. Sushmita Dash. I'm a PhD student in the IC department, ISC Bangalore, and I'll be showing my work in the droplet dynamics in the transitional boiling regime. The main motivation behind this work is the spray cooling of liquids on a hot surface. We create a single droplet impact to mimic the process. The droplet dynamics depends on the wall superheat, surface roughness, and the surface and liquid properties. This is the general boiling curve. To study it in detail, we performed experiments on a heater plate with concave aluminum substrates of different roughnesses, as well as with the liquid as water. When the superheat is low, we see that the droplet boils vigorously from the surface. With high superheat, droplet gently bounces on the surface. So what happens when the droplet is in the transitional boiling regime? In the transitional boiling regime, we see that the droplet bounces to much higher heights compared to the lightning fast bouncing cases. This happens because of these intermittent solid-liquid contacts. And also with that, we see that the droplet bounces to much higher heights with each jump. So it behaves as a trampoline. To study this further, we plotted the evaporation time with respect to a non-dimensional temperature theta, which signifies 0 as the start of the transitional boiling regime and 1 as the end of the transitional boiling regime. So we see that there is a dip in the evaporation time when the theta is around 0.4. So to see what happens at point 4 and what happens after that. We plotted the volume versus time graph. So we see that in the start, the volume change is much higher compared to end. So this happens because the evaporation time is a function of the droplet residence time and the droplet time in the air. So if we plot the average heights and the ratio of residence time with the evaporation time, we can see when the dip is happening, the residence time is increasing and the average heights are reducing. So droplet is more in contact with the surface. So that can explain the decrease in the evaporation time, while the further increase can be explained on the basis of film boiling, because the film boiling will then increase, which will reduce the evaporation time overall. The mechanism of going to higher heights can be explained in the process of bubble growth and then vapor escape, which can create a recoil force which propels the droplet in upward direction. The droplet can be assumed as a spring mass system when it's in contact with the surface, and when it leaves the surface, it acts as a projectile. Using the free body diagram, we can do the force balance and calculate the external force as a function of recoil force and the spring force as a function of surface energy forces. The theoretical and the experimental model fits pretty well. We have developed a mechanism to suggest the trampolining nature of the droplets in the presence of transitional boiling regime. Thank you.
Thanks, Pranjal, for that nice talk and well-timed video. So we'll now open the floor for questions to the speaker.
I have a question.
Yes, please.
Hi, Danny here. I was wondering, so you show that the bouncing increases with time, right? Sometimes, I mean, in your picture. And how does your spring mass model capture that?
So in the spring mass model, we apply an external force to the spring when it's in contact. So because of that external force, it gets an added momentum. So that's why it increases its speed of leaving. So that's how the height increases.
Oh, so that external model, external force is something that you'll extract from your experiment instantly.
Yes. So it can be extracted from the experiments using image analysis, and the order of magnitude of that extracted force was approximated by the recoil force, which we calculated using I've shown it here. So we calculated the recoil force assuming a semi-infinite heat transfer model. So we calculated the average heat flux, then the mass flux, and then we calculated the recoil force.
Okay, thanks.
Yes, we have time for more questions. So if anyone has a question, please go ahead, or you can put it in the chat box.
Jason, can I ask one?
Yes, please.
Pranjal, nice talk. So what kind of image analysis tools do you use for extracting the quantitative information from your experiments?
So we are using MATLAB for the image analysis process. So we first threshold the image and then use region props to get the region of the droplet. So we then use the area of the droplet and then we calculate the area of that blob that we have to calculate the displacements, and then also the diameter of the drop.
What if the drops, I mean, in some cases,
it won't be of this spherical shape.
Yeah, that's true.
So I took only those readings where the droplet is in the spherical shape, that when the circularity is equal to 1.
But the other drop shape fluctuations, everything could also be really interesting, right? So would you be interested to look at some of those things in future?
Yes, so we haven't considered any shape oscillations right now, but we will do that in future.
Yeah, thanks. Yeah, thank you.
Do we have time for another question?
Yes, Danny, go ahead.
So continuing, so your spring model actually explains your deviation in the perpendicular to the flow direction.
Yes.
But looks like the it also travels a bit, right? And if you look at the travel, it's also varying in distance as the drop bounces. Is that right? Did I get that right? From your
Travel in the vertical direction or in the horizontal direction?
horizontal.
Horizontal. Yes. So we are right now neglecting any horizontal direction movements. So since it's like a flat kind of surface, so every time it touches the surface, we are just taking into account only the y direction movements.
Okay, because I mean, this is just looking at one picture, but there could be a correlation, right, between how high it goes and how far away in horizontal direction it goes. Maybe you can. Anyway, thanks.
Danny, you're referring to the picture in the experimental setup?
Yeah, that's the one.
That the x-axis is time.
Okay, in this image, the x-axis is time. So this is for a different set of for different time durations. I just merged it.
Okay, sorry. Yeah, I thought it was the horizontal displacement.
Oh no. In reality, it moves around 2 to 3 mm in the horizontal direction maximum.
Okay. Good, thanks.
So we have time for another question. Okay, so Pranjal, maybe I'll ask you a last quick question. So first off, nice work and a nice presentation. So what kind of surface are you boiling it on, and did you see any difference in like the surface or the roughness of the surface or something like this?
Yes. So for a low roughness surface, so this surface one is of the least roughness. It's a polished surface. So in that we only saw this trampolining kind of behavior on one temperature. Then we increased the roughness. So then we were able to increase the transitional boiling regime, and then we were able to see more kind of these processes. So surface 3 is the maximum rough surface.
I see. So it delays the onset of film boiling.
Yes. So the transitional boiling regime, it kind of increases.
Okay, thanks, Pranjal. So we'll have to move on. But again, if you have questions, you can put them in the chat or contact Pranjal directly. So our next presentation is by Dr. Ruchika Dadich from IIT Bombay. And yeah, I'll let the video take over.
Hey everyone. I'm extremely delighted to be a part of this conference once again. Mycobacterial bacillus has a remark. After a brief background, I'll take you to the objectives of this work. In the course of infection, mycobacteria secrete these glycolipids onto the host plasma membrane, and the dynamics of this crosstalk can impact not just the lateral organization, but also the biophysical properties of the host membrane, such as fluidity and other nanomechanical properties. This leads to the activation of different signaling cascades in the host cell. Typically, SL1, sulfolipid 1, consists of trihalose sugar with a sulfate group as the polar head group, and the 4 acyl chains at 2, 3, 6, and 6' positions, whereas PDM has 2 acyl chains at 6 and 6' positions only. These acyl chains are branched and have huge chain lengths. For the sake of biophysical characterization, different analogs of SL1, such as one shown here, were synthesized. I would now summarize some of the important results. These are the cartoon representation of the synthetic analogs, differing from each other in the terms of acyl chain position and presence or absence of the sulfate group. The highlight of biophysical characterization was the ability of these lipids to depict phase coexistence, which is usually observed for lipid mixtures, not just spectroscopically, but also through confocal microscopy performed on GUVs of SL1 and super-resolution AFM on solid supportive SL1 bilayers confirmed coexistence of lipid domain of varying fluidity and order. It was further supported by MD simulation results, which showed phase coexistence for all analogs. MD simulations mapped the lipid chain conformation order and bilayer thickness of both natural and synthetic microbacterial lipids. And it established that the different chain conformations and the dynamics are actually responsible for this kind of lipid phase heterogeneity. It was also supported by the generalized polarization and FTIR spectroscopic results. Then we studied the interaction of these with the three-component Ralph Morin membranes, and it was seen that they have the unique ability to disrupt the ordered and disordered domains in the host model membrane, as shown by AFM breakthrough force analysis. In order to conclude, I would say that SL1, synthetic analog of SL1. Thank you everyone for your kind attention. I would like to acknowledge
So thanks for the video presentation, although it I think there were
yes,
some
it did
issues
not
with
play very well.
but in any case, yeah, but anyway, I think the floor is now open. There's plenty of time for questions. So
yeah,
I think people can, if there's something that got important that got skipped in the video, Ruchika, you can maybe take a minute or 30 seconds to just
yes.
fill in something if you felt you lost something.
Yeah, actually, I wanted to introduce this properly with the help of the mycobacterial membrane model that is already available, and we know that mycobacteria has a very different cell wall structure, and these are some unique glycolipids which are non-covalently attached on the surface of the outer leaflet. These comprise the outer leaflet of micromembrane, and these lipids are somehow correlated with the virulence, and there's plenty of evidence which shows that the virulence of mycobacteria is also because of these glycolipids. And once these are secreted onto the surface of the host plasma membrane, they kind of introduce a lot of effects. And this is what we have tried to study here. We have tried to study it through biophysical techniques, where we see that these are actually getting incorporated, and we have control experiments which show that they actually get incorporated and what kind of effect it has on the membranes. Also, we wanted to see how they would themselves, what are the properties
Sorry,
of
Ruchika, to interrupt. Sorry, Ruchu, but we'll have to open for questions.
Okay.
Yeah, okay. Okay, thanks. So yeah, so the floor is now open for questions, and you can interact further with Ruchika for the next 4 to 5 minutes.
Jason, can I ask a question?
Yes, go ahead, Basa, please.
Hey, hi. Nice presentation. So, are there any experimental studies that demonstrate a similar effect that you have been able to see in your simulations?
No, sir. We haven't come across any other study which, we have established if you're asking about my studies, yes, we have done it through experimental techniques as well. We can see that the phase coexistence is very clearly seen with the confocal result. And also through AFM, we could see that the two domains have a high difference of about 1.5 nanometers. And the total height of the bilayer was actually 6 nanometers. So we wanted to make sure that this kind of effect is actually existing for all other naturally existing SL1 membranes also. So we took help of the MD simulation, where we have been able to obtain similar results with all the analogs that we have created, and as well as the naturally existing lipids, the sulfolipid and the trihaloidimycolate. So we have full evidence which supports these.
How do you resolve this 1.5 nanometer that you were talking about?
Usually in AFM, what you see is this breakthrough force, and the thickness of this kink that you get is actually will tell you that there is existence of a different thickness membrane is present. And so through AFM, we can directly see the thickness of this membrane through the software.
Okay, but does it kind of confirm? Is it also confirmed by other technique? I mean, are there like scattering-based techniques that give similar thickness?
No scattering-based techniques. I mean, yes, we have done different DLS analysis to show that what is the size of liposomes. But for bilayer thickness, we all we have is this AFM. But if you want to ask something like how else we will make sure that this is happening, we could see it in the confocal microscopy results, where two phases are very clearly seen. But I cannot assure that the height difference there also is similar. But then we are not dealing with the bilayers also in confocal microscopy. We're dealing with the GUVs.
Yeah, thanks.
Hi, Ruchika. Can I ask a question?
Yes, ma'am. Yes, ma'am.
This is Sunita here. So about high resolution AFM images, I just was wondering how does it, because those are ex situ measurements, right? How does it compare your confocal data compared with the AFM data in terms of the thickness measurements?
No, we cannot compare the thickness, because in GUVs, it is not possible through confocal microscopy to measure the thickness. But we can only comment about the thickness through the bilayer that we form on the mica and study it under AFM. So that I cannot answer, because there is no other way out. But then we all have MD simulations to support this result, where the results clearly show that the two phases are different with each other, with that kind of thickness. The difference is quite similar, but I cannot quantify in the MD simulations, though it clearly says that the thickness is different.
Okay, thank you.
Yeah.
We have one more question.
So if I have a minute, then I can just tell that what we have done here. We have tried to characterize these lipids on their own, and what kind of phases they form and all those. And then we have studied the interaction of these with the model membranes as well as with the THP1 cells. And some of the good results I've already kept in the poster. So also, I wanted to explain that with THP1 cells, which got cut off in between, that these lipids actually arrest the maturation of the autophagosomes. And it is very clearly seen in these results that the autophagy flux increases because they don't get matured, and they do not form the autolysosomes. So that completes my explanation, which got cut off in between. And I'm so sorry about that.
Thanks a lot, Ruchika, and also to the audience for interacting with the speaker. So we'll now move on to the next presentation in the lineup. So next we have, sorry, just give me a second. Yes, so we have Ganeshula Prashant from IIT Madras, and to tell us about experimental investigation of sedimentation of shape anisotropic colloidal particles. for ideal dispersion. Sorry. So over to the video.
Hello everyone. My name is Prashant, PhD scholar working under Dr. Basavaraj from IIT Madras. Today, I am going to talk about one of my research works where we experimentally study sedimentation of non-spherical colloidal dispersions. Sedimentation is a process where particles in a dispersion are allowed to settle at the bottom of the column in order to separate them. Gravity settling is a simple yet an effective method of particle separation that is important in many applications such as wastewater treatments, mineral processing, pharmaceutical manufacturing, etc. Vast amount of study has been done on sedimentation of spherical particles over decades. However, in most cases, the slurries or the dispersions consist of non-spherical particles where the geometrical aspects such as shape, size, and orientation of the particle during the fall can significantly influence the settling behavior. Also, there could be particles of colloidal size range which are present in the dispersions, which not only exhibit settling behavior but also Brownian effect. With that being said, in the present work, we experimentally investigate the effect of particle shape on the settling behavior and also the Brownian effect on the settling. I will also present the concentration dependency of sedimentation process. To start with, hematite particles of different shapes, namely cube, peanut, and spherocylinders were synthesized and well characterized as colloids. Experiments were carried out over a range of concentrations. The color property of the hematite allows a good visual observation of the fluid particle interface during the sedimentation process. The figure here shows the image of glass wells at different times during the experiment using a camera setup. Fluid particle interface height data is extracted from the images using the image analysis software and also from RGB intensity plots. Sedimentation rate of the dispersion is calculated by drawing a plot between the interface height and the time where the slope of the plot gives the bulk sedimentation velocity of the dispersion. Experimental observations are discussed and analyzed in terms of well-established settling velocity correlations developed for spherical particles, but by taking particle shape anisotropy into consideration. Experiments over a range of concentrations were done and plotted here. The plot shows the effect of dispersal concentration on sedimentation, which is in good agreement with the theoretical understanding, where the values are less than the single particle velocity. The dotted line here indicates the settling velocity of a single particle calculated using Stokes' equation by considering the volume equivalent diameter for a non-spherical particle, which gives a qualitative understanding of settling velocity of a single non-spherical particle. An attempt has been made to validate the experimental data with theoretical study where we used Carey-Lee equations to calculate the settling velocities of non-spherical particles by considering the shape anisotropy and the orientation of the particle. The green band in the plot indicates the range of settling velocities that can be exhibited by the particles considering the size, shape, and orientation. It was observed that the settling velocities of the shape anisotropy particles are within the range of possible values, which is a good validation of experimental data. Thank you for your kind attention. I hope you like the presentation. Kindly stop by my poster and share your valuable comments. Thank you.
So thanks, Ganeshula, for the video. And the speakers with us, the floor is now open for questions.
Jason? Sorry. Jason, can I ask a question?
Yes, go ahead, please.
Hello?
Yes.
Yes, please go ahead.
Yes, sir.
Ganesh, so if I'm just looking at your poster, and there is this image where you show there are 4 bottles, right? 0 hour, 2 hour, 4 hour, 6 hours. And then you say that this, so from here, what is it? So first, I just want to understand how you're going to use this for quantification and why all of them look orange. Can you tell me and explain how you will get quantitative information from this graph, from this experimental images?
Images.
Right. So
Yeah.
you have this set of images, right? 0 hour, 2 hour, 4 hour, 6 hour. There's a bottle and things are settling in the bottle.
Yes. So we
So
take
how,
the images at regular intervals of time, and using image analysis software like ImageJ, and also we also backed up the data using MATLAB intensity plots, where if we read the image, it will give the intensity plot, which is for the color intensity, it will give one straight line, and where the intensity is dropping, where the color is changing, it shows the interface. We can point out the interface there, and where it shows the intensity drop from there. So in image analysis also, you can draw a line, and you can draw multiple lines over the diameter of the vial, and we can average the measurements, so that we give a good value of interface height.
okay. So is it possible to know what is the concentration in the fluid right above the interface and below the interface? Do you have any idea of the concentrations?
Yes, like I said, the classical sedimentation experiments previously a lot of people have done. We have a simple mathematical formulation where we can calculate the concentration of the uh, particles within the below the interface height.
Okay,
It
well,
is possible.
what is that? You have it here, or it's,
I don't have it in the presentation, but we can simply use C1H1 is equal to C2H2.
so what will be the orders of difference between the concentrations in the outside and on the two sides of the interface?
We are assuming, I mean, it is not possible to assume a complete sedimentation, but I don't think there will be the concentration above the interface will be much lesser than concentration which is below the interface. So orders in the sense, let's say if I start with a concentration of 1 weight%, within the experimental time that I am working with, I can expect a concentration of 5 at the interface after complete sedimentation, given the height of the interface. It is possible
Okay,
to measure,
thanks.
sir.
Thanks. I'm done, Jason.
Yes, go ahead, please.
Okay. Prashant, so is there any, here, why they are settling? Is it due to the aggregation or just due to the...
We expect the particle, the experimental conditions that we used are, after measuring the zeta potential of the particles, we see the charge on the particle is minimal, so that the particles settle due to gravity. But at the same time, we also anticipate the Brownian effect of the particles, because the particles are in the colloidal size ranges. So they do settle because of the gravity.
So if you coat with some silica, let us say, and you make zeta potential very high, do they still settle like this?
I mean, it depends upon the surface ratios, surface area ratios of the particle of silica and hematite. If you use more of silica, they might be stable in the suspension. If the concentration is well enough to concentration of silica is well enough to cover a single hematite particle, now that with the increased mass and the charge neutrality, it might settle even faster also. Both things are possible with the change of concentration of silica particles.
Okay, one more question,
yes,
last. Sir. So here they respond to the Earth's magnetic field also, right?
Yes.
They are aligned. So is there any preferential direction that they sediment during the settling?
In general, we see the particles settle downward due to gravity. So we have done some couple of microscopic imaging where we go to certain plane in the inverted microscope into the sample, and we see the particles actually moving only downwards. Yeah, with slight deviations along with the horizontal directions because of the Brownian effect. So.
Okay, why these peanuts settle faster than the others?
I'm sorry to interrupt, but we are almost out of time.
Yeah. Here in this case, the size of the peanut shape is little bigger, and also the shape effect is also, I think, we are considering. So we are actually characterizing
okay,
the behavior of the peanut here.
Right.
Okay, so thanks, Prashant, for that nice presentation. So we'll now move on to the next poster in the series. So the next poster is by Nitin Madhavan from IIT Madras. Over to the next video.
Hello everyone, I am Nitin. I am a PhD scholar from IIT Madras. I am working with Dr. Manas Mukherjee from Department of Metallurgical and Materials Engineering and Dr. Basavaraj MC from Department of Chemical Engineering, IIT Madras. Topic of my today talk is porous ceramics from processable Pickering emulsion stabilized by oppositely charged colloids. I would like to begin by giving a brief introduction on porous ceramic. Macroporous ceramics with controlled microstructure and chemical composition are required in many engineering applications. Properties and functions of porous ceramics are very much dependent on the processing routes used. Processing route can be classified on the basis of sintering process. It can be a direct sintering process or a reactive sintering process, and also on the basis of the methods used. The methods can be replica technique or direct forming or sacrificial templating method. In this work, we have used Pickering emulsion droplets as sacrificial template for the production of porous ceramics. Here we have exploited the electrostatic heteroaggregation between the oppositely charged species for the stabilization of the Pickering emulsion. Apart from this, for the successful conversion of emulsions into porous ceramic, it has to satisfy certain conditions. It should be processable, that is, it should have a gel-like behavior and should have long-term stability and controllable microstructure. Now, on the basis of sintering point of view, particle loading should be enough to prevent microstructure collapse during sintering, and emulsion composition should be matched with the stoichiometry of the resulting ceramic. Emulsion formulation were designed for both direct sintering, that is type 1, and reactive sintering, that is type 2 conditions. In the first case, we have used Pickering emulsion stabilized by particle polyelectrolyte complexes, that is PPCs as template. Here we have prepared Pickering emulsion by using positively charged rhodoxyl particle, which is an alumina coated silica particle, and negatively charged polyelectrolyte, polystyrene sulfurate, that is PSS, at different mixing fractions of PSS. Upon mixing, they form particle polyelectrolyte complexes. Emulsions were prepared by using high energy homogenization by adding decay as the oil phase. The emulsions stabilized by PPC were used for the preparation of porous ceramics by drying and sintering. We observed that low charge PPCs are forming at intermediate mixing fractions are well suited for emulsion stabilization. At higher concentration, PPC stabilize Pickering emulsion gels, and gel modulus depends on the mixing fraction. These emulsions are processable and they were dried and sintered at 1000 degrees Celsius. The microstructure and the porosity were characterized by scanning electron microscopy and mercury intrusion porosimetry. We observed that polyelectrolyte acts as a binder during drying. After sintering, porosity is decreasing with the increasing mixing fraction of polyelectrolyte. Highly porous structure is obtained at 0.2 mixing fraction. We concluded that an optimum particle loading is required for getting highly porous structure. In the second case, that is a type 2 process using reactive sintering, we have used Pickering emulsion stabilized by oppositely charged particle, that is OCPs as template. We have prepared Pickering emulsion by using positively charged fumed alumina particle and negatively charged fumed silica particles at different weight fractions of fumed alumina particles. So these particles are fatal-like. Upon mixing, they form heteroaggregates of low effective charge. The emulsion stabilized by heteroaggregates were used for the preparation of porous ceramic by drying and sintering. We observed that weakly charged heteroaggregates forming at intermediate composition stabilized Pickering emulsion. At higher particle concentration, emulsion gels were obtained in which droplets were clustered. These emulsion gels were taken at the composition of the resultant ceramic and were further processed to obtain porous ceramic of specific composition, namely moonlight. The microstructure, phase evolution, and porosity and interconnectivity of the resulting ceramic were characterized. So here we have obtained highly porous interconnected moonlight. Ceramic is obtained by removal of the dispersed droplets by drying and sintering. So we concluded that we have proposed a general and scalable route for preparing porous ceramic for Pickering emulsion stabilized by mixtures of oppositely charged particles or particle polyelectrolyte mixtures. Mixtures of oppositely charged species are effective in emulsion stabilization. To obtain a porous ceramics of controlled microstructure and composition through type 1, there is a direct sintering process, requires an optimum particle to polyretrolate ratio for control of the microstructure. And type 2 requires an optimum emulsion composition to get highly porous ceramic phase. Thank you for your kind attention.
Thanks, Nitin, for your video, although it was a bit on the long side. But in any case, we now have still about 3 minutes for questions. So the floor is open. If you have a question, please go ahead.
Jason, I have a question.
Yes, please.
How do you measure this droplet size in the dense state like gel that you showed?
So we perform the image analysis for measuring the size, image analysis.
But in they are so dense, how do you?
No, we actually made them. So we diluted the gels also. So then we have measured.
Okay. Okay, thank you.
Sir, I have one question.
Yes, go ahead.
Nitin, can you hear me?
Yes, sir. Yes, sir.
I think I'm audible.
Yes, sir. I can hear.
Yes, sir. I have some very foolish questions. So one is, can you just tell me what these ceramic particles are? And the other question is, why are you trying to stabilize them? What happens if you don't do that?
These particles are, the first case we have used a particle polyelectrolyte mixture. The particle is a spherical silica particle and a polyelectrolyte is polystyrene sulfonate. In the second case, we have used fractal-like particles, fumed silica and fumed alumina. So upon mixing, they form low charge complexes or heteroaggregates. So they have low charge so that they can stabilize emulsions. So for getting in porous ceramics out of that, we have performed the drying and sintering.
Okay. And why did you have to stabilize this?
No, for making an emulsions, for getting in porous ceramics, we have to go for some templating method. So this is an emulsion templating method we have used here. So here, so accordingly, the ceramic composition that we required finally. So accordingly, we are choosing the particles.
And the particle size is what? I might have missed that, sorry.
Yeah, the low particle is a 15 nanometer spherical particle, but the fumed silica and alumina are 15 nanometer. That is a primary particle, but they are fused during the preparation itself. So it's like a fractal-like particle.
Okay. And there is no spread, right? I mean, after 15 is probably the mean, but there must be a spread around that.
That is actually the spherical particle or monodispersed particles. But in the second case, we are using a fractal-like particle. So the primary particle size we have measured, that is coming as 15 nanometer. But they are fused.
But if they are fused, then if they are fractal-like, that means that there are many scales. So are they all fusing into a very large structure? So are the agglomerations very, very large? Then?
Yes, sir. It's large.
So if the agglomeration is very large, maybe a micron, I'm just guessing. Can it be stabilized then? Wouldn't it be too large for a ceramic particle to be stabilized?
No, I didn't get the point, sir.
Is a particle?
I'm sorry to interrupt, but maybe we can just see if there's someone else has a question.
Yeah, I have a
question. Because otherwise,
I have a question.
Yeah, Danny, go ahead.
Nitin, nice talk. So I was wondering, do you see any correlation between droplet size distribution and the porosity distribution in your ceramic?
Yes, sir. They are same. Actually, after drying, we have actually, I didn't show it here. After drying, we have measured the pore size distribution also. From the SEM images, we analyzed the SEM images and found. So it's coming exactly same after drying.
By exactly same, do you mean the image on top 2C, your Pickering emulsions 2, and there's one double P, no? Are you saying
Yes.
you'll get something exactly like that?
It means there is some shrinkage is happening, but still it's coming in that range. So here I'm getting an
Shrinkage would mean that it's moving left. Is that right?
because of heating, it's coalescing. Because of this heat treatment, it's coalescing at high temperature.
So let's say if I took a droplet size distribution with 5 peaks, you would expect 5 peaks in your porous size distribution. Is that right?
Yes, sir. Yeah.
Okay. That's very interesting. Thanks, Nitin.
Okay. Thank you, sir.
Okay, thanks, Nitin, and thanks to the audience for the questions.
Thank you.
So we now move on to the next presentation. This poster is by Rajkumar Biswas from RRI. So we'll now watch his video.
Good morning, everyone. Today I'll talk about quantifying the destructuring of a thixotropic colloidal suspension using falling ball viscometry. So here I will use Laponite suspension and I will perform falling ball viscometry to see how the motion changes. So I can divide my talk into three topics. One is geology of Laponite suspension, and then I have performed falling ball viscometry in Newtonian sample to calibrate our viscometry. Then I will talk about the falling ball experiments in Laponite suspension. So here in rheology, from these plots, we have calculated viscosity with time and shear rate. So in it, here we have shown the aging process of Laponite. Here we have shown the shear thinning process as the shear rate increases, viscosity decreases. And in this plot, we have shown if a fixed shear relatively high, 100 or 180, applied to Laponite suspension for certain time, what happens. So first is shear thin, then it increases due to aging. So because Laponite grows structure with time, this kind of properties is observable, and it can be explained using this lambda model where rate of restructuring and destructuring defines this rate of structure parameter, time evolution of structure parameter, where eta viscosity depends on the structure parameter. This is the experimental setup which we have used to perform our falling ball experiments. And then first we have calibrated our viscometer using Newtonian sample, which is crystal water mixture. And we have found that for this case, it achieves a terminal velocity, but it requires a drag correction, which is defined by, which is by scalar Norman correction, and which fitted with our experimental data, which is circle, brown circles. So now let's go to the main topic, which is falling ball experiments in Laponite suspension, where we have proposed the model where when the ball travels through the medium, it shear thins around it, and this shear thinning depends on the velocity it travels and time required to travel its own distance. So by assuming that we have written this equation df/dt minus ed by d by d. This minus sign is because this is destructuring, and we have solved this we have integrated this, and we got the lambda. We have included this in the eta, and we have modified the velocity term. So by replacing the velocity in this equation, we get the velocity with time relation where beta is there, which actually shows the shear thinning effect. So this is the experimental data for Laponite suspension for 2 mm, 3 mm, 5 mm, 6 mm diameter. For 2 mm, the ball achieves terminal velocity for all the aging time, but for 3 mm, it achieves terminal velocity for 1 hour, but 3 hours there is a gradual increase. The increase is more prominent for 5 and 6, so you can see the velocity does not achieve terminal velocity, continues to increase because of shear thinning. And this can be quantified here with beta. I plotted here. So for 6, the beta value is high, which shows at 6 mm ball diameter, shear thinning is more, and it is destroying the structure more than 2 mm, where it is nearly 0. So we have developed a model which can successfully describe the motion of the ball inside Laponite suspension, and larger balls are not attaining steady state for our experimental window. And destructuring rate indicates the effect of shear thinning, that it is more prominent for higher diameter balls. Thank you.
Okay, thanks for the presentation. The floor is now open for questions to the speaker, Rajkumar Biswas. So if you have a question, please go ahead.
Rajkumar, I have a question. So I was wondering, the motion of the ball does not seem to be a straight line, right? Can you comment on that?
Yes, yeah. So you are saying that it is not going down in a straight line, right?
Yes, that image, if someone
Yeah.
can roll the.
So we have also calculated along with the vertical velocity, we have calculated velocity in the horizontal plane. So we measured that, and it is very less than the vertical velocity. So by calculating, we have seen that it is very small. So we can neglect that.
But why do you think it happens? I mean,
So there can be some kind of rotation. So because of that, or because of the drop mechanism, also it can happen.
Okay. Okay, thanks. A quick follow-up, if I may.
Yes, Danny.
Yeah. So in one of your plots, looks like there's a tiny bit of non-monotonicity happening for every one of your runs. Okay, how do I read this plot now?
So you are saying the velocity versus time.
Yeah, the fourth one. Yeah, where it increases. You see a non-monotonicity for every one of those plots, no? So I'm little.
Yes.
Yeah.
So because it is at a high Reynolds number, so this because of turbulence that can happen when it is entering the fluid, and at high Reynolds number, that slight vortex shading or something like that can happen. That is for calibration experiment, which we did for new glycerol and water mixture. But for a Newtonian sample, we did not observe those systematic kind of bumps.
That's for Newtonian liquids, is it?
That is for Newtonian liquid. Yes. That is a very low viscosity. That is 0.016 Pascal second.
Okay, thanks.
Jason, do we have time for one quick question?
Yes, go ahead. Yes.
Thanks. Rajkumar, a nice presentation. Can you just tell me one thing? When you are doing this viscosity measurements,
yes,
you have the viscosity measurement with the shear rate, and so outside of this, so this seems to be a very restrictive 0 to 100. It's only 2 orders.
Yes.
So have you done it for more orders of magnitude of shear rate?
Yes, we have done it up to 1,000. So it is same.
There's similar behavior. Huh? You don't shear thinning anywhere.
No, this one you are talking about Newtonian, or the straight line is for Newtonian, that glycerol water mixture.
Oh, okay, got it. Okay.
So that will be like fixed only.
Okay, yeah.
So we have time for at least 2 more minutes for questions.
Okay, maybe I'll ask one follow-up question.
Yes, go ahead.
So, Rajkumar, sorry, at that time I was focusing on the wrong graph. The graph I wanted to ask you about was the viscosity versus shear rate on the left-hand side, where you go from 10 to the minus 1 to 10 to the 3. And how do you know that there is no microstructure ordering or changing? Do you know? Do you have the equipment to look into that when you're doing this experiment? Do you know any comment on that?
So microstructure, while doing rheology, it is not possible. But we have done cryosem of laponite, where we can see the formation of structures. Yeah, for different aging times.
Okay, thanks.
So we can take one more question. So Rajkumar, maybe I'll ask you a question. So what is the Reynolds Reynolds number of the flow in the case of the shear thinning fluid, the complex fluid?
So complex fluids, calculating the Reynolds number is a little difficult as it is not achieving any terminal velocity, and also the viscosity changes with the applied shear rate. So what we have done is, like we have done it for Newtonian with similar velocities we observed. We have prepared this Newtonian sample where the velocities are similar. So to say that this is the order of same Reynolds number. That is the reason we perform the Newtonian experiments, and also to say that these equations are also valid in this range. So the order is around.
You are saying your Newtonian experiment had the. Sorry, carry on.
So it is the order for Newtonian is from 12 to 355 Reynolds number.
Okay, interesting presentation. I'll ask some more questions later in the chat.
Yeah, sure.
So we'll now have to move on because we're out of time. So thanks, Rajkumar, for that. We'll now move on to the next presentation, which is by Rumaiya Pervin from IIT Madras.
Hi, I am Rumaiya Pervin, PhD scholar from IIT Madras. I am working under Dr. Basavaraja and Dr. Pijit Ghosh. In this e-SMYIM event, I will be talking on controlled polymer film porosity for solvent-triggered self-actuation. Inspiring from self-actuation phenomena happening in nature, such as Venus flytrap, Pachminot plant, there are enormous synthetic approaches have been performed for synthesizing and for transforming shapes which are initially 2D to 3D, such as Dr. Leonard Einach and co-workers have developed three-dimensional pyramid shape structure from initially 2D planar films. They showed one video where you can see how the shape transformation happens from 2D to 3D. This behavior of shape transformation can potentially be used in controlled drug release system. In this study, we developed a facile route for the fabrication of porous polyvinyl alcohol films. The route is very simple, which is slightly different from the existing immersion precipitation technique. In this technique, we casted the polymer solution directly into non-solvent. After some time, around 50 to 60 minutes, the precipitation complete and the flame solidified. This flame is dried under ambient condition, and you can see here this is the digital image of the dry flame. As I already mentioned, that technique that route is very simple, where polymer flame porosity can be tuned simply by adjusting the initial volume of PVA solution as well as the initial volume of IPA. You can see here how the morphology has been changed. Coming to the pore formation mechanism, I will briefly discuss about the pore formation mechanism. This is liquid phase separation of non-solvent droplets IPA. So we experimentally observed that the top surface of the film is always non-porous, whereas the bottom surface of the film is always porous. This is simply because that in the top surface, the precipitation is happening prior to phase separation, while in the bottom surface, the precipitation always happens before any precipitation takes place. And then I will discuss about folding of different porous polyvinyl alcohol films. This is a schematic of this folding phenomena in response to water. Here, that folding of PVA films has been shown. You can see how the curvature of the film has been changed with time, folding time. And then I am showing some examples of curvature change which I measured by measuring theta, that is changing slope of the tip of the film. Yeah, that's all. Thank you.
Thanks, Rumaiya, for that nice and well-timed video. So once again, the audience is free to ask questions to our speaker. So please go ahead. If
Hi, please feel free to ask any question. My voice was not clear during the video.
Hello, Rumaya.
Yes, yes.
So you're using this ISO IPA, right? The droplets you are mentioning. So that will be evaporating after some time.
Basically, the droplets is not evaporating. This is phase separation phenomena. So during the flame formation,
yeah,
that IPA droplets are there in the flame, and once phase separation complete, then we need to remove the flame from the mixture for the complete dry. So during the drying process, all the droplets will evaporate, which form the pores in the dry flame.
Okay. So which way you are drying? It's in the room temperature. You are drying these flames.
Yeah, it's basically in ambient condition in air, room temperature.
Thank you.
Hello, Rumaya.
Yes, sir.
Did you try to measure the mechanical properties of these films?
Yeah, exactly. We measured the mechanical property. I have not shown here. So we have observed
what
that.
What do you expect if you increase and decrease this PPA volume and IPA volume?
So basically, depending on PVA volume or IPA volume, the porosity in the flame will change. And then because of changing porosity, the modulus of the flame, the dry flame, will also change. So we observe that when porosity increases, the modulus decreases. And also another very nice property we observed, that tensile property. So if we increase the porosity by changing the amount of PPA or IPA, we have observed that the elongation properties increases very nicely. It goes up to 800%.
Okay.
While in the non-porous film, we have observed that the elongation property is around 300 to 400% for the same film, same thickness.
Okay. Thank you.
yes, we have time for more.
Please feel free to ask any doubt. I am happy to answer.
Yeah. So, Rumaya, I have a question.
Yes.
So you characterize this folding behavior. So what is the time scale of the dynamics at which it starts to fold and things? Does this happen like very quickly, or it's a slow process?
Yeah, actually it took quite a minute. Let's say sometimes 15 minutes, second. Extremely sorry, second. So some flames, depending on the thickness of the flame, it varies. So basically in 50 seconds, 36 seconds, in this particular example I have shown, it took 36 seconds to completely fold. And it took somewhat 45 to 46 seconds to unfold. And it completely come back when we remove from the water surface.
I see. So, and if you repeat this let's say 4 or 5 times, do you lose this behavior, or is it like very robust? I mean, if I put it in water, take it off, put it in water, take it off, does it like, how long does it take to kind of lose this effect, or it's very, I mean, it lasts for a long time?
So you are saying that for the same flame, if I repeatedly do the same thing.
Yes, will I see the same behavior?
Yeah, yeah.
Or is there some like deterioration?
If I do the similar experiment for the same flame repeatedly, let's say initially for the dry flame, it took around 36 seconds. Now after one complete experiment, the solvent will go into the matrix, in the flame matrix. Then if the solvent evaporate completely, then it will come back to the original position. Then if you do the similar experiment for the same flame, the mechanical properties somewhat will get distorted because there will be some bound water inside the matrix, which was not there at the first time of the experiment. So obviously there will be some change in the mechanical property which cause the change in folding behavior. Basically, for the folding phenomena happening, it needs some mechanical strength, that is modulus of the flame. So if you change the modulus of the flame by some other means also, it will affect the folding phenomena. So obviously your question is very good in the sense of mechanism of folding. So it will affect the folding time as well.
Thanks a lot, Dr. Meyer. So we're out of time now, so we'll move on to the next presentation. Thanks again to the speaker. So our next talk is by poster talk is by Palak from RRI.
Hello everyone, I am Palak. Title of my poster is Side Branch Patterns, Coalescence and Stable Interfaces during Radio Displacement of a Viscoelastic Fluid. This work is done in collaboration with Rahul and Dr. Sriram from IIT Madras and supervision Professor Ranjini Dandapatya. Now the displacement of a more viscous fluid by a less viscous fluid renders the fluid-fluid interface unstable and leads to intricate patterns called viscous fluids. The nature is full of these intricate patterns, for example, tree branches, formation of river networks, and even in human lungs. To understand the problem experimentally, people openly use Hilleshoff cell. Now, for our study, we have used radial Hilleshoff cell, and we have used a pair of Newtonian and a viscoelastic fluid. So, the glycerol water mixtures are used as inner fluid of viscosity eta in, and constant suspension is used as outer fluid of viscosity eta out. By preparing constant suspension, we have added cesium chloride for the density matching. Now, constant is a well-known viscoelastic material exhibiting properties of shear thinning and thickening. So, this is a viscosity versus shear rate plot for 35% of constant suspension. And this black line over here shows a fit of the data to a simplified Taylor-Rosada model, where this is the zero shear viscosity of the system, tau is the relaxation time of the system, and n is a power exponent. So, since the viscosity mismatch plays an important role in the interfacial instability, so we have done experiments at different viscosity ratios and observed a transition from side branch patterns to more stable interfaces. There's an inner darker region which appears and gradually increases with increasing viscosity ratio and covers the entire pattern with small protrusions at the periphery. So to quantify this pattern, we have calculated the size ratios and observed a decrease in the finger length with increasing viscosity ratio. So we have also calculated the sweep efficiency for these patterns and observed an increase in sweep efficiency with increasing viscosity ratio. Now, while exploring the temporal evolution, we came across an unusual feature characteristic of proportionate growth. So here you can see these are the patterns which are acquired at a viscosity ratio this for 3 different times. So they appear in this new shape, and when we have plotted the size ratio for this case, we got a flat curve up to a characteristic time Tc, and later on it starts increasing. Now, to understand the problem numerically, we have calculated the most dominant wavelength by using a dispersion relation proposed by these guys and incorporating the values obtained from this fitting. So, and this plot and compare these values with the average finger spacing, which is obtained experimentally. Now, from this plot, we can see both are in the close agreement with each other and increases with increasing viscosity ratio. Now, for an intermediate range of viscosity ratio, we have observed the coalescence events where a finger starts bending towards an adjacent finger and eventually merges to form a wider finger. And this event is followed by another event where a low outer fluid is trapped inside the inner fluid and which eventually diffuses at a later time. Now, to quantify these observations, we have calculated the perimeter and the overall width of the patterns. And For intermediate range of viscosity ratio, as you can see the blue curves over here, there is a dip in the values of both like perimeters and the overall width. So which is happening because of the coalescence cement. Now I would like to conclude by saying that the patterns are governed by the viscosity ratio, where we observe the transition from side branch pattern to more stable interfaces. Pattern emulsion exhibits unusual feature characteristics of proportionate growth and the coalescence events. So the coalescence events are predicted earlier in the nonlinear simulation of interfaces between a viscoelastic and nonlinear fluid, Newtonian fluid, but it's observed experimentally for the first time. And the successful application of Carrier-Suda model confirms that the shear thinning nature of outer fluids has an extremely significant contribution in determining the morphologies and the landscapes of the interfacial patterns. Thank you.
Thanks for the video. We can now take questions from the audience. Is the speaker with us?
Yeah, hi sir.
Okay, great. So yes, the audience, please ask your questions if you have any.
Jason, I have one question. Palak, it's a very nice work.
Thank you, sir.
So what is the concentration of cornstarch that you have used here?
It's 35%.
So what if you go beyond 30 or?
Yeah, so actually,
so
the thing to do here is like cornstarch is the viscosity of cornstarch is shear dependent, as you know, and if you increase the concentration, so then this shear thinning and the shear thickening behavior will occur like at the lower shear rates. But the purpose of using this particular concentration is like there is to get a huge range of viscosity ratios over here. So that's why we have used it. Otherwise, if we increase the concentration, then we'll be exploring two regimes. We also have done experiments at that higher concentrations also. And when we done the experiments, there was some unusual characteristic of reverse fingering observed there. Like if you go at the higher concentration at higher flow rates, so there was a reverse fingering. So the inner fluid starts pulling back the outer fluid. So that happens at the high concentration. And if or the other factor is like the cornstarch becomes more elastic with the increasing concentration. So the elasticity tends to decrease the growth of the finger. So there we have saw a decrease in the finger length with increasing concentration of cornstarch. So I haven't incorporated the data over here, but if time is there, so I can share the screen and show you those images, like if I'm allowed. So
meanwhile, I have another one. So why don't can we use the other viscoelastic materials than this cornstarch?
Yeah, we can use that, but the purpose of using this one is to explore these two regimes together, and plus to have to do it at the different viscosity ratio. So that's why we have just used it. So yeah. Shall I share the screen or like?
Yeah, if there are no questions, you may share.
Okay.
Just a sec. So.
Yeah.
No, I think it's okay. You can just stick to the presentation and maybe discuss later. Because,
okay, sure. Okay, yeah.
So if are there any other questions? We have maybe another couple of minutes, 1 or 2 minutes. Okay, so Pulp, maybe I'll ask you a question. So
yeah, sure.
In all cases, the cornstarch is in the shear thinning regime, if I understood you right.
Yeah, right. So
and your inner fluid is always less viscous.
Yeah.
Or,
so yeah, it's always less viscous. We are always in that regime. So we have used glycerol water mixtures. So it's these two are miscible in all proportions. So we have taken the different proportions of like different concentrations of glycerol water mixture, and that's how we have controlled the viscosity ratio over here.
Okay, and the last thing is, so would you characterize this as a immiscible or miscible fingering?
Miscible.
So are these things soluble in each other, the cornstarch and
Yeah, so these are considered as miscible
And have you been able?
Yeah.
And have you been able to compare it to equivalent Newtonian displacement with similar viscosities?
Yeah, so there was one study where they have done the experiments with the Newtonian fluids, like pair of Newtonian fluids. So there was not like, yeah, so the patterns were like the thicker fingers were there in the Newtonian case, like we have got this side branch, like side shedding of the like branches at the low viscosity ratio. And for their case, they have observed a suppression of instability at much lower viscosity ratios than for our case. Like even at the higher viscosity ratio, we are getting small protrusions at the periphery. So there is a study which claims that the elasticity of the outer fluid plays an important role over here. So basically elasticity increase the most dominant wave number, like and you can say the characteristic wavelength, such that it divides the interface into multiple protrusions, like multiple number of fingers. So that's what we are expecting, which is happening over here. That's why we even at a higher viscosity ratio compared to the Newtonian case, we are getting the small protrusions.
Okay, thanks, Palak. Nice work.
Thank you.
So we'll move on now to the last poster.
Okay. Thank you.
Thank you. Yes. So our last poster is by Anjana Menon from the IITB Monash University collaboration. And let's hear her video.
Hello everyone. My study is on the effect of antitubercular drug on mycobacterial cell membranes at different growth stages. The distribution of lipids in the membranes changes during the early and late infection phases. To be specific, the amount of surface lipids, PDIMs, TDM, and TMM decrease during the late infection phase, while the amount of lipoarabinomanans and lipomannans increase during the late infection phase. This could influence the transport mechanism of drugs for it to reach the site of action, which is within the cell. Therefore, the influence of exposed outer membranes and inner membranes in the drug transport mechanism is studied here. The properties of the membrane varies across the outer and inner regions and across infection stages. Outer membranes are rigid and dynamic throughout the lipid bilayer at both early and late infection stages. A successful first-line antitubercular drug rifabutin localizes evenly across the lipid bilayer, changing the dynamics of the membrane as it gets across. The inner membrane at early infection stage is least dynamic among all the four, where the dynamics changes only at the deeper acyl chain region. And therefore, the rifabutin gets localized at this region, changing its dynamics. The inner membrane system at late infection stage is having extremities of dynamics, but it's least rigid among all the four systems, allowing a free flow of the drug across the membrane. Although rifabutin's partitioning is highest in inner membranes at the late infection stage, in a living cell, a drug has to cross the outer membranes before it reaches the inner membranes. Therefore, the effective amount of drug partitioning into the membranes during the late infection phase would be much lesser than what it would be during the early infection phase. And therefore, the outer membrane systems might be acting as an effective barrier to such drugs. And to prove this further, experiments can be conducted. Thank you.
Thanks, Anjana, for that video and for keeping so well to time. So the floor is now open once again for questions to the speaker.
Hi. Please feel free to ask questions. I forgot to mention that I've done experiments for determining the drug partitioning and the localization, which I had explained the results in the presentation. Right.
Jason, I may ask a question.
Yes, please.
So thanks for the talk, Anjana. Can you? I mean, I'm somewhat of a novice in this. Could you just explain to me how the drug crosses over to the membrane? Is that a diffusion process, or is there a chaperoning process involved, or how does that really happen?
So for these are like lipophilic drugs. So these would be passing across mainly due to passive diffusion, but then it has not been studied yet. But here there is a study where I have used fluorescent probes within the membrane, and these probes are getting quenched. So this experiment proves that the drug would be passing across the membrane through passive diffusion. There could be other methods, but it's definitely also passing through passive diffusion.
Okay, thank you.
Thank you, sir.
So we have time. So Anjana, I'll ask you a question.
Yes, sir.
So I'm wondering now, like you said, it's passive diffusion through the membrane.
Yes.
So I'm wondering, is the diffusion through this membrane Fickian, or in other words, from your data, can you like describe it with a simple model of usual diffusion through an interface, or is the presence of these polymer chains and things like this hindering the?
So the different structure of these lipids could could control the transfer of these drugs across the lipid bilayer, but what we can see is in this quenching, if I'm referring to the drug location experiment done where the fluorescent probes are quenched with the help of rifabutin, and these fluorescent probes are located within the membrane. So what we can observe is that there is definitely in all these membrane systems at early and late infection stage, the drug do gets across the membrane, which can be proven by the quenching of these fluorescent probes within the membrane. But the extent of quenching is different in different membranes. Say it's early or late, it would be different. So this difference in quenching is influenced by the different lipid compositions in each membrane. So definitely the membrane composition do affect its potential to get transferred across the membrane, and that can be like understood from the drug location studies.
Thanks, Sanjana. We have at least one more.
Hi, please feel free to ask questions.
Okay, so if there are no further questions, on behalf of the audience, I'll thank you again, Anjana, for your nice presentation. This brings us to the end of this poster session. So thanks to all the speakers and all the audience for their interaction and for making this a nice and very instructive session. So with that, I'll hand it over to the organizers. Thank you.
Thank you very much, Jason. So on the behalf of the entire SMYM organizing committee, I'd like to thank the two judges, Jason and Udita, for being part of this event and sitting through all the posters very patiently and listening to them and for conducting this event in the wonderful manner that it has been conducted. So thank you, the two judges, very much. I'd also like to obviously thank all the students for participating. The winners for this will be declared tomorrow at the valedictory function. So please definitely be there. And right now we'll close for lunch and then we'll reconvene at 2 o'clock. So officially it begins at 2:15. We'll start at 2 o'clock if anybody has to check their laptops, presentations, etc. So right now we can close for lunch. Thank you, everybody. Thank you very much. Hi, Prerna.
Hi, Alok.
Hey.
How are you?
Good, good. How's life?
Life is good.
So what we'll do is from now to 2:15, we'll just give them a chance if anybody wants to test their laptop, etc. And we'll begin exactly at 2:15, and we have to keep the 4:45 time.
Yeah.
So I'll just introduce you when it's time, and then you can take over. I don't know.
Yeah.
Anjana,
Are all of them doing live talks or anybody has a recorded talk?
no, I think all of them are doing live talks. I have not gotten any requests for requests here. All are live talks. Yeah.
Okay, sounds good.
Hi, Prerna.
Hi. How are you?
I'm good. Thank you for being the session chair.
Yeah, we got lucky. So mid-semester exam, my class was not there, so I could just.
You're taking a full course this time?
No, actually, I'm helping Krish with a large course.
I see.
It's an undergraduate course with 122 students.
I see. Only online.
Yeah, online. That's right.
Okay. Nice. So yeah, so this meeting has been going on good so far.
Okay, yeah, I had planned to log in before, but just something or the other.
This session is the most relevant, I mean, most interesting.
Yeah.
Yeah. Okay.
Cool. Yeah, so it's 30 minutes for each speaker. So I will give a warning at 20 and then give an absolute halt at 25.
So it's 20 minutes talk and 10 minutes for question answer. If somebody goes into the question answer, then there will be lesser time for discussion.
Right. So it's 20 plus 10 basically.
20 plus
10. Okay.
Is there anybody here for this session who wants to give it a shot right now before the session really begins? Anjana.
Hi. Yeah. So I was. Hi, Anjana here. Nice to meet you guys online. So can I briefly check my slides and make sure everything is okay?
Yeah. Sure.
And sorry if I'm coughing along the way. It's not COVID. It's some sort of allergy that has turned up in this weird
I know.
Bangalore weather is
It's all over Bangalore right now. Yeah.
Yeah. So anyway, yeah, I'm going to just share and make sure everything is okay. Right. Just going to go to one movie and make sure the movie is fine as well.
So Anjana dropped off, is it?
Yeah, I was wondering what happened. Yeah.
I think she dropped off.
Okay, connection. Where is she right now?
I think she's at NCPS in her office. That's what it looked like. If she doesn't come back in a couple of minutes, we'll give her a call.
Mm-hmm. So are you teaching this semester, Alok?
Actually, I was teaching fluid mechanics, and I just got done with my portion. I already teach half of the PG fluid mechanics.
Mm.
I'm hoping next semester the solid mechanics class I again get to teach in the real chalk and board.
It seems like, प्राचीन काल में हम ऐसे पढ़ाया करते थे.
Even I zone out when I'm teaching. It's so difficult to imagine a set of students and then record. It's really difficult. I hope this doesn't go on for long enough. Anyway, the vaccine seems to be in sight. Multiple vaccines seem to be in sight. So, are you teaching that same course? Are you going to teach? Which course are you teaching? UG as well?
So I was helping Krish with UP201 this semester, which is a modern physics course. And then next semester I will teach UP204 thermodynamics and statistical mechanics.
Hey, sorry, I don't know why, but something happened. I got kicked out. Let me start again. And hopefully I don't vanish anywhere. Hold on. Okay, let's hope this works. Can you all see the screen?
Yeah.
Okay, great. I'm just going to go through a few slides up to the first movie just to make sure that is fine. Okay, I think this is okay. Let me end and hope that I don't get kicked out again. Okay, I think this looks fine. Thank you.
Yeah, it does look good. No problem. Yeah. Anjana, you are at NCBS right now, right?
Yes, I'm at NCBS at the moment. Yeah.
Have your lab started?
Well, at 50% capacity. So we're running at we're running in the shift system. So half the lab comes in for 1 week and then the other half comes for the other week.
Okay.
And no overlap. But I guess it's okay. At least we're able to do some work, which I'm grateful for.
Right.
But it's been a really strange time, to be honest. How is it for you? Yeah.
Many of our students have started, I think.
Okay.
Prerna, your lab started?
Yeah, so we started like gradually. So in June, I had one student. Then because all of them had been sent home, right? So they were slowly coming back in. So by October, I had everybody back. And now it is like, so I have 5 students, and at any point of time, 2 are there in the lab. The other 3 are in the sitting room. So, yeah. So how long have you been at NCBS?
I finished my 4th year officially. Actually, today is my 4th year anniversary. Wow.
Oh, wow.
I did not know 4th December.
So we are not that apart. I mean, I joined 2 years before you. I finished.
Okay. Time goes too quickly, I want to say I just started, but it's 4 years already. Yeah. And this year, I don't know, to be honest, has gone by faster than I would have ever hoped for.
Yeah, I think this year just slipped out of our hands.
Yeah.
Yeah.
Hello,
I
everybody.
see Sunita there. Hey, Sunita.
Hi. Hi, Sunita. Hi. Hi, Prerna.
Hi.
Sunita, you've checked your system, right? So you don't need to check.
Yeah, I think I checked it last in the dry run.
Right. Shobna is there, I think.
Hi.
Hi, Shobna.
Hi.
Hi.
We did it for you too.
Hi, Sopna. Hi. It seems like this session is full of female faces.
Yes.
It is active matter and girls are
very
active.
Yeah, always active.
They lead the way in being active. So Shobna, you've tested your slides?
Yeah, I tested it on the dry run day before yesterday. But do you want me to test it now as well?
No, I think it's fine if you just done that. So it's 20 plus 10.
Yeah.
Yeah.
I think Shubhashish is here also. Shubhashish, you have joined us?
Yes. Yeah. Sorry, I was in quarantine, so I have some symptoms. So I was, yeah.
Okay. Sorry about that.
No. Yeah.
Tamal is there?
Yes, I'm here.
Hi, Tamal.
Yeah, hi. Hi, Prerna.
Hi, Tamal.
Hi.
This is just right after lunchtime, usually a difficult time for everybody to get together.
No, this is all right. I mean, nowadays I eat my lunch in my office itself.
Okay.
How are you doing, Shubhashish? Hi.
Yeah, I'm doing good. I have some symptoms, so I'm in quarantine. So.
Oh,
yeah.
you have symptoms. Did you get tested?
Yeah, I just tested now.
Okay, so you'll get the report in.
I was not present in the meeting. Yeah.
I think it's just time, so we can start. What I'll do is, first and foremost, I'll introduce and invite the session chair for today, which is Dr. Prerna Sharma. She asked me to keep it very simple. She just said to introduce her as an assistant professor at IIT Bangalore. She's in the Department of Physics, and she works in biofluids. And I think she has been part of the previous SMYM meetings. So I think she's the perfect session chair for this. So I'd like to welcome Prerna to start the session.
Thank you. So I won't take much time. I would invite Dr. Anjana Badrinarayan to tell us about homology. Anjana, you can go ahead and share the slides.
Great, thank you. Can everyone see me?
Yes, we can see you.
Okay, great. And hear me clearly, right?
Yes.
Okay, fantastic. So, and can you see my presentation? Not yet, right? Okay, yeah, that's where the problem was. Okay, now is that working? Okay, great.
Yeah, it's working.
Okay. Okay, so let me start by thanking Alok, Sushmita, and everyone else for putting together this meeting. And I feel like a little bit of an outsider, well, actually a complete outsider, because I'm not a physicist by training at all. My lab is a biology lab, but we use a lot of quantitative approaches to understanding biological phenomenon. And many a times, organically, our work leads to some very fun and exciting collaborations with physicists who can understand our data and our approaches in a more basic principles manner. And towards the end of this presentation, also I will maybe in just a few seconds touch upon an active collaboration on this project with Madan Rao's group here at NCBS. Right. So let me get started on the question. Always to sort of orient us into what the problem is, I start with this slide. What you're seeing here is a lysed cell of E. coli with the DNA out in gray. And sorry, can I just ask, can you see my pointer? Like I'm moving my pointer around.
Yes.
Is that visible? Okay, great. Perfect. Thank you. Yeah. So the DNA out in gray, right? And this DNA is, 1,000-fold compacted to fit inside a living cell. And this DNA is not just highly compacted, it's also very well organized. So each individual locus of the DNA takes up a specific position inside the cell. Now, for the faithful propagation of life, you don't just need that DNA gets duplicated and segregated to give you two daughter cells with complete genetic information. You also need to preserve genomic integrity. And cells, across domains of life, from bacteria to human cells, they face a constant threat of DNA damage by both external and internal environments. Sometimes the process of life itself is filled with damage because you produce reactive oxygen species as a consequence of metabolism, and that can cause problems to genomic integrity. So, you have several types of DNA damaging agents that can all break DNA. And if damage is incorrectly repaired or unrepaired, it can lead to mutations, loss of genetic information, genomic rearrangements, and finally cell death. So cells in all domains of life, they have mechanisms to fix DNA damage. So what I'm showing you here is a very simple example of a damage in this triangular orange triangle. And cells across domains of life have two methods by which they correct for this error. One method is error-free, and it requires the presence of a duplicate intact copy of the chromosome that is used as a template for repair. And the other is an error-prone mechanism that causes a mutation during the process of fixing. And so cells essentially toggle between these two states of error-free and error-prone repair to also play around with the ability to sample more mutagenic sequence space to allow for cells to maybe get fitness advantages in stressful environments. So in fact, these togglings between error-free and error-prone repair lead to mutagenesis and enhance adaptation and evolution under stressful growth. For example, in antibiotic resistance development. And this toggling is also a basis for cancer propagation in cells. So in my lab, we are interested in trying to understand how cells choose between these two pathways of repair, the error-free and the error-prone pathway, and how the error-free and error-prone pathways are regulated. And we take a quantitative live cell imaging approach to this problem so we can look inside the cell. And I'll highlight to you why this is important. So a very fundamental or a very common form of DNA damage is a double strand break where both ends of your DNA get broken, both strands of your DNA get broken. Now, the best way of repairing this is via a process called homologous recombination. Recombination requires the presence of an intact duplex copy of DNA, so your second copy of the chromosome present in the cell for repair. And this process, in fact, has been studied since the 1960s in great detail biochemically. We know that the first steps of repair require end resection or the degradation of DNA around the break site, followed by a process of strand invasion where the broken piece of DNA pairs with its homologous partner and then conducts repair. Now this stick drawing is quite easy to visualize, but harder in the cell, because in the cell your chromosomes are not lined up right next to each other in this manner, and even if they are, your broken piece of DNA need not necessarily match perfectly with its homologous partner. So invariably what ends up happening is that you have a broken piece of DNA, say on one end of the cell, which needs to find its homologous partner all the way at the other end of the cell, sampling approximately 8 to 9 megabases of DNA in bacteria, for example. So again, to just sort of highlight the problem, I'm showing you here an E. coli cell, a bacterial cell in white, with the DNA marked in green. And so an example is where you get a break at one end of your chromosome, and a homologous partner is present at the opposite end. And so your broken piece of DNA, so this red bit, has to traverse across the whole cell volume, searching for the right partner. And so the question that is unanswerable in vitro is how a broken piece of DNA finds its homologous partner. Now, if you were to invoke random search as a mechanism for this to occur, modeling and theory suggests that it can take anywhere between 30 hours to even 3 days for a single break in the bacterial cell to find a partner to do high fidelity repair with. But we know inside the cell, this process is rarely error prone. So no matter what happens, 98% of times, the broken piece of DNA will find the right partner. And this happens within a matter of few minutes, not a few hours. It happens no later than 50 to 60 minutes after the break forms. And the search process itself, as I'll show you today, can happen within even 5 minutes of the break being formed in the cell. So this is what we wanted to try and address. We want to try and address how the broken piece of DNA finds its homologous partner. And we use this bacterium Colobacter crescentus to try and address this question. Now, Colobacter has a very well-defined cell cycle and a very well-defined chromosome architecture with certain pieces of the chromosome, such as this origin I'm showing you in purple, anchored to cell poles. And so we know how the chromosome is organized in this bacterium. And so we can make double strand breaks or these damages at any position we want on the chromosome, and then observe the process of search and homologous recombination in living cells. So we do this by using a genetic trick, to isolate these type of cells with 2 chromosomes. So these black circles, these inner black circles are chromosomes. And what we do is we take these types of cells, these pre-divisional cells, with 2 completely replicated chromosomes, and then we induce a break on them. So we do the induction of the break via using an ISC1 site. This is a double strand, this is a restriction site that is recognized by an enzyme called ISC1. So it binds the break site and cuts the DNA, giving you a double strand break. And we can visualize the dynamics of the break site itself via a marker that's going to bind right next to it. And so we can make a single break at some frequency and observe how this break is going to traverse to its homologous partner for repair, and then go back again after repair is completed. So this is a movie showing you that example. So you get a break at this end of the cell, the break site traverses to find the partner, and then it goes back again after repair is completed. So we can quantitate this quite nicely and have 2 clear events of DNA damage, double strand break repair. The first event of repair is pairing. So what you're seeing here is a chymograph, which you'll see quite often now through the course of this talk. The high intensity shows you essentially these localizations at the poles. A break gets induced at one of these loci, so that's the break right here. And when a break gets induced, you see loss of localization of that fluorescence marker at that pole. You see an increased fluorescence here. And then after repair is completed, you get the 2 loci split again, which says that now the broken piece of DNA has been fixed, and now you can get resegregation. And so in some work that I had done previously in my postdoc lab, I was able to establish this sort of a system to study double strand break repair and show that when you induce a single break on the chromosome, we can observe the break site move all the way to the other end of the chromosome where you have your homologous partner, do repair, and then go back again. So we can now see all the events of break repair inside the cell with clarity. However, the important question of how this broken piece of DNA even got to the other side is not answered as yet. And for this, what I'm going to do is introduce to you an important molecular player that is essential for this mobility to occur. So when a break gets induced, it gets degraded by a helicase nuclease complex at AB. The DNA starts to get resected. So the DNA is removed from around the break site by this protein until it recognizes a specific sequence on the DNA, at which point it switches to degrading only 1 strand of DNA instead of 2. So now you're going to have single-stranded DNA, this little loop that you're seeing here, revealed, on which a recombinase, REC-A or RAD51 in eukaryotic cells binds and conducts the process of homologous recombination. But we really don't know how this filament orchestrates homology search, right? And so in the past, this filament has been imaged in E. coli and has been shown to form these long structures inside the cell. But again, how these long structures can even do homology search has not been addressed before. So what I'm going to do today in the next few minutes is show you that REC-A alone, this filament alone, is insufficient to do homology search. And it's actually a two-component system. REC-A along with a structural maintenance of chromosome protein REC-N that triggers the large-scale translocation of a nucleoprotein filament inside the cell, allowing homology search to occur. And I'm going to propose to you a mechanism by which this large-scale movement is triggered that then facilitates the ability for repair to occur. And this is the work done by a graduate student in my lab, Afroz Chimtanawala. Right, so what we did was we took our Colobacter system that I've described to you already, and we did this experiment in two conditions. We did it in one condition, like these three-divisional cells, as I had told you, which have 2 chromosomes. And so if we make a break on one chromosome, you will get repair. So we can study both search and repair. We also have a genetic trick to isolate cells with just a single chromosome. And that's great because now you can ask, what is the influence of the partner on the mobility of the break site? And so we can really just investigate homology search alone without repair occurring. And so I'll show you some examples of dynamics from both of these systems. And what I'm really going to focus on is the dynamics of this nucleoprotein, REC-A nucleoprotein filament. But we've tagged REC-A here with a YFP, so we can track it in live in cells. And we use 2 main metrics for studying the nucleoprotein filament dynamics. We study the relative position of the centroid of the filament inside the cell over time. And these are the graphs I'm going to show you a lot of. I'm going to show you some of these fraction cell length occupied graphs also, which essentially tell you how long the filament is and how dynamic its architecture might be through the course of a search process. Right, so the first thing Afroz did was to take these pre-divisional cells and induce a site-specific break. So the break occurs now on this pole. REC-A will localize and form an intensity that is visualizable by us and also for analysis. Only when a break is induced. And once a break is induced, we then follow REC-A dynamics over time to see how it moves inside the cell. Now, just to sort of orient you as to why this type of imaging is important, is that in the past, search has always been thought to be a random process, almost like how a transcription factor tries to find its promoter site. And the expectation then would be that REC-A, the filament, should also move in a random manner inside the cell. But what Afroz observes at short time scale imaging, when she images every 30 seconds to 1 minute after a break, we find that REC-A does not move in a random manner. In fact, the break is not randomly searching inside the cell. It takes a very directional move from the break site to the opposite pole, and it undergoes several iterations of this cycling. So it gets to the opposite pole, goes back again, and then goes up again, and keeps doing this cyclical translocation across the length of the cell until finally the partner is found. And so this is a chymographic example of this iterative search that I'm telling you about. The break is here. It starts at one cell pole. REC-A is this high intensity filament that you're seeing in this chymograph. And so you can track the filament dynamics going from one cell or going from one side of the cell all the way to the other pole, turning back again, and then going again and turning back again. And so it goes through these several iterative cycles till it finally finds the partner. So we can do this analysis for several hundred cells and see what the average movement over time is, along with the standard deviation in blue. And this really just again reiterates that search is going in a directional manner. The filament is translocating in a directional manner. And from this, we can also extract some features of the search kinetics. We can ask, is there a cell length dependency to how long it takes to get from one pole to the other? And we almost immediately see that there's no cell length dependency. You can take really short time scales to get to the opposite pole, or you can take a really long time, and it's not dependent really on the cell length. We can also ask, how long does it take to finally find your homologous partner? So how often do you go up and down till you finally stop and do repair? And we find that you take approximately 6 to 8 cycles from one pole to the other until you finally find your partner and then stop for repair. So from this, we then ask the question, okay, the filament is moving in a directional manner. Is the filament moving as a single entity, or is it undergoing dynamic reorganization during the process? And so we analyze the various types of architectures we can see of the filament inside the cell. And this is just to highlight to you that the filament is really dynamic in nature, and there's really no predictability as to what type of a localization it is going to take up during the course of the cycling in the cell. You can see it go from anything from this sort of loop-like structure to an elongated rod to even very discrete localization, during the course of a homology search cycle. So from this, we can build a really nice sort of time scale for how repair is occurring inside the cell. The first step, obviously, is once a break has formed, which is the star shown here, you get the loading of the Recce monomers on the DNA. The Recce then begins to grow and does the part of homology search, looking for the homologous partner, which is this other red dot on the other side. Till finally you lose the Recce localization, which essentially means that you have found your partner and you've stopped searching, and then you get repair. Now you get 2 instead of 1 blob again. Right, so now one can ask the question, does this directional movement we observe depend on the fact that there is a partner on the other side? Or is search independent of knowing whether you even have the ability to do repair? And so for this, we turn to the swarmer cells, these cells with a single chromosome I had told you about. And we asked whether if you now induce a break in these cells, would you still see search occurring? And you see search occurring. In fact, Recce still does the same thing. It goes from one pole to the other, searching for its homologous partner, even though there is no partner anymore. It's a bit heartbreaking, actually, because in this case, it just keeps searching. It keeps going up and down till as long as you can image it. So here you can see that repair does not occur, but search will happen, similar to what we saw in the case of a cell with the homologous partner present as well. Right, so what I've shown you so far is this very dynamic picture of homology search, except that search is not random anymore. We think that search is a directional process where a nucleoprotein filament that has nucleated at the break site begins to grow and then travels across the length of the cell to find a homologous partner, at which point it disintegrates and then repair occurs. And during this process, the filament itself is quite dynamic in nature and undergoes dynamic remodeling during the search process. So now, obviously, the question is, what is the mechanism of triggering this translocation? Is there a motor? Is there a motor that's driving the nucleoprotein filament to move in the cell? So we know about a motor like this. In fact, recent work in the community of chromosome dynamics has revealed a rather beautiful mechanism for motor-like behavior for the structural maintenance of chromosome family of proteins. These proteins can bind DNA, and via their ATPase activity, so binding and hydrolysis of their ATPase cycle, can trigger translocation of DNA via mechanisms by which extrusion of loops of DNA occurs inside the cell. This is a really beautiful recent example of loop extrusion occurring from Mahipal Ganji's work while he was with CSTECA. Now he's at IISc, actually. And so he really beautifully showed the ability for cells to extrude, for SMC proteins to extrude DNA as a loop via using their ATPase cycle as a motor for extrusion. So we then asked, could it be that an SMC protein is also involved in the repair process, allowing the nucleoprotein filament to basically move in the cell? And so there is an SMC protein also present for repair specifically in bacteria, and this protein is called RECN. It has a characteristic architecture that you would see for all structural maintenance of chromosome family proteins, along with the characteristic ATP binding and hydrolysis ability. In the past, it has been sort of implicated in doing some form of double-strand break repair with Recce, the protein I've shown you previously. But its exact mechanism in triggering break repair via Recce is not known. And so we decided to ask, could it be that RECN is the motor that is allowing the translocation of the filament to occur? Now,
Anjana, 20 minutes are over. And
okay, I'm going to rush really quickly then.
Sure.
Sorry, I did not realize that. Thank you for letting me know. I'm going to quickly skip on this part and tell you that we found that RECN interacts with Recce. And so we asked, is RECN essential for the mobility? And lo and behold, RECN is essential for the mobility. if you don't see, if you don't have RECAN in the cell, you don't see any movement at all. The filament just ceases to go from one pole to the other. And so this is just to reiterate that same thing again. You saw this nice systematic movement from pole to pole, but in a RECAN deletion, you don't see it. However, the growth of the filament itself is not so perturbed. And I'll just quickly show you some data to show that RECAN does not perturb the growth of the filament. So in fact, we asked these three questions. Is it affecting the rates of loading? Is it affecting the association with DNA, or is it affecting really just the translocation? To see loading, we asked how quickly does the nucleoprotein filament begin to form once a break site a break is made. And we found that the rates of loading are similar between wild type and the absence of RECAN. We also then asked how quickly does it grow once it has loaded in the presence or absence of RECAN. And you see that the rate at which it grows as well is similar in both categories. It's just that in the absence of RECAN, you don't get movement, but in the presence of RECAN, you get movement. So we rule out the ability, the perturbation of loading rates. So then we asked, is it affecting the stability of the RECA filament on DNA? And for that, we took two approaches. We asked whether RECA is unable to displace the single strand binding protein that marks the DNA, the single stranded DNA in the cell. And we find that it's not perturbing the stability of the RECA filament. Another nice way of looking at RECA filament stability is to look at the loss of DNA around the break site. In the absence of RECA, you get extensive loss of DNA around the break site as seen from sequencing experiments. However, if you remove this RECAN translocase, you don't see the loss of DNA around the break site. You actually get DNA present just like you see in wild type. So again, we really rule out the problem of RECA filament stability or loading, pointing us to the idea that maybe it's affecting the translocation of DNA. So one way, there are two hypotheses, right? One is that RECA loads on a stiff rod, and then RECA grows on the stiff rod. Another possibility is that it is RECA and DNA together that are translocated by RECAN. And so we can actually test this by looking at where the DNA itself is. If it were a stiff rod, then you would see DNA present all around the cell in the presence or absence of RECAN. But we don't see that. In the absence of RECAN, the DNA is crunched up on one cell pole, similar to what you see for RECA. But however, in wild type case, the DNA can move anywhere in the cell, and this is really getting triggered by RECAN. So we think that what is happening is that RECAN is triggering the translocation of the nucleoprotein filament. And so this brings me to the model that we have right now. We think that the mechanism of homology search in vivo is actually triggered by this directional translocation of a very dynamic RECA nucleoprotein structure. And this nucleoprotein filament structure is toggled or is affected by the presence of RECAN, which I'm showing you here in blue. And this could be occurring via two things, either dynamic exchange or nucleofilament loop extrusion. One way in which we can ask whether it is extrusion and not dynamic exchange is to perturb the ADPase cycle of RECAN and ask what happens to the movement of the filament, which ceases when we perturb this ADPase cycle, but also what happens to the lengths of the filament. And what's exciting is that when you don't have the ability for RECAN to release DNA after binding, you get very tight filaments, almost similar to the structure here, where when you cannot release a DNA due to an ATP binding mutant, this mutant here, you scrunch up DNA. And so you also see very, very tight localizations of the RECA nucleoprotein filament. Right, so this essentially brings me to the end of my talk, where what we think is going on is this dynamic remodeling of the RECA nucleoprotein filament by RECAN that triggers directional homology search. And this allows iterative search at every step along the way in the cell. So every time RECA moves, it can search the blue DNA shown here in a sort of a multiplex manner, speeding up the search process. It allows you to sample local areas before going to long distances, and it's not limited by the amount of template you've made for the search process to occur. And in general, what we are working on is a theory on the idea of symmetry breaking with Madan Rao's group, because it seems like what is fundamental to what we are seeing is the ability of this SMC protein RECAN to break the symmetry of the RECA nucleoprotein filament. And this seems to be a really universal function of SMC proteins, independent of what they're doing in chromosome dynamics. And we're really excited about exploring this idea further in the future. Right. So with that, I'll stop. I'll thank Afroz and all the other people involved, funding agencies, and I'm happy to take questions if there's time. Sorry for going over time.
We have about 5 minutes. So
okay, great.
Yeah. So I'll set the ball rolling because
Sure.
So is there a way to see this in some kind of in vitro assay with purified proteins?
Yeah, so we are going to go towards that now and look at whether we can look at specific aspects of the nucleoprotein filament in vitro in the presence or absence of RECN. For example, filament stability would be something to measure in vitro. The one thing to sort of reiterate about the in vivo system is that in an in vitro system, you cannot possibly reconstitute from beginning to end the entire reaction. We will have to pick and choose which part to do. And so the power of the in vivo system really is that we are able to see the whole thing occur. But we are going towards, looking at filament stability, exchange rates, ADPase rates, etc. in vitro now.
Right. Yeah, thanks.
I have a question, Anjana. Can you hear me? It's Shobna here.
I can hear you.
Yeah, I have 2 questions actually.
Sure.
The first question is this RECN. So you said that REC A and RECN are interacting. Is there any other protein you have found or you think is also involved? Because probably there are many proteins that are involved in this process.
Yeah, so I mean, at the moment, we don't know whether there are other interacting players for RECN. It is an SMC protein which is known to have multiple partners that regulate its own ATPase cycle.
Right.
But RECN in the past, people have tried to see if it interacts with other things and they have not found anything else. We know that the phenomenon we are seeing is really solely dependent on RECN alone. If you remove any other aspects of any other break repair proteins through this schematic I've shown you here, you don't perturb mobility unless you remove RECN. So we do think it may be as simple as a 2-component system with RECN driving either instability of the REC filament or driving extrusion of the REC filament.
Okay, so someone has done some kind of siRNA screen or something. Okay.
We've done pull downs. Yeah.
Okay.
Yeah.
Then just out of curiosity, the other question is, does the sequence of the DNA impact the RECN and REC-A dynamics? I mean, I'm just curious.
No, that's a nice question, right? I mean, finally, if you think about it, it has to be able to recognize sequence somehow. REC-A by itself does not recognize DNA sequences when it's binding. It can bind any substrate that is provided for it to bind to, any double-strand break substrate. We do think that there is some influence of the second chromosome. I didn't go into this in great detail, but it's possible that chromosome organization itself plays a role because based on how compacted or decondensed you are, you can speed up the search process. But that doesn't seem to be sequence dependent. It's more sort of generic and to do with chromosome compaction itself.
Okay. Great.
Yeah.
Thanks.
Hi, Anjana. It's Tamal here from TF. Yeah. So I have one question. So what is driving the directional motion of RECN?
What is driving the directional motion of RECN? Okay, yeah. So that is like the key question, right? So how does if RECN drives REC-A's directional motion, what drives RECN? Well, this is where we do think it is the ADPase cycle of RECN. So we have evidence to suggest that RECN actually localizes several times at the base of the filament. So it's not co-localizing with the entire REC-A filament. It's actually just localizing at bases of the filament. So it's possible that the only way RECN can actually associate with DNA is via binding nucleoprotein filament itself. So it is dependent on this filament forming, but once it binds it doesn't bind the whole thing, it just binds an end. So it's possible it anchors at the end of the filament and it's just pumps the rest out. And that's what allows some directionality to occur. And it just then follows wherever its substrate has gone. And so every time, say, for example, from here, when REC-A transitions here, RECN will turn up at this base and then pump again. And so it's likely that it's just tracking the REC-A filament as it moves. Which is why it's in some ways I feel it's a bit cute because you're not dependent on any other anchoring system because one is dependent on the other. And so as long as A moves, N moves, and N will trigger the movement of A itself.
Okay.
Yeah.
Thanks.
Okay. So our time is up. Thank you for the wonderful talk, Anjana.
Thank you,
And I will invite now Shoguna to tell us about membrane mechanics.
Okay. So I guess the screen is visible now.
Yes. Go
okay.
ahead.
Yeah. So first of all, I thank all the organizer for giving me the opportunity to talk about our work, and I hope to keep up the high standards of talks that were that have been set by all the previous speakers of yesterday and today. As the title of my talk suggests, the kind of soft matter that we or our lab works on are membrane bilayers composed of composed of lipid biomolecules, which are amphiphilic biomolecules that entropically driven in an entropically driven fashion, they self-assemble to form phospholipid bilayers, and these bilayers are ubiquitously found in all membranous organisms. So let me give you a detail of why we are interested in these lipids and membranes. So as I said, that they basically are found in, as a part of compartmentalizing various organelles of all membranous organisms, including our mammalian cells. However, as shown on the screen, the bilayer is not as simple as it looks, but rather, if you look at this super resolution image of a cell membrane or plasma membrane, it shows you these kind of hills that are present of variable sizes. So these actually are lipid domains induced by lipid clustering. And these lipid clusters are basically regions of, lipid membranes that are very compact and have very low polarity because of very low water dynamics around these. And this lipid clustering or domain formation is actually one of the defining features of plasma membrane. And why is it important is because these actually regions act as, kind of platforms for kind of sequestering membrane proteins that enables, let's say, the communication of the outside world with the inside world in the form of, for example, signaling that regulates a lot of processes. And not only that, these lipid membranes or these different nanoclusters or domains, they also affect activity of proteins that are embedded in these. In addition, they in context of our work, they are very much important players, as they provide cues for these pathogens to bind to the host cell for during the course of infection. So the logic that we had was that any agent or any phenomenon that can kind of disorganize this lipid domain or bilayer organization will have an impact on cellular function. So that was basically the logic or rationale that we started with. And that brings me to the gist of the kind of lipids that we work with. So in our case, these lipids are derived from Mycobacterium tuberculosis, which is the agent that causes TB. And what you see here on the screen is a very complex lipid membrane structure of this organism. And of most important to us are the lipids that are present here in the outermost layer, which are also known as free lipids. And in fact, there is a notion that these lipids are secreted during the course of the infection, and they then interact or prime the target cell or the host cell in which it causes infection. And basically, our lab is interested in understanding the molecular details of their crosstalk with the host cell plasma membrane or membrane, which is the first point of contact when the bacteria reaches the cell for causing some kind of infection. So the first thing that we had to do was we had to design some kind of an infection model. So what we do is that we work with purified lipids from this organism. And I show you structure of one of the lipid, which is quite distinct compared to mammalian phospholipids that we have in our body. For example, it has a sulfated trehalose head group, and it has excessive methyl branches and very long acyl chains of the order of about 60 to 70 carbon atoms, which is very long compared to almost maximum 20 carbon atoms that we have in our lipidome. Then what basically the study goes like, we have our target cell or a host cell, and we kind of expose these cells to the purified lipid suspension, and we follow their interaction with the first point of contact, which is the plasma membrane, and ask the following questions: whether this interaction brings about any changes in membrane organization or dynamics, and whether there is some kind of functional significance or implication associated with it. So first things first, we did some kind of mass analysis as well as TLC to confirm that these cells which are treated with these lipids, when you extract these lipids and run them on a TLC, you can actually find the presence of these signature lipids in these mammalian cells compared to the purified control lipid, which suggests that these lipids indeed do insert into the plasma membrane of the host cell, propelled by their hydrophilic or lipidic nature. Then what we asked was whether there is some kind of reorganization of these domains that I had shown in my previous slide, the lipid nanodomains or clusters. So in order to map that in live conditions, what we do is we use a method known as Laudin generalized polarization microscopy, wherein we work with this Laudin dye, which is a solvochromic dye. So its amphiphilic nature, makes it partition at the lipid membrane. However, depending upon the environment of this dye, it can show solvochromic shifts. For example, when the dye is partitioned in a very tightly packed environment, similar to those that are found in those ordered low polarity domains I had talked about, then it exhibits a very low wavelength emission. Whereas when the environment of the dye is more fluid or more water is around it, high polarity region, then the dye exhibits about a redshift in its emission. So using a ratiometric, imaging of this dye's emission properties, one can calculate this generalized polarization parameter. And what you see here is basically a pseudo-colored GP image of live THP1 cell. So these are THP1 macrophages, which was one of the most extensively used model for tubercular research. And this is not a conventional fluorescent microscope image, but rather each and every pixel of this image gives you a value of GP, which varies theoretically from -1 to +1. Wherein low negative values basically tell you that the membrane or the environment of this Laudin dye is similar to as shown here, which is very fluid and ordered or high polarity. Whereas the large positive values indicate that the dye is sensing an environment which is very compact and low polarity or very ordered. And what we could instantaneously see on the surface of these live cells was that there is some kind of lipid nanoclustering, which is in accordance with published reports and the notion that the plasma membrane of cells are not very homogeneous, but rather they have some kind of these domains which act as signaling platforms. And in addition to seeing them, we could also quantify their distribution by plotting the GP values as a function of the, in the form of a histogram. And we could see at least 2 distinct populations. Of course, there are more, but experimentally we could validate or at least quantify 2 of them. The next thing what we did was we actually incubated these control cells with the mycobacterial sulfoglycolipid 1. And what you can see here is that the red orange regions which were present in these control cells are no longer visible in these treated cells. In fact, we see some kind of a phase demixing on the surface, and there is a fluidization because most of the GP values shift to low negative values, suggesting that there is a disordering of the membrane by this mycobacterial lipid insertion in the host cell, and there is a remodeling of the lipid domains. Of course, the functional significance of that remains to be studied. Then we actually quantified it not only in terms of image, but what we could see is one of the population, which is the high GP population or more ordered domains on the cell surface, were actually decreasing in a concentration dependent manner. And the take home message from this work was that yes, the host cell membrane organization is remodeled by at least one of the mycobacterial glycolipid SL1. Up till now, the results of this 2-photon microscopy that I showed you were also, including the results of internal membranes because the dye can internalize. So what we did was that we performed another experiment using the same method, but using now some kind of image segmentation algorithms, where we can only specifically look at the plasma membrane pixels. And we could confirm that yes, indeed, the mycobacterial glycolipid, kind of disorders the plasma membrane, in addition to showing a global effect on all internal membranes as well. Then what we did was we asked the question whether this effect that we see is selective for sulfur glycolipid or other lipids of mycobacterial origin, which are also secreted from this outermost layer, but are structurally different, also have similar influence, or whether it's something, selective process. We were actually quite lucky and happy to find that not all mycobacterial glycolipids elicit a similar membrane reorganization phenomena, but what we see was very specific to sulfur glycolipid, but not to other lipids, clearly suggesting that the lipid structure has a role to play in this membrane reorganization that we see. Then what we asked was, in addition to organization, is the dynamics of the membrane also affected? So for that, we decided to measure the diffusion of plasma membrane components using two reporting dyes. One which is in green, that is basically having saturated lipid chain. So it prefers to go into the more ordered regions of the plasma membrane. And the dye which has two unsaturated or double bonds, which is the rhodamine DHP, it basically partitions in the disordered regions of the membrane. And using both these as the probe or indicator dyes, we wanted to basically see whether the diffusion of these components in the membrane is being affected by adding mycobacterial glycolipids. So what we did was we performed the FRAP experiments as a function of time with different, structurally different glycolipids. And to cut the, make the story short, what we could see is that whereas some lipids do not affect the diffusion of both the ordered and the disordered domains, some lipids increase the diffusion coefficient irrespective of whether these are ordered or disordered domains of the plasma membrane, and some of the lipids selectively affect the dynamics of one of the plasma membrane regions. So clearly, these structurally distinct lipids not only kind of disorganize the lateral organization of the plasma membrane, but also affects the dynamics of plasma membrane components. Next, what we did was we basically wanted to study whether these dynamics and organization is also affecting the mechanics of these membranes. So we used atomic force microscopy. And what we did was we basically took our live cells, treated or untreated. We brought a AFM cantilever close to the surface of the cell to indent them, to measure force as a function of distance, as shown by the black curve. And by fitting this curve, we can calculate parameters of elastic modulus. And what we could see was addition of these lipids, it decreases the stiffness of these cells, suggesting that there is some kind of a softening, which if you put it in context of host pathogen interaction is kind of makes sense, because let's say a pathogen is coming near its site of infection, it releases these lipids which prime the target cell to become soft so that the pathogen entry can be facilitated. Next to that, what we did was, again, using the same method, we looked at tethers, which are thin nanotubes that basically, are seen during the retraction phase of the experiment. That is, when you come close or indent, you basically measure the elastic modulus. But when you start moving away from the cell, then these thin nanotubes are formed between the AFM tip and the cell membrane. And these actually, occur as or can be seen as events of constant force as a function of force and distance or extension curve. And the parameters you can get out of it is the force with which these tethers are attached to the AFM tip, the number, as well as their length. And each of this parameter gives you information about the membrane stiffness as well as their resistance to bending. So using this method, what we found was that SL1 actually requires less force. The tethers requires less force to be extended. The number of these tethers increased, whereas their length was found to decrease. So the premise that is there in the field is that these formation of these membrane tethers is associated with induction of membrane curvature. So we think that there might be a tantalizing possibility that this SL1, because of its very unusual lipid structure, might be able to form such curved membrane regions, kind of dictating the tether dynamics that we experimentally see. Then we actually, extended the study with all the different structural lipids. And without going to the details of the experiment, what I can tell you is that whatever effect we see on their elastic modulus, tether number or tether force actually maps to their structure. For example, these saturated chains in, the lipid PDIM is able to pack very efficiently. So it kind of increases the stiffness that we experimentally observe. Whereas the methyl branches that we see in SL1, they mitigate tight packing. As a result, we see that the stiffness decreases. So using structure function relationships, we could arrive at some kind of guidelines how the different chemical moieties of these lipids could impact lipid-lipid interactions in the bilayer. Then the final thing what we did was we basically asked the question whether this membrane remodeling is, only limited to the plasma membrane, or does the effect percolate to the actin cytoskeleton? So actin is, cytoskeleton is nothing but a network of actin proteins just beneath the plasma membrane that provides a much needed support and form to the cell. And it is also involved in providing forces for processes associated with cell shape, migration, as well as during pathogen uptake. And in fact, it has been shown that pathogen modulates actin network during the course of the infection. So what we did was that we basically monitored the actin morphology and its abundance using confocal macroscopy in the presence of different lipids. The first thing we found was that some of these lipids were actually increasing the volume of actin. Why? We don't have an answer yet, which we're trying to, understand in our lab right now. But in addition to the total abundance of actin, what we found was that their morphology were also being, redistributed, wherein the actin protein exists in at least 3 different morphologies, either in the form of these dot-like structure, which is puncta, or the form of patches, or there are these filaments that you can see. And this, kind of equilibrium between these 3 morphologies is dynamically changing in the presence of different mycobacterial glycolipids. So with this, I would like to conclude my talk. And altogether, what we can say is that these structurally diverse glycolipids of mycobacteria are able to insert in the plasma membrane of these macrophages target cells, wherein they cause a change in the membrane mechanics, diffusion. They disrupt the actin filaments. What I could not show you is the physical or like the biological significance or functional significance of these perturbations, which actually lead to modulation of autophagy and cytokine signaling in favor of the pathogen. And therefore, we think that this is a previously unknown mechanism, whereas this organism, in addition to proteins, can also use its lipids during the course of infection. And I would like to acknowledge my lab members for their interest and hard work in this project, my institute, my collaborators funding the resources, and you for your kind attention. So thank you.
Thanks, Shabna.
Yeah.
So I'll ask a couple of questions. So do you know what is the role cholesterol plays in this, if any? Like, is the cholesterol of mycobacterium different from what's on human cells?
Okay, so mycobacteria does not have cholesterol.
Okay.
So mostly the bacteria, they acquire the cholesterol from the host. So during what is known in this field is that they basically, these pathogens or mycobacteria, it prefers to bind to regions which are rich in cholesterol.
Okay.
And then they acquire this cholesterol. For our experiments, what we have shown is that these orange colored domains, if you see on the surface of the cells, so these actually, we have done experiments and found that these are actually cholesterol rich. So it's not only the bacteria, intact bacteria, but also its lipids favor to partition into these domains and then try to kind of redistribute cholesterol everywhere.
Right. And you mentioned that you were adding lipids purified from mycobacterium onto the human cells. So was there a concentration dependence to see all that you saw, or like you were dosing at very high concentration?
No. So that's a very good question. So we did observe a concentration dependent effect, and the concentrations, we actually limited ourselves to the physiological concentrations of the lipids that are found on the surface of the bacteria, number one. Second, the concentrations were in the range that is also secreted by the bacteria in the form of its membrane vesicles. So we wanted to be in the physiological range of working with, so they're like few micrograms per ml, the concentrations that we have chosen here.
Okay, okay, thank you.
Hi, Sobna. Hi, Prerna. Can I ask a question?
Yeah, please go ahead. Yeah.
Hi, Sobna. Very nice talk.
Yeah,
I have a question about the FRAP experiment. If you could please go to that slide.
Okay. Yeah.
Yeah, so where you have shown the recovery part. So I was wondering, does the recovery curve that you get also depends on the dye you use, and whether these are in situ samples, I mean the dried samples, or the membrane in the liquid state?
So these are membranes in the liquid state, and these. I mean, if you say the recovery of the dyes, so of course it depends on the dye that you want to use. So if you can see here, this is the kind of N-rhodamine is basically a dye that goes in the more fluid regions of the membrane. So the red curve that you see shows almost 80% recovery. Whereas if you look at this part here, which is the NDD, this dye goes in the ordered regions of the membrane. So the ordered regions of the membrane means it's a very compact, tightly packed parts of the membrane where the dye is not very free to move. So what you see is the recovery is only about 30 to 35% only. And also the diffusion coefficients that you can see is also shown here, that the diffusion coefficient of the dye, which is in a more mobile environment, has a higher diffusion coefficient. And the red is basically the diffusion coefficient of the dye, which is reporting from more rigid environment. So automatically the diffusion coefficient and the mobile fraction is very low.
Okay, thank you.
Any other questions? Please feel free to unmute yourself and ask, or raise a hand, or type questions in the chat.
Prerna, can I ask one?
Yeah, please go ahead.
Hey, hi. Really nice talk. So you showed data where you mentioned that you extracted elastic modulus from the AFM data. I mean, I think because of the interest of time, I think you did not give the details. Can you just touch upon how do you do that?
Okay, so basically what we do is that when you measure this force versus extension curve during the indentation process, you actually, have to fit it to certain kinds of models. So what we do, or at least in the field in cells, people use Hertz model using a conical tip of the AFM tip, and certain parameters that you have to keep into account. And then we basically fix the indentation depth up to which we want to kind of fit the curve, which happens to be around 2 micrometer. And then, by fitting it to a Hertzian model, you can get the values of elastic modulus. I mean, I don't know the equation right now at the top of my hand, but you can basically take this black curve, fit it to appropriate model, whichever you are comfortable with, and then you get the parameters of elastic modulus, which we then plot as a function of, its relative frequency. Yeah.
Okay. Yeah. Thanks. Thanks.
Okay. If there are no further questions, we have plenty of time, by the way. So I don't want to prematurely close. But if there are no further questions, then I would invite the next speaker and thank Shobna for a really exciting talk.
Thank you.
Shubhashish, could you please share your slides, and we look forward to your talk on chaperones.
Can you see my slides?
Yes, we can. Thank you.
Okay, thanks. Okay, so thanks, Swapna. She already introduced force spectroscopy, AFM, so I will continue with that. And thank you so much for inviting me in the nice small conference. So I really like that. And I really would like to acknowledge the uh, people for that. So let's talk about that. So, when we are talking about the force spectroscopy, we already have several techniques available. So Sobna already mentioned about the AFM. We also know that we have optical tweezers. So what our lab is doing is that we are actually developing single molecule tools and trying to understand the biology out of it. So we are working with AFM and optical tweezer, but now we move to the magnetic tweezer, and we called our magnetic tweezer a special magnetic tweezer. We called it covalent magnetic tweezer. Why we call that covalent magnetic tweezer, I will tell you in next few slides. At the beginning, a brief discussion why we moved to covalent magnetic tweezer, whether we have AFM, optical tweezer, or magnetic tweezer. The reason is that AFM and optical tweezer has a issue. So when you try to understand the protein conformation or dynamics in a single molecule level, due to the using of the cantilever by the AFM doesn't resolute steps in the very low force. And for the optical tweezer, it actually works mostly in the low force. In the high force, they actually, the detachment between the bead and the protein occurs. So we need such a technique which can cover from the low force to the high force range. Additionally, with the AFM and optical tweezer, we can see a particular molecule for a few seconds, like 100 seconds, 200 seconds. With the magnetic tweezer, with our development, we can see a particular molecule constantly for 1 month. Now, if you ask me that, what you will see a particular molecule for 1 month, what the new data it will tell you, that actually a different argument, and I have a different answer for that. But the main issue is that it can have a technical advancement of a great stability where you can see a particular molecule for 1 month. You can change solution during the experiment and see all the results in real time. That's why sometimes we call it dynamic single molecule technology. Very briefly, how the technology looks like. So this is the homemade covalent magnetic tweezer. You can see this is a voice coil. This works like a a voice recorder, which actually can change the position of the magnet. Just below that, you can see we have a magnet, and if you may not see very well, but here we have the samples, right? So then this is actually this is how our sample look like. So the sample is stitched with the glass with a halotech chemistry. I will not talk about details, but if you see me, then you can see that the protein is attached like that. This is the attachment of the protein with the glass, and at the top of the protein, it's a small magnet, a tiny magnet. Now, what happens is that we have a larger magnet on the above this. So when I actually decrease the position of the permanent magnet, the force here is actually it actually feel the force here. Now, what we do here is that we have a reference bit, and during the experiment, we actually changes the magnet position. How we are doing that, I will show you in the next slide. So this is a real experiment where you can see that how the magnet is moving. So this is the permanent magnet which is moving, and all my tiny magnet attached with the protein are in this cell where my cursor is right now, and this is a liquid cell. So you can actually try your samples here. And the other part is that you understand that when you decrease the position of the magnet, then the force increased. When you pull the magnet up, the force is decreased, and the force and the magnet positions are calibrated, and we calibrated it with previously with this paper. So now I would like to see you a real data. So I would like to tell you one thing which I didn't tell you before is that here we stitch the protein, and in this case, we don't take one protein, but we basically take the 8 repeats of the same protein. Now, why 8 repeats? Because I wanted to show you how mathematically, correct the instrument is and how precise the instrument is with the step size and the length. So the data is a little bit complicated. So I would like to go very slowly with me. So here you can see that at the below we have the force curve. So at first we have very low force. Then we increase the force at 49 piconewton. You can see it here. Then we decrease the force, keep it at 6 piconewton. Then we keep it for 6 piconewton for some time, then pull it once again, right? So this is my force curve. So now, if you see that how the data looks like, so in the left-hand side, I actually plot the extension. So the point is that when you apply the force, you can see that each and every protein starts to unfold individually. And as they are stochastic process, so you can see each and every step. As we have 8 protein repeats, we can see 8 steps like 1, 2, 3, 4, 5, 6, 7, and 8. Then when we decrease the force, you can see the same thing, that when I decrease the force, again, we can literally count all the 8 steps, right? 1, 2, 3, 4, 5, 6, 7. And here all the proteins, the whole protein becomes refolded. Now, as I keep the force constant, so here we can see that the protein is hopping between the folded and unfolded state. And as 6 piconewton is very low, you see most of the domain of the protein is folded. So here 8 protein is folded. In this stage, 7 protein folded, 1 unfolded. Here again 8 folded. This position again 7 folded, 1 unfolded. And if you see that at the end of the plot, here we have 7 steps. So as we have 7 steps, we actually got 7 steps after the 49 piconewton. So this is the only slide to show you that, how nicely the technique is correlated. So from this green region where the protein is actually folding and unfolding in equilibrium, you can have the idea of delta G, and you can calculate that by calculating folding probability. Now, if you see the graph carefully, you see that one single graph can actually give us a lot of information, right? So if you plot this one properly and if you fit it, you can get unfolding kinetics, where my cursor is right now. If you fit this one correctly, you can get it refolding kinetics. Here you can get the equilibrium information, and this conformational, these changes from the steps, you can get the change in the conformation, right? So from a single graph, you get kinetics, unfolding kinetics, refolding kinetics, equilibrium. And if you see the time scale, that previously where we can see one particular molecule for a few seconds, now we can definitely see it for 500 seconds, but we can go up to, a few hours. Okay, so now what we did, we actually add a microfluidics chamber with the same covalent magnetic tweezer. And what we found out that now not only we can monitor all the molecular properties, but also we can monitor that how much change is happening when you are actually introduce a new thing. So if someone is interested in protein drug interaction, he can introduce drug. If someone interested chaperone, he can introduce chaperone. If someone interested about all the cholesterol, all the salt, DNA, you can actually put it and then exactly monitor that what exact the thermodynamic and kinetic parameters changed in the with your respective interest. So we think that this has a huge applications. So this is a real data which actually showed you that how the experiment is done. The first way, we did the experiment in very same way that you see that my cursor is here. When we apply force, we can see the protein unfolded, right? And then we reduce the force. We see that only one domain is refolded, right? It is 10 piconewton. So only one domain refolded here. So then what we did is that we again unfold the protein, change solution. Here we introduce salt and then again come back to the same force. So here you see 10 piconewton, the green one. Here is also 10 piconewton. But as now you are changing the salt concentration. The salt is actually helping the protein to fold, and now the protein is folding very much. So then you unfold it again and refold it again, and then unfold it once again. Now, the effect of salt on protein folding is very common and known. But here what I wanted to show you that in this experiment, only a single experiment can tell you the difference in the unfolding kinetics, refolding kinetics, equilibrium, and the conformational change. To show you better, I am zooming this range. So if I zoom this range, you can see that the black one is here and the red one is here. So for the black one, you can see that again, as we have 8 repeats, you can monitor 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. When you do the same thing with increasing the salt concentration, you see that again, you see the 8 steps, but there is a difference between mean free passage time. That means very easily saying that the unfolding kinetics is lowered down. And here you can see that what is the step size difference. That means what is the conformational change of the whole molecule. Now, very similarly, if I compare these two regions, you can exactly see that how fast the refolding is happening, and you fit properly, you can actually see that what is the delta G and how much change in the delta G is happening. Now, this is a nice place to collaborate and doing all these things. So you can exactly see that what a single experiment, how many information it can provide it to you. So not only that, if you see the plot here, this is the exact plot you see in the last slide. So here you see that I changed the force, something like that. You just need to monitor where my cursor is right now. So you see that the force is very low. You increase the force, you decrease the force, right? Something like that. But here you can see that what I did, here we did the same experiment, but we increased and decreased the force by a ramp. You just need to exactly follow my cursor. So when you did that, that force can be increased or decreased by ramp. Again, you see the same thing, that you can see all the 8 steps if I zoomed it, and it actually totally depends on what is your topic of interest. But the idea is that here you can apply force ramp as well instead of force clamp. So previously, the magnetic tweezer provided us the information about unfolding kinetics, refolding kinetics, delta G, mechanical strength, and conformational change. And in addition to that one, the real-time microfluidics magnetic tweezer provides us all the information along with the quantity change when you add salt, drug, or chaperone, or anything else. So I would like to tell you and emphasize that maybe this is the first time it is possible to see the exact change in monitor the molecular properties on a same and single protein. And correct me if I was wrong, but I think before, with any of the single molecule technique, going back on the same molecule and tracking the same change was not possible. So we have a small lab in Ashoka. Our lab is dedicated on development and technology, and try also to understand, what is the biological meaning, what is the biological information we can get with these technologies. So then we try to understand that, how basically chaperone works, and we studied the chaperone using the same technology. So with real-time covalent magnetic tweezer, we can also apply physiological force pulses. So that means that the force which basically our protein faces during translation or translocation, it is believed from around 1 to 20 piconewton. And then with this technique, we basically mimic the force condition and try to understand how basically chaperone behave under force. So before talking about all, let's just discuss about what a chaperone is. So chaperone, we all know that in the textbook that chaperone is known so far as a holdase and a foldase. That chaperones, we know that they basically rescue misfolding or aggregation. Some chaperone, they actually hold the protein. That means they don't allow the protein to fold. Whereas there is some chaperone like Groviel, HSP70, they actually fold the protein. That means they basically increase the folding rate. However, when we see that how basically chaperone behave under force, which was not done before, we actually found out that chaperone's behavior is now different under force. Very simply, I just can give you two examples. Is that trigger factor previously known as hold days, that means it actually don't allow the protein to fold. But now when we apply force, we found that trigger factor is increasing the folding rate. And in the next session of the talk, I will discuss that, why the change is happening and what is the physical meaning of this change inside a cell. So to begin with, we will start with a chaperone, which is trigger factor. So trigger factor, if you know that when the protein is coming out of the ribosome, trigger factor is the first chaperone that interact with the protein, right? So the recent paper actually shows that when trigger factor interact with the polypeptide, they actually, the polypeptide is under force of 6 to 9 piconewton. So what we did using this technology, we apply this 6 to 9 piconewton force on the substrate protein and then add trigger factor to see the effect. What we see that when I apply the force on the polypeptide, the protein is not folding at all. Let's see the data in the next slide. So, okay, again, the same plot, but I would like to ask you to go slow. At first, we have 4 piconewton, the force. We increase the force up to 50 piconewton. We decrease and put it at 9 piconewton. Then we increase the force 50 piconewton. Here we introduce trigger factor and then decrease the force and exactly come back at 9 piconewton. So how the data looks like, when I go 50 piconewton, again, it gives me 8 steps. And this is where we are using the 8 steps because, this gives us a nice fingerprint of showing that, this is exactly our protein is. And when you go 9 piconewton, you see that only one domain folded, right? Only one steps, one domain folded. But then when you add the trigger factor, the same protein here is actually gives you 6 steps. That means 6 domain folded now. So the folding is much increased. Now, if you think about a simple physics is that if you are applying force on the opposite direction, and if the protein is folding on this direction, that means folding of protein itself doing a mechanical work. And if we calculate the mechanical work, that is actually 59 zeptojoule. We explained that this is the force needed. This is the mechanical work needed for the protein to come out from a stalled ribosome. So then we check another chaperone, which is basically SEC-B. And what SEC-B does, SEC-B actually took the polypeptide from trigger factor and carry it to the SEC-A, which is basically a translocon pore and which passes the protein and the protein goes outside in the cell. So what SEC-B does, in short, SEC-B actually carry the protein from trigger factor towards the SEC-A. So now we try to understand what is the role of SEC-B on the folding of the protein. Our data shows that the first one is the refolding time. So we actually monitor how long the protein is refolded in presence of SEC-B. We found out that in presence of SEC-B, it took longer time to refold. That means SEC-B is actually acting in an opposite way of trigger factor and it works as a hold days. We found out it is decreasing the refolding but increasing the unfolding. That is saying the same thing, that the protein is helping the unfolding. And as the helping the unfolding and refolding, from the folding probability data, we can also see that the red one is the SEC-B, black one is without SEC-B. You can see that the folding probability goes towards the left-hand side. And as we calculate the delta G, I'm actually keeping the transition state constant because of explaining it easily. We can see that SEC-B is actually taking the protein towards the unfolded state, right? This is a very simple reason that the protein, when it goes to the SEC-A, the protein needs to be unfolded because the protein needs to pass through this gap. So the folded protein cannot do that. And we think that this is a nice meaning of the data is that the protein can actually unfold it while it passed through to the SEC-A pore. So then we tried another chaperone, which is DNAJ, which is also work as a transferring protein like SECB, and our result says that the DNAJ is also working as an unfoldase. Then it actually behaves very similar to that of the SECB and unfold the protein. So then we put the another chaperone, which is DNAK. This is a counterpart of DNAJ. We found that it also behaves, very similarly than of the SECB, and it also unfold the protein. So then what we did is that we found out that from the data is that DNAJ is unfolded, DNAK is unfolded. So we add now DNAK, DNAJ, group E and ATP, and found out that this actually working this actually increasing the folding of the protein. So here the data is little bit complicated, that when you have DNAJ, you see that it basically takes lesser time to refold rather than if you have only DNAJ. So the black one DNAJ, the red one you have DNAJ, DNAK, group E and ATP. So you see the refolding is now much faster, unfolding is slower. So the protein is actually helping this chaperone complex actually helping the folding of the protein, and it is actually comparable with the control one. So the black one is DNAJ, the red one is DNAJKE, but it is overlapping with the control. So that means it is of course helping the protein to fold, but not in a much greater extent. The reason is that when the protein is actually comes to the DNAK, it becomes unfolded. Then when DNAJ comes, then the whole protein goes inside the cage of DNAK, and then with the help of ATP and group E, the whole folding cycle starts. That's why it is folding faster than DNAJ, but it cannot increase the mechanical work like trigger factor, because in cytoplasm, you don't need excess energy to fold the protein. So to put it forward, we actually put another translocane pole associated chaperone, very similar to trigger factor. The name of the chaperone is DSBA, which actually sits on the periplasmic side of the translocation pole. So when we tried that one, because it looks like very similar to trigger factor, the effect is amazing. You can see the refolding time is so faster that immediately tells you that it actually helps the refolding of the protein. Again, the black one is the control and this one is the refolding. Unfolding time doesn't change a lot, but as the refolding time changes a lot, it shifts the energy landscape towards the right hand side, and the black one is the control. You can see the folding is much faster, and again the reason is very same, that as it folds the protein against the force, it generates mechanical work which actually translocate the protein from cytoplasm to the periplasmic side. So this is basically the pictorial description of that. So you see this is a SEC-A. This works as a motor with the help of ATP. This pushes the protein towards the cytoplasmic side. In the cytoplasmic side, there is DSBA. When DSBA interact with the protein and fold the protein, it actually stops the backsliding. So now the protein cannot go on the cytosolic end, and due to the generation of the additional mechanical energy, it actually pull the protein towards the periplasm. So then we try to understand that, why this is different. And we thought about that DSBA has a thyroidoxine domain. So maybe thyroidoxine domain is acting as a mechanical foldase. So what we did, we basically took two other thyroidoxine domain, but those are actually cytoplasmic one. So we took PDI and thyroidoxine, but interestingly found out that PDI, thyroidoxine and control all are overlapping with each other, but DSBA is the tunnel.
Subhashish, sorry to interrupt you. So 20 minutes are over, so you should be looking towards wrapping up soon.
Yeah, I think I have one more slide. That's it.
Okay.
Yeah. So DSBA is actually folding much faster and much more. The reason is that it can generate the mechanical energy, which can actually take the protein from the cytoplasm towards the periplasmic side. So now I can show you the best data of my slides so far. So I did all the experiment in a same and single protein. So when I put, and all the force is actually 9 piconewton. So, and I showed you only the refolding part. So the black one is the protein is hopping when we don't have any chaperone. So you see that the protein is hopping something like that, the black one. Then in the same protein, I add DNAJ. I see the protein is now hopping less, and it is basically shifted towards the unfolded state, because here in average 4 domain folded, here only 1 domain folded. On the same protein, when I changed the solution to the DSBA, I found out that the same protein is now folding very much, and almost 8 domains are folded here. So again, we basically calculate, we put all the folding probability together, and when we put all of them together, we can calculate what is the work done for all this protein. And we found out that protein is now classified in a 3 different classes. One is the mechanical unfoldage, where this is the mostly the transferring protein, where DNA-J, DNA-K, and sec-B, they transfer the protein. They are unfolded because they want to prevent the misfolding. Then we have mechanical restorage like DNA-JKE, PDI, and thyroxine. These are mostly cytoplasmic protein. They can fold the protein, but not to an extent, because they don't want to generate extra mechanical work. However, the tunnel-associated chaperone like DSBA or trigger factor, they actually folding the protein against the force, which actually create mechanical work. This mechanical work is helping the protein to translocate either from ribosome to cytoplasm or cytoplasm towards the periplasm. That's all. Thank you so much for your attention. This is my group. Shorodip, Shoham, and Deep, they did most of the experiment. And these are my groups which are working with, these are the undergraduates who are working with me. Thanks again for your attention. And I would like to thanks again for the organization for the inviting me.
Prerna, can I ask a question?
Sunita, go ahead, ask the question. Sorry.
Yeah. Hi, Subhasis. Very nice talk. I have a very naive question. This is a new area for me. In the first slide, you showed the schematic where you're trying to pull and push an protein molecule. Right? What I want to know is how do you select a single protein molecule, like a protein chain, for these experiments?
Yeah.
Yeah.
So yeah, I think I should also show you the picture. So, so at first we basically dilute the protein in so much extent that, all the proteins are kind of separate. So our concentration is kind of 5 picomolar. And then then we have also a bead, right? So the bead is actually a little bit bigger in size, and which actually we can see with the help of the microscope. So, we also have a microscope here, and from the microscope eyepiece, we can see the bead. So we exactly can see the beads, sometimes 2 beads are close together, maybe 2 or different proteins will be closer. But if we find 10 beads, we can find 1 bead with, they are separate. And as we have the fingerprint that we should exactly see 8 steps, of course we can do with a monomer, but particularly for this experiment, as we have the 8 steps, 8 domain, if we have all the 8 steps, so we took the protein. If we see here 16 step, 24 step, or 1 or 2 step, we didn't took the protein.
So if I understand correctly, the binding of only single protein chain happens because of this biotin streptobidine specific reaction?
Yes, totally
correct in saying that?
Yeah.
Okay. Okay, thanks.
I had a follow-up question on that. So how are you measuring the length of the tether?
Okay, that's a good question. And I actually, take out that part out. Okay, so I have 2 things there. One is that you see that I have a magnetic bead, and the magnetic bead attached with the protein. And the next to the magnetic bead in the same plane, I have a reference bead. So what I did is that at the beginning, I go different position of the magnetic bead and the reference bead, changing the Z axis, and check the diffraction pattern of the magnetic bead and reference bead, and make a library out of that. So in the library, I exactly know that what is the diffraction pattern at which positions, right? So then during the experiment, I actually compare the library and see what is the distance between the protein. Because when you apply the magnet, the magnetic bead involved, it increase or decrease the position, or so the reference bit still is there.
Okay. All right. Yeah. Any other questions?
I have a follow-up question, but I think Shubhashish's screen is. Shubhashish, are you still there?
I think he is there, no?
Yeah.
Okay.
Yeah.
So Shubhashish, just again, just a follow-up question to that. If you're measuring the force on the bead, does the force look like what you've drawn in the schematic there? Because it seems like the force has a significant, there's a significant gradient of the magnetic field, which would imply that the force is probably changing very locally, spatially it is changing. And if the particle must be exhibiting some sort of Brownian motion or XY motion, in that case, how do you keep that 45, 49, I forget the number exactly, but whatever piconewton constant?
Got it. So, okay, if you can see my hand, you have to see that. So this is the slide, right? This is the slide where my protein is threaded here, right? And the top, there is a permanent magnet. So, and the distance is so nice that you can monitor, you can keep the force constant. So, okay, if my permanent magnet is here, if my hand is here, if the distance is 4 millimeter, then the applied force is actually 4 piconewton. So the position, this 49 piconewton, or it's actually 49 piconewton, but you can also think it as a position of the magnet. This is controlled by a voice coil. So this is very stable. So as long as the position of the permanent magnet doesn't change, the force is actually constant. So,
but the bead is how big in size?
So bead is actually little bit. Bead is actually big. So bead is actually 2 micrometer in size.
Okay, so it's not moving at all by itself.
It can be moving like it's actually is a threader, so it can move like that, but not in the z-axis.
Okay. And this, so because you're using a permanent magnet, I guess the spatial at that particular location the magnetic field is quite flat. There won't be much gradient by itself, right?
Yeah, that's correct. So if I go very closer, so the force increases exponentially, but the difference in the force, if we have 3.6 millimeter, the force is 6 piconewton. If you go to 4 millimeter, it is actually 4 piconewton. So you have a large excess.
Okay, good. Okay, I'm done, Prerna. Thanks.
Yeah. Any other questions? If not, let's thank the current speaker, and I will invite Sunita to tell us about polyelectrolytes in multivalent salts. Sunita, you can go ahead and share your slides.
Can you see the slides now, Prerna?
Yes. Just go to the slideshow.
Yeah,
great. Yeah. Thanks.
I'll begin by thanking the organizer for giving me an opportunity to present my recent work here in this forum. I think it's a very appropriate forum for the people working in the area of soft matter. And today's what I'm going to talk about is the behavior of polyelectrolyte chain in multivalent salt environment. Before that, allow me to introduce my group, which is at Department of Physics, IIT Bombay. So these are the couple of projects that we are here interested in our group, starting from the tunable material properties, where we are interested in the self-assembly of functional materials by design. and where what we basically do is try to tune the interactions at the nano length scales using nanoparticle and several biomolecules to attend a programmable assembly of materials. In this process, we also investigate the physics of the self-assembly processes and some of its functional properties. I think my cursor is not there, right? 1 minute. Yeah. So we also look at some of the functional properties. The expertise that we have in our group is mostly in the techniques that we use is X-ray scattering. Interface rheology is a new addition to the available equipments in our group, and microfluidics is something that I'm interested to explore in the recent future. And the materials that we work basically the huge range of materials starting from polymers to biomolecule, nanoparticles, etc. So before I begin the scientific part of it, this is a picture of our group and these are our group members here. Today I'm going to talk about the work which was done by one of the group member, Anuj, which is shown here. He also presented a poster yesterday on the same topic. And the funding agency is basically DST for the Ramanujan Fellows, DST-SCRB, and the Startup Research Grant. Facilities here at IIT Bombay has been very useful in the initial days when the lab setup was going on. So with that, first few slides, I will try to introduce the basics of the polymer physics for the sake of the student audience. When we talk about a general chain in general, how does the soft matter chain difference is basically these are more flexible in nature. So one cannot define a distinct length scale for the polymer chain. The way it is modeled is using this bead model, where each of this monomer unit can be considered as a single bead. And the morphology this chain attains depends on several parameters. Okay, so in general, the size, if I call R, depends, of course, depends on this number of monomers that constitutes this chain, which is shown as by these blobs here. But it also depends on what solvents we are putting this. For example, in case of neutral polymers, what do I mean by neutral polymers? Are the chains which are basically don't have any charge in the background. Okay, so for that, if we put this chain in a poor solvent condition, for the sake of simplicity to understand what is poor solvent, a solvent which basically in which this polymer chain doesn't like to dissolve. So in those cases, we see that the morphology this chains attain can be calculated using this scaling relation here, which basically the chains adopt a collapse-like state. In theta solvent, where there is no preference for the polymer chain beads to interact with the solvent molecules, the chain size scales as n power half. And if you put the same chain in a good solvent, which means the chains like to interact with the solvent molecules, then one can define the size of these chains by something which is known as the Flory radius, and then it can be indicated or scaled. It scales using this relationship here. So the motivation of putting this little piece of information here is this: even for the neutral polymer chains, the chain morphology is not simple, and depending on its solvent behavior, and also not only solvent, the pH as well as the concentration of the polymer chain itself, the morphology that these chains adopt, the soft chains that it adopts, can be quite complicated. So this has been an area of investigation for quite some time. For now, if we move to charged polymer chain, if you take the same number of this monomer unit, but if you somehow, let's say, put some charge on the backbone, what you will see is this chain starts extending in, let's say, one-dimensional chain. If you take it, starts extending in one direction. So instead of adopting this blob-like morphology, the chain exhibits this extended behavior. So this is quite interesting. In case of, let's now focus on the polyelectrolyte chains in different salt environment. So here are some of the examples that I've taken from the literature from this particular paper. So what is plotted here is end-to-end distance for a polymer chain. And this number here are the number of monomers that constitutes the polymer chains. So as one would expect, as we increase the number of monomers here, the end-to-end distance increases. What is interesting to see, as I told in the previous slide, if one can calculate the chain length using the same number of monomers for a non-charged chain, you see this is the plot shown here. So of course, with salt increase for the non-charged polymer chains, it should not change, but effectively even at zero salt, you see that charged polyelectrolytes actually exhibit longer chains. So this is what was shown in the previous slide here, okay? And then if you increase the salt, there are some complicated behaviors that I'm going to address in this talk. So for example, for the same system, if I introduce a divalent salt, in this case it is MgCl2, and perform the same calculations. Here you see for the MgCl2, the starting for the same system, the starting sizes are much more smaller. So it seems when you have a cation into the system, there is some kind of screening of the electrostatic repulsion going on. So yeah, I forgot to mention actually in this slide here, why do the chain keep an extended morphology is due to the fact that now on the backbone, they have this, let's say, negative charge on the backbone. So these chains, apart from the usual steric repulsion, they also experience is the electrostatic repulsion. So that leads to, that basically prevents from this monomer by coming together by folding or any other mechanism, and that's why energetically it is more favorable for these chains to adopt this extended morphology. Okay, so coming back here, yes, now when we start adding an external salt, in this case it is cations, there is some sort of a screening of the electrostatic repulsion that is happening, and the chain length starts decreasing. Okay, and eventually at very high salt it starts saturating to this values. Interestingly, this behavior again seems to have a non-uniform dependence on the valency of the cations that we add. For example, here, this is a trivalent salt, cobalt salt. Apart from the usual initial decrease here, after a certain salt concentration, the data shows some sort of increase. Okay, and this has been puzzled into the in the community where people are looking at the salt dependent morphology of polyelectrolyte chains in general. So let me give one more example here. So this not only depends on the valency of the salt, but also on basically the size of the physical properties of the cations that one uses. But that in case of monovalent, you see that if you use a bigger salt, this is slightly higher in number. But overall, the dependence is much less as compared to a divalent salt. As one changes the size from 3.6 to 1, here the difference is quite large. So this again tells us in an overall that the way divalent salts interact with these polyelectrolytes is much different from the way monovalent salt do. So this is a simulation result where the authors have plotted the force. So they've taken this two double stranded chain, and they introduce both NaCl and MgCl2 salt. So NaCl is monovalent and MgCl2 is divalent. So in those cases, what they found for the NaCl2 throughout the force versus distance curve, it kind of shows this. There is a slight dip, but overall doesn't show any strong indication of attraction between the chains. Whereas for MgCl2, which is a divalent cation, at certain distances between these chains, there seems to have a strong attraction between the polyelectrolyte chains in general. Some other examples from the MD simulation, that it shows that apart from the salt-induced attraction, there are also processes that happens in which one can see that there is something called salt-induced overcharging or charge repulsors, if I can say. So there's some kind of saturation that happens from the attachment of these cations to the backbone of the polyelectrolyte chains. And beyond a certain salt concentration, the chain again starts behaving like a chain with the same charge, and they start repulsing. So initially one sees a drop in the chain length and then it starts increasing. So most of these results are based on the theoretical calculations or simulations. The experimental results are very limited in context to understanding the morphology of the DNA chains. in general. And the limitations come from the fact that the techniques that one uses to measure the chain morphology, because the DNA, let's say DNA or any polymer chain has a very low contrast with respect to the solvent medium. So there is the limitation here. So with that brief introduction, I'd like to introduce the system that we are using to kind of address the problem in context to the investigating the morphology of DNA chains under multivalent salt environment. The system that we are using is DNS, as many of you might know, but again, for the sake of the students of audience who are students in the meeting, this DNA chains are this double helical structure, which has this phosphate backbone, and the nucleotides, which are basically CTGC, are attached to it. And this also has a negative charge on the backbone. Interesting part about this DNS that basically separates it from other polymer chains are the fact that these nucleotides can exhibit this very specific Watson-Crick base pairing, where, for example, the G can react to C and T can react to A to form hydrogen bonds, which are reversible in nature. Okay. And it is also like one can do a thermal cycling and go back and forth. It's like you can zip and unzip the bonds, those are formed. So this came as a very interesting property in terms of the self-assembly of nanomaterials. And the fact that these chains are reversible, also the bond length and the chain length here is tunable. One can take a synthetically designed DNA chains and program the number of monomers here. So I try to tune the self-assembly processes. And again, as I said, the fact that these bonds are reversible, one can envision to have a programmable assembly. So the major limitation before the role of DNA-driven self-assembly came into picture was the fact that if you look at a self-assembly process in most of the system, if you take two system and try to self-assemble, what happens it gets stuck in a local minima. And then either it is basically, it forms some kind of arrested phase, glasses or gels. And only once if you can take this system from a local minima and put it into a global minima where energy is minimum, then what you will get is a crystalline structure. So people started exploring the role of this kind of properties of DNA and using the nanoparticle, functionalizing the nanoparticle with DNA chains. So to begin with, what I'm showing here is just a schematic of gold nanoparticle, which can be attached to where the DNA chains can be attached to the surface of this gold nanoparticle by using a simple chemistry. And I can choose the end of this DNA chains in a particular fashion so that if I bring two of these nanoparticles together, they are able to form this Watson-Crick base pairing. Through that, the hydrogen bond will with them. So if I make a system like that, and if I look at the self-assembly, in the beginning of 1900 or 1990 also, what people saw that these systems are actually aggregating in a nice structure. Later on, into the 3D morphology, people have figured out a way of looking at the crystalline assembly based on this self-assembly of nanoparticles which are coated with DNA. So what's shown here is this data. We see diffraction data from this nanoparticle clusters assembly, which shows this high order of peaks and which can form certain kind of structure. So now we talked about the crystallization. So okay, this can form a nice crystal structure, but it can not only do that, it can do much more than that. For example, here it's shown as case where if I can take this two nanoparticle system and coat them with DNA chains which are self-complementary. What do I mean by self-complementary is that externally from my experiments, I'm not putting any constraint in terms of the number of bonds that they can form with each other. In these situations, what happens? They come close to each other and they form this nice close like BCC structures. FCC structure. Now, if I want to tune this crystalline lattice, I can change the composition of this DNA chain, which is on the second nanoparticle, let's say, and then I can design a system where I force my nanoparticle, which is shown in blue here, to have a specific kind of interaction with only nanoparticle, which is shown in red, but the red cannot interact with red itself, and the blue cannot interact with blue. So once we do this, then we see that the system is forced to adopt a crystalline lattice, which is much more open and which is not necessarily an energetically favorable, but still, because of the way by design we're able to switch this structure from FCC to PCC. And then there was this paper in Science in 2011 by Merkin's group, where a lot of experiments have been done. And now this lattice crystals that we can get from the DNA coated nanoparticle are not limited to simple cubic structures only, but there is this whole range of crystalline systems those can be formed. Starting from, I've shown you example for FCC and BCC, but simple cubic can also be formed, as well as complicated structures with binary phases, including the diamond kind of lattice has also been now reported. So this is very promising. Okay, the advantage of using DNA, as I said, is that one can, at any by thermal recycling, open the connections between the nanoparticle and again reassemble them. So any properties, if you want to introduce any drug or something, you can do that in that context. So this was about the 3D systems. My contribution in this field is basically trying to get something on the 2D systems, where during my postdoctoral work, I have shown that one can use the same kind of programmable assembly approach and assemble these nanoparticles in 2D. This is in GSAX data, which is some extension of X-ray scattering in 2 dimensions, which is known as grazing incident small angle X-ray scattering. The peaks that you see here are the diffraction peaks, which comes from the intercorrelation interactions between these nanoparticles. Okay, and more number of peaks here indicates long range of ordering. So by looking at this peak position, one can estimate the lattice symmetry. In this 2D case, it turns out to be hexagonal. So these are the SEM images, where you see like this scale is around 100 nanometers. So very long range ordering can be seen from these particles. So the other advantage is, because this is polyelectrolyte chains on the nanoparticle, I can tune the interaction between these 2 nanoparticles, right? So for example, in this case, this is a repulsive particle. Now I can design the DNA chain in such a way that this ends here would prefer to talk to the neighboring particle. In those cases, I can this would be attractive actually. So I can make this particle from repulsive to attractive, and what I can get is this transition from this nice ordered structure to in this linear like phase. And we also did a detailed study about how this structure relates with the other dynamic properties of the system. I'm not going to talk about that anyway. So with this little background, I'm going to introduce the system that we are going to use for our this multivalent salt dependent studies. So since being an familiar with this technology, I began wondering about what system to choose, and then we started with this DNA coated nanoparticle. So we synthesize our own nanoparticle and we functionalize them with synthetically bound DNA chains. And here is this characterization in terms of the UV vis spectra that's shown. The black curve here is for the single nanoparticle system, and as you know, this peak here is the plasmon peak coming from the nanoparticle. There is this additional peak that comes from the DNA adsorption on the system. So as I said, once we have this DNA coated nanoparticle, the possibilities are enormous, because there is a huge amount of tunability that one can get. For example, these are repulsive particle, and I can design these ends where I can make these nanoparticles attractive. And these are the data for the BCC crystals that we have obtained from by taking this assembly of this kind of nanoparticle. And what happens is there is this nanoparticle at the center and the nanoparticles at the corner. Okay. So with that, since we already have this information that we can get this nice structure from this DNA coated nanoparticle, and the advantage of using this system is basically I can estimate like the positions of this particle can be very accurately determined using this X-ray scattering technique within the resolution of 2 nanometer or so. So the hypothesis that we, like the idea that we begin with is that we start with this kind of BCC crystal, and we add monovalent and divalent salts into the system, and we look at the diffraction data and we see how the crystal lattice changes. Okay, and that is what we see here. So this is particularly a small angle X-ray scattering data. The different numbers here indicate the salt concentration. I've shown it for MgCl2, the divalent salt. I've already showed you the data for a monovalent salt. So you see, when we go from a monovalent to a divalent salt, actually the structure of the lattice does not change. But what changes is with increase in the salt, similar to what I have seen. I think I haven't shown you the data, but similarly what we see for the NaCl system, the monovalent salt. A little bit about the small angle X-ray scattering technique is what we see in that data is basically scattering for this core of the nanoparticle. So the X-ray only sees the nanoparticle core, which happens to be gold in this case. And from this peak positions here, so this is just a schematic showing that. Yeah.
Hi, Sunita.
Yeah.
Sorry to interrupt you. 20 minutes are over, so we have 10 more minutes to complete the session.
Oh, is it? Okay. Yeah, so these are the lattices that we saw. So maybe I'll try to speed up, and then if there is a query about how we arrive at the result, I can take it in the session. So from this, I can estimate the basically the center to center distance between the nanoparticle from the lattice. And this is what is shown here. So then we add different types of salt. In this case, I'm just presenting the data for NaCl and MgCl2. And what we see is that basically with increase in salt concentration, the center to center distance from this information here, we can calculate the DNA chain length by using this formula. We subtract the nanoparticle diameter. So interestingly, what we see, the common features are in both the system, the NaCl and MgCl2. With increase in salt, the chain length decreases. But if we do the power law analysis, we see that in case of a divalent salt, the exponents that we get is almost 2 times the exponent that we get in the NaCl. And I will also want to bring your attention that what we are plotting here is the ionic strength and not the salt concentration. So any valency related changes are taken care of. For the monovalent system, there has been a lot of studies, and the exponent that we find are kind of in hand with the information from the literature that people have done calculation as well as experiment. But the divalent salt is a puzzle for us. The fact that there is no upturn in this H versus I data, then here at this point we can rule out the factor that there could be any charge reversal phenomena happening in this system. So I will quickly skip, like run through this part where we have tried to model this H versus I data using a standard Dowd-Cotton model. And we made some of changes in terms of the excluded volume parameter and the cone length. We introduced some salt dependence into this, and we saw that this data fits exactly. However, the exponents we get for the divalent salt are not in hand with what comes from the theoretical calculation. So we propose, in order to understand that, what we propose is that there's some kind of ion bridging that is happening in our system. And to quantify that, we plotted this data where we took the difference in the DNA chain length for the monovalent versus the divalent system. And interestingly, what we see that at the initial salt concentration, it increases and then saturates. And these are the saturation values listed here. So what we found is that that the electrostatic screening is present both for monovalent and divalent system. However, for divalent system, there is this extra overriding effect, which comes from the effect of ion bridging. And at low salt, the DNA chain is primarily governed by the divalent mediated bridging for the case of the divalent salts. And whereas for the monovalent salt, it is just the usual electrostatic driven screening that dominates the morphology. So this is some additional experiments that we did to verify our hypothesis, and it turns out that the results that we get is as per our hypothesis, and it is correct. For example, if we reduce the grafting density, by increasing the size of the nanoparticle, this chain adopts less morphology, and we see this interesting two phase into the H versus I data. Initial phase is dominated by ion bridging. At high salt concentration, what we see is the usual electrostatic repulsion, and this is comparison for the monovalent systems. So with that, I would like to conclude that for these systems that we have studied, high density DNA driven systems under different valency salt environment, for the divalent system, what we see is ion bridging driven change in the chain morphology, whereas for the monovalent system, it is usual electrostatic screening. And I'd like to conclude since I already ran out of time. And thank you very much for your attention. If there is any question, I'll be happy to take it.
Thanks, Sunita. So the floor is open for questions.
Hey, Prerna, can I ask a question?
Yeah, please go ahead.
Okay. Sunil, is very nice talk. I have two questions. One regarding the two-dimensional assembly that you made.
Yes.
So why there are too many defects here in this system?
Here?
Yeah.
Yeah, this defects are something that is unavoidable. So I like to bring your attention that this two-dimensional assembly happens at the air-water interface. So the system that we have is this lipid membrane we are using as a facilitator to bring this nanoparticle in the confinement geometry. Now, these are the SEM images which are taken after transferring this nanoparticle system on a solid substrate. So if we want to look at the defects, the actual thing that you should be looking at is this data here, the X-ray diffraction data, and you see that the first peak is almost like a delta function. Okay, so this kind of correlates, SEM images correlates with what we see, but the actual picture is given by this diffraction data because these are the NC2 data. This defects mainly comes in the SEM images due to drying mediated change in morphology of the nanoparticle, which is something non-avoidable actually.
Okay. Okay. Another question is regarding the last part. So you didn't talk about the overcharge if there are.
Yeah. So in mostly in case of those are not my data. In case of trivalent salt, people have reported by some calculations that there can be overcharging. Okay, in those cases, what happens if you look at the polyelectrolyte chain length as a function of salt concentration, then basically initially it decreases, but when there is some kind of equilibrium that is reached, then there is again repulsion between the monomers that starts. So what you see is this kind of upturn in the data. For our divalent system, we have gone to very high salt concentrations here. Yeah, if you look here, even in terms of ionic strength, we have gone to like 0.3 or so. That is huge for the divalent salt. But we do not see any kind of upturn. What we see is the data kind of saturates. So that's why we have ruled out the possibility of any charge reversal in our system.
But if you use calcium, you will still
yes, that's something we are actually trying to look at different kind of salt, because the literature does suggest that the specificity of the cations also have a role, but we haven't done it so far.
Okay. Thank you.
Okay, thank you.
Sunita, I have one question. This is Divya here. Hi, very nice talk. Actually, I was just wondering that when you use the divalent ions, does that affect the surface coverage of the nanoparticle in the way that these divalent ions, you said they form ion bridges. So do they go in between the chains and do not allow more chains to cover the nanoparticle surface? Is there a correlation?
In order to rule out any of such thing, what we do is we first assemble this, we first functionalize the system in basically following a protocol which doesn't involve the divalent. So there is some kind of incubation that is needed in terms of addition of salt. For that, we use monovalent, and then we try to wash it out completely with a buffer solution. So when we start with this system here, we don't have any divalent. So functionalization is not done with the divalent salt.
Okay. And the subsequent question I have is like, what is the role of water in this? Because I believe when you add divalent versus monovalent ion in water, they behave very differently in affecting the structure of water. So do you see any effects?
That's a very interesting question, and that's something I'm also breaking my head over, how to try to like differentiate the effect of the cation and the water molecules, right? But I will say that I'm ignorant about those effects at this point, because the technique that we are using is not sensitive to get any kind of internal details in terms of the cations and the water molecules. So yeah, that's an assumption we are making, that they don't affect the lattice structure.
So probably like if you can do some structure factor measurements for the solvation shell waters of in the first solvation shell of these coated nanoparticles, maybe that can give you some idea.
Yes, yes. And what we need to do, we need to measure this scattering in terms of absolute unit. So that's something I have put a proposal in the synchrotron for getting this kind of data. But yeah, that's something in the future. Yeah.
Okay. Thank you.
Yeah. Thank you.
Okay. If there are no further questions, let's thank Sunita for a great talk. Is there a question? Okay. So Tamal, you can start sharing your slides.
Okay, sure.
And Tamal is going to talk about collective cell migration.
Is it time for that?
I think someone's mic is unmuted.
I think Prerna, someone is trying to ask a question, if I'm not wrong. Is it Dilip?
Yeah, Dilip's mic was muted. I mean, unmute. So Dilip, were you trying to ask a question? Okay, go ahead. Yeah, you can go ahead.
Yeah,
I think
Then there is some
internet.
Okay. Dilip, we can't hear you properly. Your voice is breaking.
One is additional salt. Can you hear?
Sorry, Dilip, I can't hear you.
Perhaps you can type your question in the question answer box and Sunita can answer there. Okay, let's get started with Tamal's talk, and at the end of it, we can see if we can get to the list.
All right.
Yeah.
All right. Thank you.
Yeah.
Okay. So can I start, Prerna?
Yes, go ahead.
Okay. So first, I'd like to thank the organizers, Susmita and Alok, to give me this chance to talk about our works. So this is going to be something different, and this is going to be something on the other side of the biology. When you talk about the cells and the multiple cells, we have been listening to the story at the molecular end of it. Now we are at the other end. So what I'm going to talk about, some emergent feature of collective migration, and then you may ask what is collective migration, and in a one single sentence I can say that it is the coordinated motion of many biological cells as a single group. And what I'm going to talk about in this in this talk is how is it different from the single cell migration. So this collective dynamics, it happens at the many level in nature, and especially at the organism level. You have seen this nice displays of the bird flocking, fish school, sheep herd, and it is generally can be defined as the correlated or the coordinated behavior of several individuals. And at the level of the organism, there have been attempts to explain these patterns with some local rules. And eventually these rules, what people have discovered, are very simple. So can you see my cursor? Can you see my cursor? Sorry.
Yes.
Okay. Yeah, so that these patterns can be explained by very few local rules. So one of the rule is that if the two organisms are very close together, if they are within this sphere of attraction, then and they're going to be a sort of repulsive interaction between them because they don't want to collide each other. On the other hand, if they are going very far apart, then this organism would be drawn to the collective again because nobody wants to be alone. And within some radius, the organism just, let's say in the nearest neighborhood, the organism actively tries to sort of orient their movement and the behavior according to the nearest neighbor. And the important thing is, if you in the motion, if you vary the contribution of these three rules, repulsion, orientation, and attraction, you can produce this sort of behavior like swarm or torus or flock. Okay. And so the question that we ask, that when you look at the collective motion at the cellular scale, like what you are seeing right now, so what is happening here, the group of cells, the epithelial cells, they are moving together to close a wound. The question that we ask, can we find the similar sort of rules? Okay. So here what we do, we create a wound in the epithelial tissue, and then the cells move together to close the wound. Okay. And then we can image that under the live microscope and find out different things about this collective migration. And with respect to that, one of the important questions is that how collective migration is related to the single migration. If you, I don't know how many of you have seen these movies. Maybe many of you have seen these movies. So this is a very old movie in 1950s taken by David Rogers at Vanderbilt University. And it shows a neutrophil chasing a bacteria and eventually engulfing it. And since then, over like next 70 years, the cell migration at the single cellular level has been dissected. And now we know all the nuts and bolts of the single cell migration, like they form this complicated network of actin. There are some actin fibers as well as the intracellular structure. The structure inside the cell changes as the cell migrates. Now, with related to the, so this is a kind of a fairly, from the molecular point of view, this is a very fairly complex and detailed picture. But the question is related to the collective migration, that all of this complex event now need to be synchronized in the many cell level. And the question is, how do the cell achieve that? So to understand that, what we do, we take two complementary approaches. The first is physicist approach, what we call. And there, what we do some physical or geometric measurement. And with those measurements, we ask, can we find some sort of rules or underlying principles of the collective cell migration? Now, once we know these rules or the underlying principle, then we become biologists and we start asking the question, deeper biological question, and actually try to find out what would be the molecular mechanism that decide this rule. So what we are trying to do, we are trying to understand the rules at the multicellular or the collective scale, which is like the tissue scale, and then trying to explain those rules by the event that is happening at the single cell level or even at the molecular level. And so first, talking about how do you do, what do we do in terms of the physical measurement of the geometric measurement. So we use an array of biophysical techniques like traction force microscopy, by which you can measure the forces that cell exert on the surface. We can also measure the forces at the level of cell-cell junction, and we can talk about the stress distribution in a tissue as such by monolayer stress microscopy or Bayesian inverse stress microscopy. At the other end of the story, we can actually use some Fred-based molecular tensor sensor with which we can measure that how much force a molecule is experiencing by measuring the Fred. And then we have also started building tools like optical tweezers to measure as well as exert forces on the cell. Okay. And all of these biophysical techniques we then complement with the molecular cloning, gene silencing, immunocytochemistry, the sort of the typical biological or the molecular biological technique to understand the mechanism. So with that, let me talk about some of the emergent features of the collective cell migration. By emergent features, what I mean, something which does not exist at the single cell level, but it appears at the collective level. Okay. So this is where, let us start with a very simple thing first. So let us start, since this is a migration, it involves motion. And so how does the motion look like in a collective? And already what you can see over here, that the cells, if they are moving together, if they are moving collectively, they show long range motion coordination. Okay. So there is long range coordination of motion. So how do we quantify this? So for this, what we quantify is the velocity correlations. So we try to find out that two cells, let's say separated by a distance r, how their velocities are correlated. And then this generally follows in sort of exponentially decaying curve. And at some level, we said that we can determine the correlation length beyond which the correlation, this velocity correlation vanishes. And we can observe that this correlation length within which the cells are actively coordinating their motion is actually multiple cell length. For example, here the correlation length is about 150 to 200 micron, and each cell is about 10 to 20 microns. So we can see the cells are able to coordinate their velocity over a length scale which spans maybe 10, 15 cells. Okay. So this is one behavior emerges, but the question is, how do the cells coordinate their movement? So for that, the other things come, which is the force measurement. And when we do the force measurement and especially the stress measurement in sort of this migrating monolayer, there is a nice behavior or the systematic behavior or the rules or the principles come out. And it seems that at any point, if you are able to draw a stress ellipse and have the true principal stress axis like the sigma max and the sigma mean, then the local velocity vector invariably follows the maximum principal axis. So quantitatively what it means is that if I draw an angle omega between the local velocity vector and the maximum principal stress, then this angle is very heavily biased towards zero. Okay. So this is a behavior which shows that the cells follow. So if I want to interpret it in terms of the biological sense, then we can say that the collective cell motion is kind of directed by the cooperative cell-cell normal or pulling forces, because this is the direction in which the shear force is zero, and this is the direction the cells are trying to follow the maximum normal force, okay, at any point. And this motion has a special name called plethysmataxis, meaning the crowd following behavior. Now, as we know that this is the sort of the emergent property which does not exist at the single cell level, but it exists at a multiple cell level or a collective level, then the question is, what is the molecular mechanism that enables cells to follow the principal direction of the stress or this pulling force? So to do this, what we can do, we can use this sort of behavior, this sort of relation, what you have over here as in a typical biological language, what we call the phenotype. And then screen for gene, knock down one protein at a time, one protein at a time from the cell, and then try to find out that how this behavior is jeopardized. And with that, what we found, 5 years ago, that there is a protein called marlin, which has some role, because if you knock down marlin, if you remove marlin from the cell, then the stress following behavior doesn't exist anymore. The motion becomes random. And then in further molecular investigation, what we found that in a standing cell, marlin is there at the cell-cell junctions, but as the cells start moving, marlin moves to the cytoplasm. And we have then further keeping the long story short, we did a lot of molecular biology studies showing that as the cells in the front start moving, the tension in the junction increases. As a result of that, marlin, which was localizing to the cell-cell junction, now moves to the cytoplasm. That kind of triggers some molecular reaction, which leads to the formation of leg-like structure or lamellipodium. And this is how one cell would follow another. So this is the molecular mechanism. And whatever we found, right, this behavior, this stress following behavior is the general rule or principle. The second emergent property of the collective cell motion is the existence of these leader cells. Like what you see here, these cells with this orange color. So it is kind of had a head start. So all of these cells are equally likely to become leader, but somehow one cell became the leader cell. And it seems that these leaders have very important and physiological implication for wound healing, for new blood vessel formation, as well as a cancer metastasis, where a group of cancer cells are moving and invading the tissue. And the question that we ask, that why do only some cell becomes leader cell? So all of these cells are equally likely to, apparently all of these cells are homogeneous. So they are equally likely to become the leader cell, but then only few cells become leader cell. Why does it happen? What is the selection process? So this is where a graduate student, Medhavi, she started asking the question. And at that time, when he started exploring the question, the conventional idea was that there is a hierarchy. is that when the wound is created, all of these cells are equally likely to become the leader, but some cells can trigger their signaling reaction and can form this leg-like structure. They would become leader, and they will then instruct the followers to follow them. So within this conventional idea, the followers play no role in selecting the leader. But when you started looking at it, when it started bringing our tool of biophysics and apply that and trying to understand that how the leader cells are generated, we are in for a surprise. So what you notice is that before the leaders are actually formed, this is like 15 minutes before the leaders generated, and the would-be follower cells already having very high tension. And if you look into the traction, that is the force between the cell and the substrate, you see that the would-be follower cells already are having highest traction, and they are also under a lot of contractile stress as such. And this is like a behavior we found again and again and again. So we tried to understand that where this fluctuation in traction comes from. And this is where I should mention, if you measure the stresses in such a monolayer, just like a granular matter, if you measure traces or if you measure the velocity, it is not a smooth profile, but it looks like an peaks and valleys. The same way in a cell monolayer, we have the stress peaks and stress valleys. And somehow the difference, the distance between two nearest peak correspond very well between the difference between two consecutive leaders as such, showing that there is a correlation between the force fluctuation in the bulk and the leader cell generation. What we also did, we created some of the cells, like in the red cells, which are like control cell, we have some green cells, which are more contractile, more force generating cells. And what you see over here, that these cells, if they are on the follower layer, inevitably they form a leader cell in front of them. So what we have shown in this story, which we published 2 years ago, is the leader cell formation is a more democratic or system driven process, in which way the followers actually define the biophysical behavior of the followers, actually define the leader cell formation. So now the question remained, what is the molecular explanation? I mean, we know that there is some biophysics thing going on, but what is the molecular signaling happening? So this is where a postdoc in my lab, Ritu, I mean, she is a specialist in lysosome biology. She did her PhD in lysosome with in Aizer Mohali. So she started looking at how the lysosome, which is a cellular organelle generally known for degrading some of the cellular material and localize it in a collective. And what she found is that before the leader cells are actually formed, lysosome accumulate it in the would-be leader cell. In fact, she could show that if you look at a lysosome deprived region and compare that with a lysosome rich region, then you see that the lysosome rich region kind of expand and successfully form this protrusion, while the lysosome deprived region within the same time doesn't do much. Okay. From moving from this correlation to causality, what she has done is she has sort of optimized a tool by which she can either pull lysosome towards the peripheral membrane, or she can hold lysosome back towards the nucleus. And using that tool, she is able to now control the leader cell generation. So what happens is that if she pushes the lysosome towards the cell periphery, in the cell where she does that, those cells inevitably becomes the leader cell. At least there is a high chance of those cells become the leader cell. On the other hand, if she keeps the lysosome in some cells, she keeps the lysosome towards the nucleus, like what happens over here, those cells rarely become the leader cell. In fact, in a collective, if we don't do anything, of all the marginal cells or the cells at the boundary, there is a 15% chance, like 1 out of 6 or 7 cells become the leader cell. But if you are able to throw the lysosome towards the periphery, that chance improves to the more than 50%. And if you bring the lysosome towards the cell nucleus, then that chance reduces to the 5%, showing that lysosomes is actively doing this. And now she is trying to understand the deeper molecular mechanism, that how lysosome localizing to the cell interface actually makes this protrusion formation and this lamellipodia formation. Coming to the last emergent property is the cell polarity. And there is so we look where we try to look into the internal organization of cell. And there is a very old idea that the cells that we look at, what we call the epithelial cells. So in epithelial cells, there is a polarity that if you look into the cells, the cell nucleus is towards the basal level of the cell, and the Golgi complex, which is a very important organelles inside the cells, is on top of that. Now what happens? So this is generally in a epithelium which is quiescent or sedentary or not moving. Now when the cells start moving, then this apicobasal polarity, or you may call it vertical polarity, becomes the front to rear polarity or the horizontal polarity. And there's a question that how does this thing happen? And this sort of thing is, again, this is a very much property of a collective. You don't see this polarity switch in a system where if you are looking at a single cell level. And this question, this observation has been known for many decades as such. I mean, in the earliest was probably made by Ramanwai Kahal in 1910s, but at least in 1970 there was a paper where somebody named Robert Strelstad started looking at these changes of Golgi in epithelium, and what he conjectured is that this change must be an active process, and it should have a purpose. But 50 years later, we still do not know, is this process active or a passive consequence of cell flattening, and what is the underlying molecular mechanism. And this is where a very talented PhD student in our lab, Purnati, she started looking at it. And what she started noticing is that at the very simplest level of cell collective, where we just look at two cells, like what you call the cell doublet, the polarity of the Golgi apparatus looks like a dipole. That is, if we draw an arrow from the center of the nucleus to the center of the Golgi, for a cell pair, these arrows will be pointing away from the cell-cell interface. And she further showed that this pointing away of this Golgi polarity, or what we call the cell dipoles as such, this is an active and force-dependent process. Because if she gets rid of the active force generation within the cell by treating the cells with a drug called brevistatin, these arrows become random. And when you washes out this drug and let the cells again acquire an active force generation mode, then it establishes again, this dipole establishes again. And interestingly, as you know from the collective migration, and a collective in some theoretical view can be considered as a combination of dipole. So one of the question is, how do the Golgi polarity behaves in a collective sense? And we can determine the Golgi polarity in one of the cells by segmentation, as well as we can measure the forces. And when you do that, what you find is that the force polarity is very much aligned with the Golgi polarity. In fact, if we define an angle theta between the force polarity and the Golgi polarity, they kind of go very in hand to hand together. So this is the kind of rule which exists in a collective sense, which does not exist. You don't see that in a single cell migration. Now the question is again, what is the molecular mechanism? So this is where Purnati started looking at the dynamics of Golgi, and what she discovered is a very fantastic thing, that the Golgi undergoes through 3 stages. So in the quiescent cell or the sedentary cells, the Golgi is on top of the nucleus. Then this Golgi complex breaks down and it sort of spread all around the nucleus to the equatorial plane of the nucleus, equatorial plane of the cell, and then it gets assembled at the one end of the cell. And now doing some super resolution microscopy, since Golgi has a complex structure made of stacks, and stacks are connected together to make ribbons, we now know that using the super resolution technique, that during this transition, the stacks remain intact, but the ribbons get fragmented. She has also started looking at further deeper molecular mechanism. And now we know that the Golgi complex interacts with the actin cytoskeleton. And if you notice these movies, there are like projections coming out of the actin cortex, which is kind of catching the Golgi and tearing them apart. So with that, right now, what the model is trying to build is that in a standing cell or a sedentary cell, the actin ring kind of holds the Golgi together. As the cell flattens, this actin ring pulls the Golgi apart and in a process just fragments it. And we are also looking into the deeper molecular mechanism. So to conclude everything, so we looked at 3 emergent properties. We looked at collective coordination. We looked at the leader cell generation, and we looked at the collective polarity as such. And the idea is very same, that we first take the physicist approach to understand the general rules or principles, and then we take the biologist approach to understand the mechanism. So in our group, we follow, so whatever, so there is a nice comment which I very much like from Sidney Brenner, who said that the progress in science depends on the new technique, new discoveries, and new ideas, probably in that order. And then spirit of Sidney Brenner, I mean, the approach that we take is also the same, that we try to make new techniques which leads to new observation. We understand the rules of this game, the collective cell migration, and then we go after the molecular mechanism. So we have a very dynamic group at TIF and Hyderabad. And in addition to collective migration, we work on one other collective phenomena. It's called cell competition. And there have been also some wonderful collaborations, especially with Medhavi, Joachim, Ulrich Schwarz, Mohit Jolly, Max B, and Leo Ratia. And we are funded by DAE, Wellcome Trust, and the Max Planck Society. Thank you very much. I will be happy to take questions.
Yes, thank you, Tamal. So, any questions? So, in this force dipole study, Tamal, the Golgi study. So, I didn't follow. So there was a correlation between the dipoles here and what you get from from the stresses below the substrate, or you don't measure the stresses below the substrate here?
Yeah. So what we are so these forces are actually indirectly calculated from the stresses measured at the cell ECM interface. But here we are looking at in-plane stress, that is the stresses in the monolayer.
Right.
Okay. And if the monolayer is thin as compared to, like, if you look into this is like a few hundreds of micron by hundreds of micron, and the height of the monolayer is 5 micron. So you can just consider this is like a 2-dimensional solid body problem where the traction forces will come like in source term. So you are basically solving this Cauchy stress problem and trying to calculate all the sigma xx, sigma xy, and sigma ayy.
Okay. Thanks for the clarification. Any other questions? So there's a question from an attendee. Go ahead.
Yes.
Hello, sir. Can you hear me?
Yeah, I can hear you. Go ahead.
Yes, sir. It was a very nice talk. So I just had one question regarding this leader cells. So the first thing is I'm not able to visualize what's the energy source which are making the cells move, and what makes a cell a leader cell, because usually in bird flocks there's no leader, but I'm just surprised that there's a leader cell here.
So the energy source, I think this is an active field of research where people have started. So see, the energy source has to be some sort of metabolism, right? The glucose metabolism and so. But the thing is, the glucose metabolism can have like 2 parts. In one way, the glucose metabolism can entirely go towards glycolysis, which is like producing the building blocks of the cells. And in another way, it can also go to the oxidative phosphorylation and producing the ATP. So in leader cell, apparently, and this is something I cannot give you a very confident answer, because people have we don't look at it, but people have started looking at it. And it seems like there is a metabolic switch in which the metabolism become more oxidative, and to make a leader cell a leader, you need to have more ATP, and this is what where the switch happens.
Oh, I see. Okay. Thank you, sir.
So following up on that question, so the leader cells are moving at a higher speed than the rest?
Initially, yes, but you see, there are two things are happening. One is that so the leaders cannot move like very much faster than the other cells, because then they will become separated from the. So that is one thing. So what happens first is the stretching of the cells, and but the way the leaders are sort of, you can distinguish from them from the other cells is that they are more persistent. So if you look into the tracks of other cells, they look like their persistence is not that much. But the leader cell, at least in the initial phase, they are very, very persistent, and as well as their immediate followers.
Okay, thanks. One last clarification question. So you labeled the first phenomenon as plithotaxis. So what is, like, taxis is motion and
Oh, well, so plitho is crowd.
Okay, so following the crowd.
Yeah, and this is not eye level. So this term comes from Jeff Redberg. So, he coined this term plithotaxis.
Okay, yeah. Yeah, thanks for the clarification.
Okay.
So if there are no further questions, then let's close the session and thank all the speakers for great talks. And we will reconvene later. So, Alok, if there are any announcements you can make now.
Sure. Thanks. Thanks, Prerna. Our keynote talk is supposed to begin at 5 o'clock. So we'll just take a quick 5-10 minute break. But I'd just like to remind everybody who's there that at 5:45 today, we are scheduled to have the discussion for SMYM 2021. So please try to be there for that. We want faculty from other institutes to please come and participate. And there were questions about the poster prizes. Those will be announced tomorrow at the valedictory function, which is scheduled at 8:30 tomorrow 11:30 tomorrow in the morning. Okay, yeah. So we'll reconvene in about 5 minutes. We'll keep the link live, but we'll be back in about 5-10 minutes.
Hey, Alok.
Basa, you are loud and clear. Basa?
Is it okay?
Beach mein thoda sa it was not, but right now I can hear you clearly.
Yeah, I can hear. I can hear you.
Okay. Your connection is a little bit dicey.
Okay, sounds good. Let's see. I'll attempt. Otherwise, you guys can go ahead.
Okay. Okay.
We will see.
Sure. Okay.
Hi, is it break time now?
Yeah, we could hear you.
Yeah. It's a break time. Yes, it's a break time.
Basa, your connection is quite poor. It breaks a lot right now. कुछ सुनाई नहीं दे रहा. We can't hear you at all, Basa. Zero.
See, I don't have a problem hearing, but I have a problem when I speak. I think the bandwidth is not enough. I believe.
Yeah, it's not enough.
Can you hear me?
I can hear you. It's a little bit choppy, but I can hear you.
Oh, you can. Okay, okay. But I think it's
better
little
than Basa.
because it's mobile.
Right. It's better than Basa's, but it's not that bad.
Okay, okay. No, see, if I switch the video, it will be a little difficult because, it's voice. I think one of you can because I want to have since.
Okay.
The participation is poor.
Ashok, are you there? Ashok, can you hear me? Basa, your voice is absolutely very poorly audible. I know you're talking, but I can't hear you at all. Dilip is still better. Ashok?
Look, I'll call Ashok.
Yeah, please. Yeah. Yeah.
Yeah, no, one switch on my video will not work. It's too poor.
Hello, Guru.
Hey, Sushmita, how are you?
Good, good. Very happy to see you here.
So you've got about 24 people, I see.
Yeah, yesterday there were more. Maybe they'll trickle in sometime.
Okay.
So there were around 50 participants for the conference.
Hi, Guru. Can you hear me?
Just about. The voice
This is Dilip here.
Hey, Dilip, your voice is cracking.
Yeah, Dilip and Basa don't have internet connection to their campus.
Suddenly we have a net in our campus.
Okay. So we are on for tomorrow though, right, Dilip?
So I'm trying to connect to mobile, so I think the voice is very sluggish. Probably it will not work.
Okay, but tomorrow we are okay, right? I'm sorry, I'm giving a talk in
Yes, yes.
tomorrow
This
morning.
is a kind of maintenance, scheduled maintenance. They should be back at 4 p.m.
Sure.
Tomorrow will be fine. Tomorrow it will be
okay.
fine.
Okay. Okay.
Hello, Guru. Alok here.
Hey, Alok.
We have the network maintenance today, but the network should be back by 4 p.m. But now it didn't come back. I'm trying to use my mobile internet, but not sure.
Sure. Sure.
So hopefully SMYM will be back to its normal track next year.
Fingers crossed. Hopefully everything will be back to normal next year.
So we are done with the online mode now. Initially, it was okay.
Well, I don't know about you guys, but I taught a class of 75 for this entire semester, and it's not fun. It's not fun at all. And the teaching is okay, but especially when it comes to evaluations and exams, it's a lot of work.
Yeah, plus you don't know the exams, students are cheating.
No, we do full proctoring, by the way. So they have to have 2 devices, their cameras have to be on, they have to be visible at all times.
Oh.
Hands, everything has to be visible. But even so, right? I mean, it's very difficult. It's very intrusive, right? I would hate to have something like that, but that's sort of what we have right now.
Yeah, I didn't do that in my course because I felt like if I asked them to do that, they might forget what they're writing.
No, this is an institute mandate. It's not like I have a choice.
Yeah.
In our case, some of the students are complaining that because it's online mode, the classes are just going on and the amount of load is very high. There are quizzes too often, and I don't think it is helping the students at all.
So we had midterms. The dean conducted a sort of a review, and the students were like, I think they overloaded on courses this term because it's all online, and they were just getting burnt. So I think it was really stressful for them, stressful for us, stressful for everybody involved.
Hopefully next semester the vaccines will show their effect.
No, so next semester for us is online. I mean, it's not yet announced in the Senate, but it's virtually certain that it will be online. So we're not, I think that's largely because of we won't be able to have so many students back on campus and then maintain physical distancing. I mean, hostels and so on is an issue, right? Our infrastructure is not really where it needs to be.
I think Sanat is also here. Looks like. By the way, Ashok, are you there? Have you been?
Yes, I am here.
Hi, Guru. Sunita here.
Hey, Sunita, how are you?
I'm good. How are you?
Hanging in there. I've got to do grading.
Where are you, in Pune or here itself?
Right now in Pune, but after my talk tomorrow, I'll come back.
I see.
Hey, Sanat,
Guru,
how was
how
your
are you?
talk yesterday?
Good, I think. Went too long. Usual. I heard you complaining about teaching online.
Yeah, I mean, teaching is not so bad. The evaluations are very stressful. Right.
Yeah, my thing, what happened was that they decided, because I'm teaching a graduate thermo course, so they broke it into half a semester. So it's twice the pace over half a semester. And it ended up that half the class couldn't come because they're all over the world because of visa problems. So I'm teaching people, it's a 2:40 in the afternoon class. Some parts of the world, it's 2:00 in the morning. So it's an insane. Everybody turns off their camera and nobody, I mean, it's like, it's a very surreal experience.
Yeah.
Yeah.
So so the teaching, so what we figured is that even with our students being all over the country, it wasn't clear that they would all have internet connectivity. So what we decided to do was pre-record lectures, put them online, and then have sort of online discussion sections. And at some point, that was too many hours of the week for them. So they complained, and we had to sort of scale back the number of minutes in the pre-recorded lectures and so on. But I think all in all, that wasn't terrible. But what really, I mean, the whole mid-semester end semester exam thing, that was just nightmarish.
So are you evaluating on a regular grading system or it's all pass-fail?
No. So at least as of now, the institute has not approved pass-fail for this semester. Okay. So we have these apps, which, once they turn that on, the exam paper comes to them through that, and it's fairly tolerant to internet disruptions. But they also have to have their cameras on, and it's very intrusive. We have to be able to see their hands and face at all times.
I mean, for us, it's been kind of insane because, there is a bunch of people here. I mean, in the US, the disparity in terms of internet access, right, is very, very large. So some schools, like my daughter, they are completely pass-fail. Okay. For us, they started out with grades, and then the kids complained, and they said, okay, we'll take 2 of your classes, make it pass-fail. I'm like, guys, just get it over with, make it pass-fail, and then tell all the employers, tell all the graduate schools that for this set of kids who are coming through the COVID era, grades don't mean anything.
Yeah.
And right, I mean, this is the mature thing to do, but it seems like it's really problematic. People don't want to do this.
Think about if you're a pre-med, right, Sanat, as an undergrad, if you're a pre-med, this is something you have to complain about. And you're going to complain about it any which way.
You are, but you see, the reality is that this year we're not accepting GREs. Okay. So that's gone. So basically, it's going to come down to letters. That's what it's going to be, right? And you can trust for these couple of years that the faculty have the responsibility to come and judge people in an honest way.
Yeah.
Right. And it requires some cooperation, but I think it's doable if we all get on the same damn playing field, which we don't do.
Yeah.
Anyway.
Yeah. So can I request Dr. Ashok to please introduce Guru and chair the session?
Okay, thank you. I am Ashok Dasmapatra from IIT Guwahati, and I briefly introduced Dr. Gurusamy. He was my PhD advisor at NCL Pune, and now he's in IIT Bombay in Chemical Engineering Department. He will talk on soft matter and industry, how this relationship between industrial problems and soft matter. So I request Professor Gurusamy to start.
Okay, thank you, Ashok. So can everyone see my screen and can everyone hear me? I guess good.
Yeah.
Good. So I wasn't quite sure. I've never done this talk before. I've never been asked to do this talk before, so I wasn't quite sure what to put down. So I've put down sort of a rambling set of thoughts, and please feel free to stop and ask me questions, because this talk's going to be more a dialogue than a talk in that sense, right? So what I'm going to talk about today is largely a very personal experience, right? It's basically what I have experienced over the last 20 odd years. And just to, by way of introduction, I just wanted to let you know that over these years, for most of this time, I was at NCL, which is a CSIR lab, and CSIR, for those of you who don't know it, is the Council for Scientific and Industrial Research. So a big part of my mandate was to work with industry and help them work through problems, right? And so over this journey, I've had the opportunity to collaborate with a wide variety of industry. And I've listed a few here, GE Plastics, SABIC, Procter & Gamble, Honeywell. These are the giant companies that are typically at least tens of billions of dollars and tens of billions of dollars in size. Mitsubishi Chemicals and so on. And then I list these other companies, ATGC and Relisys, which are sort of like startups, but not really, because they're large enough that they're talking about maybe of the order of 100 crores or so in size, and then really small companies or startups. And so the point I wanted to make is that there are models that work when you work with companies, and they might not be the same whether you're working with the really large companies. What the company wants out of it and what you can reliably do in terms of working with them might be different for large companies, sort of really slightly larger than small, and then really small companies. And I'll sort of talk through that. So, if nothing else, what I'd like you to leave with, at least based on what my experience has been, is that I see a lot of positives to working with industry. One is that the problems that you get to look at are very interesting, very challenging problems, and I'll speak briefly about that. Working with industry gives you the opportunity to translate science that you do in your laboratory and take it out of the laboratory. Most of us work at research universities, right? So teaching is a big part of what we do, but also equally important is doing research. And some of that research really pushes the frontiers of knowledge. But we all work in a fairly applied field. And we're talking about soft materials, we work in a fairly applied field. So then there is the opportunity that some of that cutting edge science gets translated into something which is of practical relevance to industry, right? And so, one of the things that certainly in our field, unlike maybe in astrophysics or other areas, something that most of us could possibly think about is something coming out of the lab that finds practical use in a product or a process, right? And therefore, I think that's something which I found very enjoyable, and I'll speak a little bit more about that as well. The last 2 points are sort of cautionary notes, and that has to do with how does one work with industry, right? I mean, most of us are typically used to working with government-funded grants, right? I mean, startup grants, DST, DBT, CSIR grants. And the point I wanted to make is that the culture that's associated with these grants, at least when you're talking about Indian funding agencies, is very different from what you should expect or should plan on when you work with industrial collaborators, right? So that's something that I wanted to emphasize. The other thing is that working with industry requires a support structure from the institute, and this is different from, most of our institutes know how to deal with grants coming from DST, DPT, and so on. They are less familiar with how to deal with grants that come from companies, and therefore that's something that I think needs to be set up if it isn't already in place. And I'll speak a little bit about that as well. Okay. So, so I'm going to sort of take you through a few talking points, and again, like I said, these, please feel free to stop and discuss these with me. So one of the things, at NCL, while it's a CSIR laboratory, we used to hire in the same way as we would in academia, right? And so you look at the brightest people, the most ambitious people in your view, who kind of fit into what the requirement was, and we would hire them, right? And so very often you're talking about people who finished their PhD, maybe worked on a postdoc for a couple of years, and have essentially experience with the academic setup, with universities, with teaching, and not so much with industry. And so one of the things that very often people would say to me is, why would industry want to work with me? I work on very, very fundamental science. The science that I do is possibly too esoteric to be of interest, right? And I'm not quite sure that is the case, and I'll tell you why that is so, right? Often, when we're talking about the research universities that we're from, we hire people who are very strong in their technical background, right? Who have a very strong set of skills, and the tools that they bring are tools that can be more widely applied as well, right? And so, for example, I talk about one of my colleagues who worked on, very fundamental method development for quantum chemical calculations, right? And one of the things she was working on is to try and understand how light interacts with certain molecules, right? And again, one of the things that she was very motivated, enthusiastic about working with industry, especially because at that point she was at NCL, and the question that she said came to me with was, why would somebody want to fund my work? So, it turns out that understanding how light interacts with molecules was something that personal care companies that worried about things like pigmentation in skin and skin coloration were very concerned about. And, to her surprise, she started getting invitations from some of these companies to come talk about some of the work that she was doing at these, right? So the point I'm trying to make is very often there's possibly aspects of your work that you might not appreciate that might be of relevance to somebody in industry. Okay. Again, I'll speak a little bit about some collaborative work that I did with my colleagues who do method development in solid state NMR, and look at how that is applied to problems in industry. Right. So I'll pick a couple of problems and I'll speak a little bit about that. And these are problems where I work with industry, but I had the freedom to publish some of those results as well. Right. Now, why would industry want to work with you? One is you bring skills to the table, and typically industrial R&D is very focused on relatively short-term deliverables, right? And they typically do not have the bandwidth to solve fundamental problems that have a longer horizon, right? Something that you would perhaps want a PhD student to work on, or maybe a postdoc to work on for a couple of years. Having said that, I mean, so one is they very often the outlook in industrial R&D is also not to look at some of these long-term problems. So I think over time they lose the ability to really conceptualize and look at some of these longer-term problems, at least in the chemicals industry as of now. And that might not have been the case 20 years ago, but certainly today I think pressures of the marketplace are much more compelling in terms of deciding what you want to solve. So while they might not be able to solve these problems or have the bandwidth to attack these problems, that does not necessarily mean that they're not interested in these kinds of results, right? I mean, because these are results that might have deep relevance to their problems. They might not want to solve it, but at the same time, they do want somebody to solve it, and sometimes they're willing to collaborate or resource someone who would want to solve these problems. So the question really is not so much about whether industry is interested in working with you or funding research in your lab. More often, it's a question of, do you have the interest or the bandwidth to work on this, right? And of course, the reason for that is that the exact specific problem that you are working on might not be of interest to the industry, but would you be willing to extend some of the tools that you've developed to look at maybe problems in similar areas, or maybe a little more applied versions of problems that you're looking at? Now, this is something where it's a very personal call, right? Because you have finite time, you have finite resources, and you can choose to use that to look at this one problem that you're very excited about, and that's perfectly fine too, right? But if you do have some bandwidth to look at some of these problems at any stage of your career, even if you're early stage in your career and you're just starting to look at problems, of course, you need to put down roots, develop a group, build competence. But if you're not averse to hiring an additional postdoc or working with some of these problems, that's certainly something that might expand your horizons in ways that you might not consider. Okay, so the other myth is, in my opinion, that industry problems are really mundane, right? I mean, they're boring. This mix and match. You take a bunch of things, you mix it together, look at properties, and that's pretty much it. And I don't want to waste my time doing that. So I'll give you two examples, right? And these are problems that I worked on many years ago. And one of them is with a large company. One of them is with a smaller company. They were funded or resourced in very different ways. And I'll talk about problems and I'll tell you why I thought that they were not really trivial problems, right? So I'll pick two out of the many examples of research that I've done in collaboration with companies. One is a problem that DuPont came to me with many years ago, probably 12, 13 years ago. And so DuPont, at that time, DuPont Specialty Engineering Plastics was in the business of looking at very high-end engineering plastics. So these are not commodity polymers. They're made in small quantities, but they're relatively valuable. And the reason they're engineering plastics is they're used in higher-end applications, right? And so the polymer that they wanted me to work with is this very simple polymer, Delrin. It's actually fairly widely used for an engineering plastic. It's probably the simplest. I call it the polyethylene of polymers that have a heteroatom in the backbone, right? So you've got an oxygen, so it's a polyoxymethylene, right? And this is a polymer that goes into making things like gears. And so, for example, in the automotive industry, you use it in a wide variety of applications. And as things get compacted in these kinds of products, they were seeing higher use temperatures, right? So this is a polymer that melts at about 175 Celsius. But what they noticed is that it started softening at much lower temperatures, at temperatures of around 100 Celsius. And so the problem that they came to me with was, we see this, it's softening much below the melting point. What can I do about it? right? It was, in a sense, a fairly open-ended problem, but with a fairly tight time frame on when I could give them a solution. So I appreciate that not everybody works on semicrystalline polymers. So let me give you like a really brief introduction to semicrystalline polymers. So polymers are long connected objects, right? So typically you take a bunch of monomers and you string them together, right? And at high temperatures, these are materials that are in the melt state. And so if you take a polymer like this, it's a fairly flexible polymer, forms this coiled structure that exists in a melt state, right? So it's a disordered structure. And as you cool it down, this is a polymer that has sufficient structural regularity that it wants to crystallize. Okay, but since it's a long connected object, there's just no way you can take this polymer chain, stretch it out completely and crystallize in any finite time scale. So what happens then is locally small segments of this polymer stiffen up, they start straightening out, and then they stack together to form these thin crystals, right? So this is unique to polymers, and it's sort of generic to polymers, is that they form crystals that are thin, of the order of 10 nanometer, 10, 20, 30 nanometer size lamellar crystals. Okay, and then these lamellae could also then stack up to form structures that look sort of like these lamellar stacks and so on. Right now, inside of these is a so if you go in and look at the monomer, this is what the polyoxymethylene looks like when it's sort of held together at the molecular level, right? So there's hydrogen bonding, and you get these helical structures that pack next to each other. Okay, now one of the things that happens in this polymer as you heat it up, and this is something that had been known before, is that these helices, while they're hydrogen bonded, they're able to start rotating, right? And it was sort of widely held in the community that rotation of these polymers resulted in them getting softer, right? And so if that's really the issue, then you're bound by the chemistry, right? So that tells you what might or might not happen, and that's then game over, right? There's not much you can do about this material. So at that point, we'd been looking a lot at polymer interfaces, and one of the things that we started looking at is to try and understand what happened at the interface. Now, polyoxymethylene is a polymer which, when it crystallizes, forms thick crystals and thin crystals for reasons I won't get into, right? So what we decided to do is to make two kinds of structures, right? So one is the standard injection molded structure where you take this polymer melt, you extrude it, and you form the structure. It forms from this melt state, which has all these entanglements between polymers. And we compared that to a model structure. This is solution crystals. So you take this in dilute solution, very carefully cool it down and allow it to crystallize, and you form these very well ordered, very similar plates. Exactly, in this case, about 12 nanometers that would then pack up to form these powders. And then we did solid state NMR, right? I told you I'll tell you a little bit about solid state NMR. And so this is what we did, right? And so here's variable temperature solid state NMR, where you heat it up from about room temperature to about 100 Celsius. And I wanted to look at, so this is carbon C13 solid state NMR. And what we were probing is the local nuclear environment around these carbon atoms in the backbone. And what you see is that if you have this helix, the local environment is different for the different carbons, right? And therefore, when you look at the room temperature structure, what you see is that you get different peaks that are associated with the local environment. So each of these corresponds to a carbon atom with a slightly different local environment, right? And what you see here, not so well, but then you can see it as it grows, is the carbon atoms that are in the amorphous phase. And so what we noticed is that as you heated this material from room temperature to 370 Celsius, I'm going to just go focus on these peaks, which are the peaks from the crystalline regions. You start off with two peaks, both in the solution crystals and in the melt crystals. But as you heat it up, these helices start rotating. And I have an echo, so maybe Sushmita can mute everyone. And so what you see then is that as you go up to high temperatures, as these helices rotate, there's sort of an averaging between these different environments, and these peaks essentially merge to form a single peak. And what's interesting is you see that for the melt crystallized samples as well as the solution crystals. Okay, what that tells you is, of course, what people have looked at for many, many years, the fact that when you heat up these polyoxymethylene crystals, the helices that form start rotating. This is of course true, right? And we were just sort of reconfirming what people saw. What's interesting is what we did subsequently, which is to look at the stiffness of these polymers as a function of temperature. And so for these solution crystals, you could do standard DMA measurements. You hold this and you sort of twist the entire structure, and you can do macroscopic measurements showing that there is a decrease in the modulus. And this is, of course, also what had been observed by DuPont. We had to then develop an AFM technique to do the same thing, and we saw qualitatively similar results. But here's the interesting bit. When we looked at the solution crystals, even though there's this rotation, what we found is that the solution crystals don't soften. Right? What this tells you is that this origin for the softening that people had postulated in the literature was wrong, which means DuPont had a shot of doing something about it. Right? Now, this is a problem that we published, I think, in 2012, way after we had done this project and we got all the clearances to publish this. But in the interim, Ashok, who just spoke and was a PhD student at my time, was doing some very interesting simulations and ended up doing a problem that was in part inspired by some of the solutions that we were looking at to address this particular problem. Right. So just to tell you that these problems are sometimes interesting enough that they can spawn off a whole set of other problems, even something which is fundamental enough for a PhD student to look at. So let me briefly tell you about one other problem, which is a problem with waste collection. Right. So I lived for many years in Pune, and there's a company called Swatch, which is really a cooperative of waste pickers that goes door to door, collects waste, and then segregates it into wet and dry waste, right? And these are people really at the bottom of the pyramid. So they take this waste and they sort it out and separate out anything that's of value. So glass, metal, clean plastics, they separate it out. These are what people from India will recognize as being from Harpic bottles, right? Like the toilet cleaner. So these are made of high density polyethylene, and what they do is to remove the adhesive labels, the paper labels, wash it with water, manually clean it. Remember, these are people who make very little money per day. They would then flake this and sell this for like 50, 60 rupees a kilo. Right? It's scrap plastic. It's fairly clean scrap plastic. And so what one of the startups that was working with this NGO said when they came to me is, can one prepare high value materials out of this rather than selling it for 40, 50 rupees a kilo? How about targeting something like 3D printing filament? And if you can make this out of waste polyethylene, then you can talk about making significantly more money for these people. It's not going to solve the waste problem, but it's certainly a way of upcycling rather than recycling or downcycling. Right? Typically, you take this, you make it into these multicolor buckets that you get in village melas, and that's really not a good use of high quality plastic. Okay, so how can one do that? So it turns out that this is actually a fairly tough problem, right? Because if you take polyethylene and you cool down this melt, the polyethylene crystallizes, and so it undergoes a phase transition. And as it crystallizes, it shrinks, right? There's about a 10% shrinkage in the volume, accompanied by a transition from a liquid-like state to a solid-like state. So there is a 1,000-fold increase in the modulus. And what that does is that to accommodate this change in volume, you have to warp to go out of plane to dissipate stress, right? And it doesn't help that polyethylene has a very low surface energy. And so when you do 3D printing, you essentially layer by layer build up this material, and it really can't stick. And so if you can't stick, you can't maintain registry as you build this 3D printed part. So just to cut a long story short, one of the things that we did is this is neat HTP, like this material. Here's the melt state modulus. And so what's happening here is as you go up in temperature, the modulus goes up exponentially. So this goes up exponentially, and that's simply related to the activation energy of the melt. So it's a jump process in the melt that makes the melt become more viscous as you go to lower temperature. Here's what happens to the solid state, and as you heat it up, HTP also softens to some extent. But you notice that there's this sort of course, I'm plotting the shear modulus for the solid state and the viscosity for the liquid sample. So these aren't really on the same scale. But the point is that you see that there is a gap between the solid modulus and the melt modulus, and that's one of the reasons why you get this very large buildup in stress, right?
Guru, I have a question, Guru.
Yes.
Hi. So this data, is it for the waste-derived polyethylene, or is it the model polymer from the?
We have data for both. I think this is for the waste derived, but we have, you see the same thing for the recycled polyethylene as well as the neat polyethylene that you can get from a virgin source.
Yeah, thanks.
Right, but if I remember it correctly, I think this is for the waste derived polyethylene. So one of the things we did is using things that we'd learned from other projects in the past, we could put in very small quantity of molecular additives that would form scaffold-like structures. It won't really change the way you process it in the melt, because the melt modulus with the melt viscosity doesn't change, but you see sort of an order of magnitude increase in the modulus as you go to lower temperatures. And similarly, there's different kinds of polyethylene. If you mix two different kinds, you can get this small decrease in the solid state stiffness, and that lets you sort of bridge this gap, right? And effectively, what we were able to show is that you could modulate the residual stress by about a factor of 10. So the end result is that you could then take polyethylene. This is actually data from waste-derived polyethylene from Harpic bottles that we got from these waste pickers. And we came up with a filament making protocol that was so robust that you could actually implement it right directly at the garbage collection center in Pune, right? And so this is work that was, the startup and the rag pickers don't really, they're not like a big company, and so they can't really fund this. So when they came to us with this problem, we went to DST, and so DST has something called a technology development board, which funds really technology development. And so we were able to then get them to fund this. There are, of course, challenges to working with DST funding. So I think they gave me my first set of money, and then they didn't give me money for several years. So I actually had to fund this out of my pocket, right? And then eventually they gave me my money so I could get some of it back. But it was really fun, right? And also something that we could publish as well as patent. And this company now has raised a large grant from the European Union, and so hopefully they have enough money to go back to NCL and license this patent, right? So just to give you a couple of examples of somewhat interesting projects that we did with industry, and to try and convince you that these are not trivial problems, right? A lot of these are fairly challenging problems, things that you can certainly publish in good journals and as well as maybe patent and so on, right? So that's a couple of examples. So if I've hopefully convinced you that that industry would most likely be interested in some aspect of your work, and that industry problems are important, the other thing that you could think about is, why should I do it, right? And this is, like I said, a very personal decision. It depends on what you really would like to do and whether you'd like to see your work being applied in some way. Or if you feel that this is not the right time and you need to focus, that's again a very personal decision, right? But here are some things that you might or might not have considered that I want to sort of bring to the fore. One is that when you work on a problem that industry suggests to you as something of interest to them, there is at least someone who cares about it, right? I mean, you absolutely know that somebody is willing to actually resource this problem, and they care enough about it that if you solve it, it's going to make a big difference to someone, right? And so then obviously that means that you have the opportunity then to translate research into applications, into something that they can actually derive value from. The other thing that I wanted to bring up is, when you go to academic conferences with a lot of other academics, in a sense, sometimes you sort of get pigeonholed into a certain set of problems, right? And I found that when I visit industry and I talk to people there, they have problems that maybe at the surface look rather mundane, but some of these are very new problems, or very different ways of looking at that problem, or that suggest a very different approach. So for me, it's been a tremendously educational experience to talk to people in industry. It has really broadened my horizons to a great extent. The other thing which I hadn't realized when I started this is how much it helps my teaching, right? I teach core courses, I teach electives and so on, as I'm sure all of you do as well. And one of the things I found is that when somebody asks me a question, when I cite an example based on something that I've done, students absolutely love it, right? Because they can then see the connect, especially if you're teaching these hardened undergrads, right? And they're like, what who does chemical engineering, right? It's like, there's lots of very interesting things one can do to save the world, right? And when you're talking about problems of sustainability, power transmission in terms of novel materials, energy savings from membranes, and you give them solid examples of what of where science can translate into real products and into technology, because very often engineering undergrads care about that, right, about technology. And if you give them that, it really excites them. So that's one of the things which is sort of a side benefit, but I really enjoy what that brings to my teaching. And other issues are that if you're running a group at some point and you're really worried about where your PhD students are going to end up, not everybody goes to academia, not everybody wants to go to academia, and academia is not necessarily right for everyone, right? But one of the things you find increasingly is that when you talk to most graduate students today, and in my department we have 225 PhD students at this time, right? This is chemical engineering, right? A very large fraction of them say they want to go into academia. Now, part of that is also because there isn't, I mean, I don't think they know what else is out there, right? And so it's clear that not all of them will end up in academia. Exposing them to industry problems, getting them a sense of what the challenges are, and also having contacts will be interested in talking to somebody from your group is really good for your group, right? It really helps them. The last two problems are sort of, I mean, I'm not sure how important that is, but it certainly is sometimes very helpful. In India, DST grants or government grants come with very, very stringent norms on what you can do with the money, right? Sometimes you have the money, you can't spend it because you've got so many rules you're tied down by. So industry funding typically is given to you because they want you to solve a problem. They don't care about whether you're going to move it from one head of spending to another. That's not typically something that they care about. And so that flexibility is sometimes very, very helpful. The fact that you might have some money that you could move around and make actually move things in the lab a lot more efficiently. And that's something which is very nice. And in these times, of course, universities love to say that they have industry collaborations. Deans and directors and universities love overheads. And therefore, bringing in industry money might also mean that they take you a lot more seriously and pay more attention to you. And sometimes that's not a bad thing. It's sometimes not a good thing either, but most of the times it's not bad. So one of the things that then you might want to think about is, sure, this is all fine, but I have no idea where to get started, right? How do I get started? How do I meet these industry people and start working on these problems, or even know what these problems are? Now, when I joined NCL, right? So as a PhD student, I'd already worked on problems where I would present at that time, for example, at the American Physical Society meetings, you'd have a lot of people from industry, a lot more representation than I see perhaps today, right? And so you have the opportunity, and I'd visited many of them, given talks at many places and so on, right? But those were all contacts in the US, right? One of the things that really helped when I came back to NCL and CSIR is the number of people who had these connections and who were generous with their willingness to help me make those kinds of connections, right? Take me with them when they went to meetings, introduce me to people and so on. So that is actually a very effective way to talk to colleagues who have these connections, to get them to introduce you. The other thing that I learned when I first joined NCL is that my director, who sort of really was a very generous mentor, generous with his time, sort of told me that I should take the time when I was setting up my lab to go around, give talks all over the place, right? And he said, including at universities, just so that people know that you exist. And this is important, right? We underplay the importance of this, but it's important to know people, and to know for people to know that you exist. I mean, these would be people who sit on funding panels. But if you're going to go visit, let's say, Bangalore, right? Maybe find out if there's somebody who knows someone at Unilever or SABIC, and get them to invite you to give a talk, right? And oftentimes they're not averse to it, right? You're paying your own way. You just come there and give a talk. They'll pick you up, have you come and visit, and maybe take you around. And so I was very shameless in getting myself invited to these, and I think I'm happy that I did that, and I made a lot of friends that way as well. The other thing is very often running these short training programs for industry is a really good way of meeting a lot of people, right? Again, this is something that I first learned at NCL. NCL would run these polymer training programs for industry, and I didn't quite see the point when I got there. These 5-day, 1-week programs. I said, why do you put in time to doing this? And very quickly saw the payoff, because this refresher courses actually bring tremendous value to people who've not looked at their textbooks in a while, right? It's something which you have to put some effort into making this tight 1-week program, but at the end of it, they really remember you, right? It's amazing how those programs then quickly give you a very extended network of contacts in a range of industries. So running these kinds of training programs on, it could be techniques, right? How do you do scattering? How do you do diffraction? How do you do thermal analysis? 2-day program where you invite a few people to your lab and train them and get your graduate students to do some of that. Some of this has a lot of, it has a lot of impact for people in industry. Talk to them at meetings, perhaps invite them to meetings like the Young Investigator meeting, because as much as you have young early career researchers in academia, you have them in industry too. And I'm sure they would also enjoy making these connections. And so that's something I'd strongly recommend. I hope most of you are coming to the Soft Matter meeting next week, ComFlu. We, as of just a few minutes ago, we had at least 250 registrations, mostly from academia, but you also get a lot of people from industry. And these kinds of meetings, and I hope we have the opportunity to get more people from industry to come. These are great places to meet. These are sort of neutral meeting grounds for you to start meeting with some of these people. The other thing, and I'm not sure how much you will enjoy this, is to go to things like industry trade shows, conclaves. If you work in the area of polymers, Blast India is something that no academic typically goes to, but everybody from industry goes there, right? Or if you're in the US, Antech meetings, right? As Society for Polymer Engineering meetings. So especially if you're sort of early career, I think these are good meetings to go to meet people. And of course, you go to these meetings, you can't sort of hide in a corner. You can't be shy. You have to go talk to people, right? And that's really important, right? Most of us have now industry teams that visit our universities and departments. So take the effort to go meet them, give them, make presentations to them. And the other way of doing it is also connect to these people through alumni, through batchmates. And so, you have to sort of do a little bit of self-promotion in terms of giving talks and letting people know about the kind of things that you do. Okay. So I think it is possible. It does take effort, and that's effort that you need to decide on whether it's worth it for you. But again, at least in my case, I found that this was extremely valuable. Ashok can tell you about the fact that our group was never short on funding when he was a student, right? Continues to be that way. So the other thing is, sometimes you can say that I've spoken to them, but they didn't seem interested. And we had this again at NCL, is when we would have teams of these people visit, and the strike rate isn't necessarily very high. It's about the same as what the strike rate is for DST proposals today, though, right? Because competition has got fiercer there as well. But I think, persistence and, figuring out what your elevator pitch is, right? To talk to them and tell them, you have to also tell them about things that they might be able to relate to, right? Or in language that they might be able to relate to. You can talk to them about your problem in a language that they can relate to. And so that's, again, very important to get them to talk to you, right? How are we doing on time? Okay, we are way over time. So let me, I have a few more slides. So let me keep this brief, and so that we have some time for questions. So when you work with industry, there's different ways of engaging with them. One of the ways which is common is when you have somebody who comes and defines a problem for you, but this does not need to be the only way, right? So this is, for example, the way DuPont worked with me. They had a very well-defined problem. They came to me and said, can you solve this for us? And so those are sort of short-term engagement. There's an immediate burning need that need you to solve. But sometimes, especially, for example, if you're looking at where industry can pitch in some money and the government puts in money, you can also look at longer-term collaborations where they might be open to funding a PhD student. So this is a 3 to 4 year commitment, more open-ended. But you have to think about, whether they're open to publications and so on. Something that I do a lot nowadays is what's called a retainer, where companies work with me, where I don't do any experiments for them in my laboratory, but I speak to them and I give them advice. The other mode is where you might have a technology solution, something that came out of a DST project, and that's possible. I'll give you an example. And you then think about licensing it or transferring it somehow to industry. And then there are other problems where you can talk about something that you're interested in, get an industry that's involved, that's interested in that, and then jointly go and seek funds to work on those kinds of problems. So just to give you a concrete example, so like I said, the DuPont people approached me saying, here's a problem we'd like to solve. What can we do about Telrin softening? And that was one way that we worked with them. These are sort of examples of other modes. And in India, there's actually a variety of government funding options, especially if you can get somebody from industry involved. And the strike rates there can be higher. And very often they tell me that they don't get sufficient, they don't get enough applications for these grants. So for example, for the 3D printing work that I talked about, this is a problem that these NGOs came to me with, but they couldn't, of course, resource something like this. And so we jointly applied to the Technology Development Board for a grant and that funded that work. There's other kinds, for example, if you work with a company, then the company can get something called a biotech ignition grant. This is something that the DBT gives to fund, and some of that they can then use to fund work in your lab. This is actually work that was developed. This was work that we did in my lab, very fundamental work looking at phase diagrams of ternary systems, ternary amplifiers. And this is a cool movie. I love playing it. So here is a drop of water on a lotus leaf. And when you formulate it with some of these surfactants, you see that it sticks to the same lotus leaf, right? And why is that important? Because if you want to develop a pesticide and you want to spray something, it's actually very hard to get these sprays to stick to plants. And so we ended up transferring this technology to a company. And even just the upfront payment was more than what DST paid me for 3 years of research on this, right? So there's opportunities in that way as well. Okay, so just different modes of doing it. Yeah, so I'm not going to spend a lot of time on this, but one thing I wanted to sort of talk about is in terms of how you cost the project and how you cost the time, because oftentimes your dean will not necessarily tell you how to do this, right? And that's something which you need to be careful about. Very often people will look at like a JRF salary and say, okay, I need 1 year's worth of JRF salary and a little bit of money for consumables. But that's really not a good way of costing for a project. You really, remember that you work in a publicly funded institution, or most of us do anyways, and therefore you need to cover costs so that you don't end up sort of subsidizing them, the industry, for work that you do in your lab, unless of course your university really just wants to show industry collaborations and there's sort of an intangible benefit to the industry, to the university. Other than that, you really need to account for manpower costs, overheads, instrument charges, your time, right? Because you're spending time on it. And who owns IP? Will they let you publish some of that work? Will it be owned by the university, or will it be you owned exclusively by them? A lot of that goes into deciding how you cost a project. And that's something which very often, your dean will tell me how much it's going to cost, and we'll approve it. So a couple of points I wanted to make before I come to an end is that when you work with industry, you need to have an agreement in place, right? It is not sort of an informal, we talked about it and we just go ahead, because it takes time and effort to do an agreement, but this is absolutely essential when you work with industry, right? Because it clearly defines what you're supposed to do, what they expect you to do, what they will fund the research, and really outlines their expectations as well in terms of what will come out of it, right? This is something which is, you might not see the relevance of this at the beginning of a project, but I've learned that it really saves a lot of heartburn, and it protects both you as well as industry in terms of especially in a project where you find something really interesting, you want to publish it, and they say, oh, we own it, right? And there is no agreement in place. It doesn't help them because they can't tell you not to publish it, and that really hurts them as well. So very often you might start off with something like a non-disclosure agreement or a confidentiality agreement, and then go on to a project agreement, which then you need to spell out things like what exactly you will do, what timeline you will do it over, schedule of payments. You don't want them to pay you after all the work is done. That's how are you going to resource the work? Who owns the intellectual property that comes out of it? Confidentiality. Can you give a talk about this work? Can you publish any of this? And all the things like liabilities, right? And again, I hope most of the institutes have decent legal support to look at these clauses, because suppose they take your advice and do something and it doesn't work out. Are you then personally responsible for all that, for whatever losses that they have, right? And you might not think about it now, but if they come at you with a lawyer saying that you owe me 15 crores because that's our loss on this project, because we actually tried doing something that you suggested to us, you might want to have liabilities that are limited, or certainly not personal liabilities in these, right? The other point is, very often, industry legal teams will come to you and say, here's our standard agreement, everybody else works with it, why don't you? You're not really bound to do that, right? I mean, these are typically open to negotiation, and the terms are open to negotiation, and you should be very careful when you enter into an agreement of this kind. And hopefully your deans and legal advisors will help you with some of those aspects as well. So again, just a very brief thing to talk about the cultural differences, because with DST, SERB, DBT, typically what they look at is, you come back to them maybe after a year and a half, tell them what research you've made, you found something really interesting and you decide to pursue that, and you convince the committee that that's okay. And here's a financial statement. This is what we use under different heads. That's pretty much what they're looking at, right? But in DST, in industry projects, there's a lot more involvement, right? So typically you talk to them constantly, maybe every week, maybe every couple of weeks, so that they really know what's going on, because they're really involved in some of these projects. And therefore you need to very carefully define what the deliverables are. What do you need? What do they need from you? And how do you sort of, at what time frame do they do that? And you have to really stick to those, right? These don't have to be written in stone, but you must have mutual agreement, preferably written down, when you sort of change some of these things. Okay? So anyway, so I'm going to leave it at that. And so just to sort of summarize that, in my opinion, I think this is something that works really well. We don't do enough of it, I think, in our country. But if both industry and academia get something out of it, then this is something that works very, very well. And to some extent, that depends on sort of due diligence, right? So we need to sort of understand what their requirements are, what they're really looking for. And there's no guarantee that they can articulate this very, very clearly when they first come to you, because they might also have a certain expectation of how they interact with other people, and they might apply that to most academics, and maybe we look at it very differently, right? But if you can sort of iron out those issues, then with sort of the right frameworks, with the right institutional support, and that's what I meant with knowledgeable deans and legal staff, then you can get this entire exercise to work really well, right? So that's all I have for now. I'm sorry I went way over time, but I'm happy to take questions and talk about things that you're interested in. Thank you.
Hi, Guru. Thanks for a very nice talk. I really enjoyed it. I'm sure everyone did as well. Any questions for Guru? There's one question, Satyendra, who asks, how can we approach to industries easily? That's what is a question.
Yes, I right on that. Right? So we'll go back to that slide. The most effective way is if you can get someone who's worked with them to introduce you, right? And this is something. So, for example, I talked to you about this colleague of mine who did quantum chemical calculations and would normally, in sort of the normal course of what she did, would never meet industry, right? And sometimes if you've been around the block a few times, you sort of make the right connections. or they're visiting someplace. You pick up the phone, call someone, say, listen, here's my colleague, very bright, very interested in doing some of these things, really wants to come and visit and give a talk, and that really works very well, right? So in my opinion, that's the most effective way. If it's very hard for somebody to say, somebody's coming to visit you, will you host them for an hour and let them give a talk? They won't say no, right? What do they have? Everything to gain and very little to lose typically, right? So that's very effective. So visiting, talking to people at meetings, talking to people at their laboratories is something which works very well. Today you have a lot of industry also looking at who've realized that they can't do everything in-house, and so they're looking at forging collaborations. So for example, I know that CII, possibly FICCI as well, keep running these discussion sessions on how do you build these academia industry collaborations. So it seems like there is desire on both sides, and there's just this barrier of not knowing how to go about it, right? And so I think where if you can take the effort of whenever you travel, or in your city or wherever you're at, right? If you can get somebody to make an introduction saying, let me go visit them, give a talk, what do you lose? You're going somewhere, giving a talk, you might get some feedback, and you might end up striking a very interesting conversation, right? So I talked to you about companies I've worked with, right? Some of them I've worked with the same person in 3 different companies, because as they move, they say, oh, this is somebody who gave us a lot of value because it was very useful speaking to this person. Let me try and get them connected here, right? And that helps, right? Because I think there's a lot more lateral mobility in industry. And so suddenly you'll find that you've got connections in different companies because that same person's moved around. So I don't know if that addresses your question entirely, but in my opinion, that's sort of that's the easiest way of making a connection happen, right? And people are willing to, right? You to go talk to colleagues in your department or elsewhere saying, hey, I'd like to visit someone, give a talk. And people are really, I think, reasonably willing to write an email or make a phone call.
Basa, can I ask a question?
Yeah, please, Sushmita, go ahead.
Guru, thank you for the very nice talk. It's actually motivational, inspiring. So what I've noticed so far, especially with Indian companies, is that we have long chats, long discussion. They seem to be interested, and then after that, it doesn't go anywhere. So I've had this experience at least with 5 to 6 companies and national organizations so far. I know, like you have noted that the strike rate is not good, and then be persistent. But I don't know, like if there is something that I should be doing so that like the collaboration can get started even at a very small scale.
Yeah, so at NCL we used to jokingly call it the Swayamvar process, right? You have all these people coming and we sort of go talk to them, and eventually somebody gets picked and everything. But hey, so that's sort of a joke. But I don't think there is an easy answer to this, right? Sometimes it has to match, right? And sometimes it helps to give them a flavor of the tool set that you have, right? Because they might not relate to that specific problem that you're talking about. Because very often we go and say, okay, here's a recent paper that we published, and here's all this cool stuff, and they're not tuned to necessarily looking at it quite that way, right? And so then if you tell them, okay, here's a set of tools that we use. So for example, I do a little bit of optics, right? Rio optics and so on. But I had a company who came and told me, tell us how to measure birefringence, and we will, hire you as a consultant to do that. And it's not something I would have talked about, but it's something that they really needed. And at some point, I had mentioned to them that this is something that I have expertise in, and that's one way by which that worked out. So sometimes not just sort of giving them a broader flavor of the things that you can do in your laboratory, the kind of capabilities you have, that helps as much as just telling them about this one specific result that you have, because they might or might not even relate to that.
Yeah. Many times I feel like they don't have the power to make a decision. I don't know, maybe I'm wrong, but that's the impression that I get. A lot of bureaucracy, and maybe they're looking for some member from outside the country for making the decision for them. Not sure, but yeah.
Yeah, so there's that as well. You have to be speaking to people at the right level who can take decisions, but it's hard to say. Sometimes they've got a mandate to solve this particular problem, and if you don't fit that bill, it doesn't quite work out. But you're right. I mean, I think it does take some effort. I think there is a sort of an activation barrier, right? It's one of those things that gets easier the more you've done it because people know you.
Thanks.
Some more questions for Guru? Sanath, you have something to say?
Sorry.
Sanath, you're muted.
Sorry, I just realized. I mean, you've talked about, the Indian milieu, right? And I'm looking at it from a different perspective where we go talk to industry and the price points for them typically tend to be very high funding stuff here, right? So they will only come to you if things are very targeted. If they want to learn about birefringence, they just go hire somebody rather than pay me to do it because the price point doesn't make sense for them. So I think the equation for you guys is different. And I think you've done this very well is you've talked to American industry very well and said that, if you come to us, we can do things for you at a price point that makes sense for you and makes sense for us. So that's an extra advantage you guys can leverage. And I don't know if you can talk about how you do that or whether that's an entree point for many people to walk into from where you're looking at it.
Yes. So certainly that has worked. I think it's in terms of price points, I think so my view is that Indian academia actually underprices even to the point where they're subsidizing, and I think that's not correct, right? And I think that's deans being lax, in my opinion, not really understanding what it costs to do research, and doing that in a publicly funded institution, I think is not the right thing to do. But having said that, yes, it is a lot cheaper to do things here because manpower costs are a lot lower. My overhead structure at universities here is a lot lower than what you pay at Columbia, right? At NCL, it was about comparable, and right now I think the current situation in CSR it's much higher than what you would. The overhead rates are much higher than in US industry, and that's making them price point not so competitive. But in Indian academia, it will be 20-30%. Right, and some places probably you can even negotiate that with your dean. So that makes it makes it much cheaper. But having said that, there is the disadvantage that they don't know you, right? They've not met you, they don't know where you're from, they can't get into a car and drive to your place. So it sort of balances out to some extent. For me, it's worked because I spent a lot. I was trained there, and I met a lot of people in industry when I was a grad student, right? So I had a fellowship that allowed me to travel to industry, and I ended up making a lot of friends in industry, and some of those continue, right? Also, 20 years ago is when, for example, GE set up their first large R&D center here, and everybody was then looking at India as being a place where you could move R&D to. There's sort of more equilibrium now, but I think the point that Sushmita made is they've now set up more development centers here that don't have a lot of autonomy. But this is a process, right? I mean, some of these equations are going to change over the rest of my career and certainly the rest of their careers as well. But what's happened when people set up centers here is they're now saying, oh, no, this is already too high a price point. That's ridiculous. I think we really, really undercharge, right? And I actually end up facing this a lot now, saying, this other IIT and other places up here, we can get this done for much cheaper. Like, go there. I can't help you, right? So true, I think, but more than that, I think it's flexibility on IP, which I think at this point, Indian academia is more flexible on IP than US academia. I don't think it's the price point as much as it is. It's also flexibility on IP.
I think there's a follow-up point to all this, which is this issue of visibility, right? I don't know you. And, we can complain a lot about the pandemic, but one of the things it has now created is that Zoom is now a perfectly accepted alternative, right? So the kind of things you did at NCL, you can do virtually, and that'll have a huge impact, I think, in terms of getting to be known. Okay. So over the last few months, I've been running webinars, and that has been extremely successful. You do short 2-hour bursts and you get associated with it, but also people are able to see it from all over the world.
Yeah.
I mean, that might be a really nice forum for you guys to start thinking about advertising what you have, right? And sort of focusing on things that are your advantage. Like you said, IP is more, and regardless of what you say, the cost of people is lower. So all those things you can advertise, and maybe that's the way to enter this marketplace.
Yeah. And so I don't know yet, right? Because all said and done, when this whole thing blows over, at some point it will, we might have fundamentally changed the way in which we work, or we might just bounce back, right? There's something to going out to lunch or dinner with someone, right? I mean, it's very hard to do that over Zoom, right? Especially when you're doing this sort of thing. If that already exists, so it works for me because I know a lot of these people. I've talked to them. I've been to their places. They know me, and so that might work for me. But I'm not sure. I don't yet know if we've really moved to a new normal where people will be willing to start a new relationship entirely on that basis. I don't know. I mean, it might work, it might not. But the point about webinars is very well taken, right? I think this is an opportunity for us to be a lot more visible, and maybe we need to have a more concerted effort in that direction as well.
Hi Vasa, can I ask you a question?
Yeah, please, Sunita, go ahead.
Yeah. So, Guru, I have a very specific question to the system that we have here at ID Bombay. Right? Many times we get these consultancy projects through IRCC, and it seems like there are certain sets of requirement that is listed there. But me as an PIA or as a group member, I can just contribute to one set of expertise that I have, let's say rheology or some kind of characterization in terms of some measurement. How does that work? Like, do they go to multiple PIs, and can multiple PIs be part of one consultancy project?
Excellent question, and I'm sorry I didn't address that. I should have thought of that. So the DuPont problem had people. I mean, I can talk to somebody who does solid state NMR, but I can't do it, right? So the DuPont project had somebody to coordinate, which was me. And then I roped in a bunch of people. So industry wants you to solve a problem. They don't want you to contribute to a little bit of a problem. So if you can put together a team of 3-4 people and they're willing to work with you, and with every other collaboration, there has to be that sort of frequency matching where people are willing to work together. I think there's a lot more value to be delivered in that. And I think really the big strength of working at NCL CSIR was that we could. It sort of got built into the culture, and so that's something that I sort of grew up with, is knowing how to just go to a colleague and say, listen, I really need I need you to help me with this. Can we work on this together? And with mutual respect and mutual confidence in each other's abilities, I think that the value that you deliver with that is much higher.
How does the documentation work? Is it a difficult process, or it is if one 3-4 people mutually come together, then it can be done without much of a?
All from IIT Bombay, right? You can be the PI, and I don't think internally there's an issue, right? I mean, you just agree on how that is to be done in terms of resource allocations and so on, and you just work it out internally. So, for example, on that project, I signed off on everything. Right? So everything had to be signed by me, but it was pre-decided what would be done.
Good to know. Thank you.
More questions for Guru? So Guru, what impressed me the most was the list of industries that you have worked with. The list was, going on and on and on. I mean, it was taking almost the entire page. So what I would say is, if somebody wants to work with an industry, just work with Guru. That'll help, right?
So I'm happy.
I just stopped myself from saying that, actually.
It was a really impressive list of industries you have worked with. That's I think that is a testimony to the fact that we have chosen the the right person to talk about this particular problem, right? So, yeah. Any more questions for Guru? So anyway, now Guru is at as a I'm sure Ashok could have mentioned, he's at IIT Bombay Chemical Engineering. So you could of course write to him and then get some more advice on
You could have
all
written
this.
to me when I was at NCL as well.
What is that?
I mean, you could have written to me when I was at NCL as well.
That's true, as well. And I don't know if Ashok made this point. Guru was one of the person who was responsible for SMYM, right? I don't know if that point was made. Guru along with Sunil, Ranajoy, as well as Apratim, right? Right, Guru, you want to mention?
Yeah, so I'm actually delighted at how far this conference has come. So when we set it up, it was really a conversation we had at one of the Conflu meetings where Ranajoy said we need to have a different model for a meeting. We have so many young PIs in the country. We really need to have a forum where they just come together. And the first SMIM, we sort of said that we will, you sit in this hotel room for the entire day, but we will not cover dinner because we want you to go out and meet a bunch of people and talk to each other, right? This was in Pondicherry. It was beautiful weather. I made a lot of friends, and I think the whole spirit of the SMYM is, I think there's a lot of learning that we can share about experiences, and I'm really delighted that it's sort of continued and grown stronger over the years.
Let me ask you guys a question. This journal Soft Matter, are they funding you every year? Is that something they do regularly, or is it a one-off? Or have you talked to them about that?
I think they've been typically doing the poster awards.
Okay. And how much? I mean, is there a need for money? Is there something that we can go and make a pitch for? Because that's something we can go talk to Maria about. Because obviously she thought it was important enough to show up yesterday, right?
Yeah, I think we were kind of talking about it, thinking, can we do this as an international event? Like we have been doing. This was a 7th meeting, only mostly about Indian young investigators. So we were thinking, Alok and all of us, at some point that can we do this as an international event, and let's say international young investigators meet, and then do it on a little bit bigger scale. Have people from Europe, US, China, Japan, everywhere in the country. So I think if that happens, then maybe we could look at a little bigger scale event. Maybe then Soft Matter could be more involved in terms of financial support as well.
I mean, I think this is, again, like I told Guru, an excellent time to do it.
Yeah, I think so.
So you should make a pitch, and if you put something together, I'm happy to push for you with Soft Matter.
Okay, so maybe we'll just, anyway, there's supposed to be a meeting about the next SMYM, so maybe we'll have a discussion and then take a call and get back to you. So yeah. So any more questions for Guru? Otherwise we'll close the session formally. And yeah, thank you, Guru. It was really wonderful. I mean, I think I'm sure the industry connect will definitely grow stronger for sure. So we also had this idea of having a few people come and talk about industry academia connect disconnect kind of a panel discussion, but somehow we couldn't have it this year. I think that would have been.
If you've invited anybody from any sort of young investigators from industry to this meeting, because I think that's important too.
Yeah.
Because this is another, these are people whose careers are going to go another 20, 25 years, right? So you want to have people make connections. So for them too, right? How do they know whom to reach out to? True. If they have this community, it's very helpful for them as well.
I think it's a great idea. We will do that. I'm sure the next set of organizers would take care of this. Yeah, I think we've had a few speakers earlier. I mean, last a few meetings, if you look it up, I'm sure there was someone from Samsung who had given a talk in one of the SMYMs and all that. But yeah, maybe we should specifically look for some more, so that at least we have a reasonable participation than what has happened in the past. So yeah. Okay, so thank you, Guru. Again, I know you're busy with organizing Conflu, everything, but in spite of that, you could really take some time and then talk to us. So yeah.
Hey, so I hope most of you show up at Conflu.
Oh no. You don't have to
So I have to plug for Conflu as well, right? So please register and send in your talks if you haven't yet done that. So we've extended the deadline until Sunday, but hopefully I'll see most of you next week as well.
Okay, sounds good, Guru. Yeah, thanks so much. Yeah.
Bye-bye.
Bye-bye. Bye. Bye. Alok, do you want to take over for the next SMYM?
I guess we can continue together. All of us are here. Okay.
You want to go? I can get this if you want. Yeah, so Alok, you want to start?
Sure. Okay. So, welcome to the last part of today's different meetings. So, the last part is SMYM 2021. Now, SMYM 2020 was supposed to be held in May, and usually this conference is held in the summer, and then December Conflu follows. But this time, obvious, this is an extraordinary year, and we didn't know what to do, and we were not sure whether we can hold this conference at all. But thankfully, we have been able to pull this together, and thanks for all of you who have contributed and who have given talks. Thank you very much. And now we have the next. The mantle has to be passed on to the next set of people, and the usual. The tradition is that from the speakers, there will be people who will volunteer for this cause and take it over, and then basically this just gets passed on. I guess we usually like to host this in a location from where you cannot escape. Last year it was at Shillong, where it was an amazing location and a small and close group of people. So this is not a very heavy conference to organize. It's relatively light. The whole duty of the organizers is to make sure that you find the young people who are just coming up to the academic scene in India, and you bring them together, and it's basically a way to bring the critical mass of young investigators together. So this is a conference, I would think, having been involved in some other conferences, this is a much easier conference to handle. One track, that's usually the way this conference is handled. Not multiple sessions, one session, only invited talks. They're not like 10 minutes or 15 minutes short talks. They are usually longer, and the idea is to engage the young researchers for longer and to make sure we understand how the research is. So that's why this is a 30-minute talk that we try to do. And we have followed the same format, and the students, of course, come and give posters. So that was what I wanted to add as an organizer. Basa, Sushmita, you want to add something so that they feel?
So, I mean, I think that the point that was made earlier, do we really want to have should we go for a international, soft matter young investigators meet? If, that is what we want to do, then I think we should think about it, and maybe online version itself, even if things go, well, and, we are not sure, right? We are not certain how things are going to shape up. So if we decide to do an online, soft matter young investigator meet, I think that this is a time to decide, and then maybe start working towards a program for an online event, because at this point we are not sure whether it's really going to be a offline kind of an event, right? So maybe we could discuss about that, and if that is taken care, then of course we would have to get hold of some folks who could.
That can be for a later, or that can be a separate event, and not necessarily this soft matter young investigator meeting. Because I really like this conference, especially when it was in the in-person mode last year, because I personally did not know anyone in India. So for me, it was like I got to meet all of you, and I made friends. And I came to know about the communities, which I wouldn't have been able to do if it was on. If it was online, it's more passive. So I would like this to be as it is, and maybe increase the number a little bit more. Of course, because of this online thing, it was a little bit less this time, but last time it was more than that, right? And this international thing, we could maybe take it as a separate thing. It can be a 2-day event where we are like, where there are international international speakers as well, and that can be an online thing. That is okay.
I also had a suggestion along similar line what Susmita was telling. So maybe because now we are living in this online mode, we can try one like next year most probably online and see how the participation and everything is, and then hopefully after that it will be more physical conferences, then we can take a call. But to keep it as a small group is definitely much more enjoyable. Like we get several platforms to talk with the international people, like we go for APS and other international conferences are there. So this is kind of a nice forum to get to know people within our community in India.
No, I think we should definitely keep it as an SMYM dedicated to folks in India for sure.
One model to look at is the alternate years. 1 year you do international, 1 year you do kind of national. That could also be. See, right now your participation is also very less. So I think if we do it like 2 years once, national one, maybe we'll catch more people.
That's also a good point.
Dilip, we keep participation less deliberately. Right? Within 100, we keep them. Since the inception
number of
of
talks
this
is less, but participation can be increased. Number of talks is limited, but the
I think we keep. I mean, within I think within 100 to manage the things well. This much I can remember since the inception. Right. There will be a small group so that even the talks are less, but you can chat with each other. You can make a group, so more interaction. Keeping that in mind, the entire participation that I think within 100 that was being followed.
Yeah.
No, so one thing.
But you see, we never rejected an abstract, right? Whoever submitted abstract for poster or talk, we try to accommodate as much as possible. Right? If talk cannot be accommodated, we convert it to poster, right?
Yes.
So,
I mean, that's one of the nice things about SMYM, right? We have never said no to any fact that comes in our way, and I think we have not done this year, none of the years. So always accommodative, and we have even gone on to sponsor students as well as the faculty if they don't have funds to come. So I think that in that sense, I think it's a great thing, and I mean, either every other year, if you want it to be international, we could discuss that, or every 3 years is okay, whatever. I think at some point to go international, I think it's an idea that we can discuss, and if there's a way to do it, we should do it.
But every year it should be online, definitely. I mean, I do not see any possibility to have a physical meeting next year.
I also think so. Yeah.
So the organizers should plan well in advance. It's online. I mean, offline, I don't see any.
See, then the suggestion makes sense. So if the next one will be online, so arranging international SMYM would be good in online mode fast.
Or you could even keep one session which is international, right? We could introduce the international aspect slowly. So
I support that. Rather than entire symposium like international, I prefer to this arrangement. I mean, which is currently being followed. Maybe what Alok said, the one session can be dedicated for other speakers from other countries.
But that will not give a good signal. We can't say that, look, we'll have SMYM, but one day we'll have only people from
we'll arrange. We'll not say that openly. We'll arrange accordingly.
The time management will be complicated, so it has to be in the evening session.
Yeah, so that's another problem. Yeah, you're right. So there's another problem with that.
But see, if you look at Conflu talks now, there are people from all parts of the world, and they're able to participate, right?
Yeah. But so they cannot participate in all hour. Like, or if, for example, from Indian side, people are presenting, they may not be able to participate because of the time difference and all that.
That's true.
Their talk has to be scheduled only in the morning or late evening, something like that. And if they're European, then we have to do it accordingly.
True.
But we can try. If we are sure that it's going to be an online thing this year, then I think it's good to try.
Yeah, I think
I don't have a
I
doubt
think-
that it will be online.
Yeah, I also am very
21.
sure it's going to be online.
Alok was very optimistic.
No.
Some conferences are restarting, like ICTAM is restarting in summer next year.
Smita,
So supposedly,
that's because Alok wants to just say organize, and then he wants to go and have fun. So no, sir.
So yes, not a lot of panelists are here.
so usually, I mean, we'd have two institutes to volunteer, and then of course they always get help from the previous organizers. So whoever wants to volunteer, we are always there next year as guiding and give all our inputs, whatever we could, even some financial help. So we got a lot of help from the previous organizers. I
am tempted to take the responsibility, but I just want to give a warning that I've never organized any conferences or any meetings. So then I might need a lot of help from. Okay.
This is my first. This is my first proper conference, and in India, when I came in, e-SMYIM was one of the first proper conferences I went to, and this is the first proper conference I've organized. So no worries. I think it went on okay, I guess.
Okay.
And I think it's good, no? If he's willing, I think let's fix that.
But there has to be
one more.
two institution, yeah, and preferably close by or who can coordinate.
So one is Sunita. Let's fix that, and then the second one, let's find out.
So Sunita, another to help maybe.
She can suggest. Sunita, you can suggest somebody.
I see somebody from IIT Bombay, Shobana Kapoor.
Yes.
Yeah.
You got me. Well, if I mean, as Sunita is here, so I can also pitch in, and so then at least two people from the same institute might be good. If something goes haywire, then at least there's a backup. Yeah.
Two people will be needed for sure.
Yeah. So I can be with Sunita for sure. Yeah.
So if it's an offline one, there will be more number of volunteers are needed. But for an online, we thought that 4 were enough, and we took help from 2 other volunteers.
Okay.
So, anyone else in the panelists who want to volunteer, if you want to come forward, please do. Otherwise, we're going to pick people, right?
But there are not a lot of people to pick from, Vasa.
Yeah, I know. I see Danny.
Yeah, I was going to say.
Hi, Vasa.
We want young, dynamic Danny.
Yeah, I can help around, but I'll be job hunting soon, so I don't. Yeah.
You can think
it
about
might
it.
actually be good for a job hunting in a sense.
Oh, he'll be busy.
And
yeah,
I see Ravi Kumar Pujala. There's Priya from IIC again. See Kumaran Lab, right? I mean, Priya is also in the same.
Yeah, I mean, we met in Kumaran's lab itself. I can help out with Danny, but I'm also in the same boat, job hunting next year.
Okay.
Ravi might be a good thing, no?
Ravi might be a good choice.
Yeah, if there is nobody else, I'm interested to do so.
Oh, good. Done.
Yeah, and also there are other folks in ICER. No, I see ICER, there is also Dilip.
Yeah, we have 4 faculty from ICER Tirupati.
Yeah, I mean, and of course, as Alok was saying, I'm sure all of us would be happy to help you out for sure. So, I mean, Danny and Priya as well, whatever role if you think, you want to play, that will be great. I mean, if you really want to have it as a, maybe a slightly bigger event, if you want to have some international folks as well, then we can think about it. Maybe it could be a 3 full-day event. We'll have to think. I mean, those details you guys can discuss and then figure out. And
But I have a question. So, what are the timelines we're looking at? I understand this year, as Alok was saying, that we got.
I think Alok would probably tell you more. I think this all happened in like 2 months, Alok, right? 1.5, 2 months maybe.
But we had made groundwork earlier because we were targeting May meetings. So we had already made the list. We had already contacted people. So we had done a lot of things like in the beginning, and then we re-looked at the list. But that took
But in 2021, it would be like we'll target to keep it in May only, right?
May.
I guess I don't know what is a good. May was the time we were looking at Mysore, and then this COVID hit. Then we about it for quite some time. I think October is started thinking about it just before the semester started, right? So it was.
Yeah, look, this offline version was happening 1.5 year almost, right? Every 1.5 year. Not see once in winter and once in summer. So
every year, no?
Summer every year, na Dilip? That's what I remember.
No, it is, I think, every year. Dilip.
Huh?
It is every year, no? During summer, it is to happen, no?
There was some break in between because
yes.
after 3 continuous times in Pondicherry, there was a gap. Then there was Goa.
Yeah.
And then
Goa was in December.
So Pondicherry, it was in December. Yes.
Correct.
Yes. And then the one in Simla that happened in the summer.
Summer and Shillong also in summer.
Shillong also in summer. Okay. So it looks like yearly.
Yeah. Almost yearly.
But I think 2021 May would be too close, right?
Yes.
Put in May. Too close to this side.
And also, see, we should get 24 young chaps to speak. I mean, not.
Yeah. I think we should at least have one recruitment season, in between.
Yeah.
Right?
Maybe October may be a good time.
Yeah, that will be also easy because most of the time I couldn't come to this because of this class with PhD interviews and those things. So
yes.
Yeah.
I teaching
Today also I
might
have
also.
PhD interview.
If we
In the
keep
first
on
time I could not
weekend, then it.
I think Sunita, this October is a good thing. October.
Yeah.
I agree.
So based on this puja vacation, you can schedule the conference.
Yeah.
Because people will be away, at least.
We'll miss a lot of Bengali folks, right?
If you do it during the puja vacation, you'll have a revolt from the Bengalis.
Make a good gap between these two. I don't know, either a little bit before that or after a week of puja.
Yeah. I mean, excluding those puja vacation days, I think it would be better.
Yeah.
Because again, May, June, July could be holiday for people. They may be doing some other.
Yes. So. And since it's online, so there is no travel constant. So anytime is fine. But since it is December, keeping again May, time is very less. So keeping October might be a good time.
Sriharika, you wanted to say something?
Yeah. Just the Conflu and this meeting are like very close, right? I'm just probably thinking if we have a little gap, it might be nicer. Just 1 minute.
No, that's true. See, usually this, as Alok was saying, this is supposed to be in May.
Yeah.
And then Conflu in December. That's usually the time frame that we typically have. But because of online and Alok really wanted to have SMYM 2020, not SMYM 2021.
That was Sushmita's idea.
Okay.
We must have it in 2020.
So I think that's how this happened. I know there are 4 back-to-back conferences for the next 15 days, but we really could. That's why we spoke to Conflu guys, and then we wanted to ensure that we have it before them.
But thanks to you, it's not really in end sem time or mid-sem time, so that would have been a bit difficult.
Yeah. So So I think we usually have 6 months gap between Conflu and.
Just a thought. So I was thinking, why not have like a 1-day meeting in 2021 and then push off to 2022 at a comfortable time, hopefully for a physical meet. I mean, just thinking differently from the.
You can, but you also need to have enough critical mass for next year, right? So every year this is passed on from one new generation to the other. So if you only get 12 new people, you might not have enough You need to think about it. I guess the next set of people need to work.
And also, if we plan to keep it in October, I think this thing is taken care, na, that it is too close by us.
No, see, when we were looking up at the list of people who have joined recently, I'm sure there are enough new recruitments already to have one full-fledged 2.5-day meeting for sure.
Yeah.
Because the list that Alok and Sushmita have made, I'm sure there are maybe 20 more names we could have accommodated, right? But because of the format, everything we could not. So, right, Alok?
Yeah, I think there will be at least 8 to 10 names that we had to leave out just because of the constraints.
Yes, I don't think we made a very exclusive list.
Yeah, I'm sure there are more.
Because we would have like reached this 30 limit and we said, okay, we are done.
And also, see, I have another suggestion which we should also think carefully. I think we should have at least one or two from NIT, one or two from other institutions.
And also one or two from industry.
Oh yeah, industry. And I'm sure there are a lot of nice guys who have joined other institutes, and I think we should also make an effort to really have them as well. RSC folks are also suggesting enough women participation, so I think all those are the things that we should that we covered. Yeah. So maybe we should keep all of that. Next set of organizers should also keep all of this in mind.
But for sure, industries. Because I think last time SMYM, there were like 3-4 people there. I remember.
Yes. Yeah.
I remember there was a very enthusiastic person also from some, don't remember the company. But yeah, that'll be good.
Yeah, true.
So last year there were the funders were, I think if I remember correctly, Anton Par were one of the funders.
Anton Par, yes.
Anton Par was there. Leica, I think, was there.
True.
So these are also people to keep in loop because they are always interested in funding. Shell I've seen at a couple of places. It was not there now, Ashika, last year. Shell was not there.
Yeah, Leica was also interested this year to fund, if it is offline and in May.
We didn't follow up more.
Yeah, we didn't follow
up.
up.
How does the funding thing work? Like, do you have a account register? Like how do you collect the money and who keeps in track of the treasury and all that?
Alok, you go ahead.
For IIC, we have a different way. I think IITs, we have a different way. We just write an application that will, at IIC, we write a email to or letter to the registrar that we'll be organizing a conference, and then they open a separate debit head for us. And then whatever money comes into for the conference.
That is fine. But the soft matter organization as it is, like, let's say you have some money left over from this year. How does it get transferred to the next year?
It will be passed on to you.
It will be passed on to you. It's very easy. Bank-to-bank transfer. We'll give you the UTR and.
I see.
I think we also got some money from ISR, right? They also supported or they gave some seed money to start with.
Yeah.
Yes.
Money is not an issue at all. I don't think money has ever been an issue for SMYM because typically you just work out and then make sure that, you charge, particular faculty so much, of course, offline mode was different because, the registration fee is higher so that, you cover the accommodation, food, everything. But yeah, I don't think money has been an issue for SMYM at all. So you don't have to worry about it. Yeah. Okay, so now that we have folks who are going to run the next SMYM, so should we decide on the October?
Can you tell the names once more? The names.
So it's going to be Sunita, Shobana, Ravi Kumar Pujala, and other folks from ISR Tirupati, and of course Danny as well as Priya are going to be part of it as well in whatever capacity they can, right? Because they're going to be busy hunting for jobs is what they said. So yeah.
Okay.
So maybe you guys can exchange an email, and maybe if you want to keep us in the loop, great. We would definitely be happy to help you guys out. So yeah.
Good. So we got volunteers for the next year.
Yeah, that's great. That's nice. Yeah.
Tradition goes on.
Yeah.
I'll let you about the experience next year.
Yes.
Yeah, it's not bad at all.
That's not bad.
I'm sure. Yeah. Okay.
I pestered Jyoti quite a bit for a lot of things in the beginning. So they were quite helpful. They had organized the last year's conference. So I'm quite sure you will need some information. And
So you're looking forward to get a lot of email from us as well.
Yeah. No, also like Alok, see, you should catch the person who pestered, right? Alok pestered somebody, you should pester Alok.
Oh, he confessed.
Yes. This tradition also will continue.
Alok has raised his hand already.
Yeah.
Good. By the way, this is not the last talk.
Tomorrow we have more.
Yes.
Yeah.
I will join most probably after 11 o'clock. I have a class in the morning, so after that I'll join.
11 o'clock, I think the conference ends, no?
No,
10:45.
11:30. 11:30 it ends.
The 12 literary section is on.
Mostly I will not be able to join, Basa.
Same with me. Alok.
PhD interview.
I may not be able to join tomorrow because there is one symposium in our department tomorrow on soft
Oh
matter.
yeah, we also have PhD interviews tomorrow. I'm
Today
sorry.
also I had.
missed
Tomorrow I have PhD interview, so mostly I will not join.
Anyway, those who can.
Tomorrow.
Sounds good then. So then we'll break and then we'll catch up tomorrow. Okay.
Yeah.
Thanks everyone.
Bye.
Thank you, Alok,
Bye.
Susmita, Vasa,
Thank you.
Devdeep, and everyone.
See you tomorrow.
Yeah, bye-bye.
Bye.
Bye.